Hello. I'm Zucky. I will be your MC for this morning, and let's kick things off. First up, we have Adrian Brink, co-founder of Anoma. No one knows what Anoma is, and I don't think you'll find out in this talk. But Adrian will be talking about shielded data availability.
All right, yes, indeed, this talk isn't about Anoma. If you wanted to find out what Anoma is, you should have listened to Chris's talk yesterday on Anoma Love Celestia. If you haven't seen it, watch the recording, it was a great talk. Cool, I will very briefly today, could I get a timer up? Well, we'll see how long it takes. Cool, yes, I will talk about shielded data availability on Celestia today, or the ability of how we can retrofit privacy guarantees and also forward fit privacy guarantees into existing protocols without needing to make changes to those protocols. Which, as you'll see in a little bit, is going to be quite important, especially when you start thinking on how do you want to build privacy-preserving rollups on a lot of these systems. So, before I start, let me give you a very quick TLDR on what Namada is, how it works, and sort of why we need unified privacy sets. So Namada, in a nutshell, it's asset-agnostic multi-chain privacy. Until really Namada, at least on the interchain, we didn't have the ability to have asset-agnostic privacy. Privacy was always tied to specific assets, right? Like when you think of what Monero or Zcash do, they provide very good privacy guarantees. Let me scratch this. Zcash provides very good privacy guarantees. And Monero provides, you should do your own research, privacy guarantees. But they provide them for specific asset types. As in the case of Zcash, they have ZAC, and in the case of Monero, they have XMR. And so users are now forced into this model where, for some reason, they have to hold or like pay for their milk in a store using ZAC, even though I think most people would much rather use USDT. And so what Namada brings, it effectively adds an extra type or an extra field to the nodes in a Zcash-like system to provide a unified shielded set where all assets, no matter where they were created or how they were created, can live in a unified shielded set. This has the tremendous property that you get low volume but high value assets that inherit the privacy guarantees of the low value but high volume transfers. So for example, a very trivial example here is all the USDT private transfers in Armada provide privacy guarantees to your like $100,000 NFT. And this is really the only way to get privacy guarantees for long tail assets, which don't have a lot of inherent volume. But due to this, you can inherit the privacy guarantees of sort of the entire shielded set. And the other big thing is, it means we don't have to keep forcing users into accepting specific assets in order to be private. Users can bring user-generated assets. I would assume in most cases it's going to be something like USDT, USDC, but if people sort of in 2 years from now want to create a new fancy stablecoin, that fancy stablecoin can inherit the last 3 years of sort of shielded set activity, and as a result has a much stronger privacy set at launch. The way this works with Armada is that Armada is a base layer chain. It's a sovereign L1 that connects to other systems via IBC. Side note on IBC, if you are thinking about building a bridge, don't read how IBC works. This mostly solves all your problems. Custom bridges are terrifying and they're very prone to errors. So with Armada, you get permissionless connections to other chains via IBC. So in the future, if other chains pop up or assets on other chains pop up, those assets can also freely flow into Armada. And maybe one of the coolest things is we have shielded set rewards in Armada, which means that the Armada governance unit can effectively incentivize rewards to be paid for holding assets in the shielded set. And this is actually very important because most people at the moment treat their sort of privacy as in, I want to have privacy right now for my asset. But this is actually really problematic because that means you sort of go from a transparent system into a shielded system and then back out. Now you have sort of a lot of statistical attacks that you can possibly pull off against this. So the much better idea is that you mostly want to hold all your assets in a shielded set all the time. And when you want to use them somewhere else that doesn't work with the shielded set, then you want to make them transparent. And the cool thing with Armada is you get shielded set rewards within the shielded set. So as in, if you hold some ETH in the shielded set, there may be incentives there that get paid out in the shielded set in the native asset of Namada, just by holding assets in the shielded set. Also, if anyone here is thinking of building private lending platforms, you need the convert circuit that enables shielded set rewards because it's roughly the same idea. You have a transparent list of sort of conversion rates for specific asset types, and you can then upgrade specific assets in the shielded set. For example, you can go from like Osmo at Epoch 1 to Osmo at Epoch 5, and at the same time, when you do this upgrade, you claim the rewards for it. Yes, this convert circuit is fully documented. If you like cryptography, you should check it out. Cool. Now coming to shielded actions. Once you have assets in the shielded set, you want to ideally have the ability to interact with the rest of the ecosystem, whether this is on the interchain or sort of within other specific L1s from within the shielded set, right? You don't want to have to take out your money from the shielded set all the time in order to use, let's say, a osmosis pool. So shielded actions is really the generalized case of how you interact from within the shielded set with application logic somewhere else. And really this can mean with specific dApps, for example on Ethereum, but this can also mean with specific app chains like Celestia or like Osmosis. And let me quickly walk you through an example here for Osmosis because this is sort of very instructive, I think. You hold some assets in the shielded set. You want to make the choice that I don't like the atoms anymore, I want to now hold some Osmo. Traditionally, what people would do is they would personally take the money out of the shielded set, transfer it over IBC to Osmosis, swap it on Osmosis, swap it back, right? And this is sort of, normally they would go to their standard Osmosis address and then sort of do the swap there. With Namada, you can instruct the validator set to do actions on your behalf. This is really the right way to think of this. You can instruct the validator set to take some action elsewhere while staying within the shielded set. So you can construct effectively a zero-knowledge proof. In Namada, it says, I would like to swap X for Y. Then the validator set will take the assets via an IBC message, bring it to Osmosis. On Osmosis, use the IBC memo to execute the swap. The counterparty or the person that executed that swap is the Namada validator set. It is not some specific person. It is the entire chain sort of wanted to do a specific swap on Osmosis. That swap gets executed. The assets get returned from Osmosis via IBC again, and they enter the shielded set again, at which point the user has full control over those assets again. And there are some downsides here, which is specifically due to latency. If you start thinking on like, what does this actually mean under the hood? This means at least one IBC message, which means at least like 1 or 2 blocks confirmation on the origin chain, as well as 1 or 2 blocks confirmation on the receiving chain. So you're talking on like maybe 30 seconds latency here. This is like not instant. If you're on a system that has sort of like 1 second block times, it's going to be hard to get the same kind of latency guarantees as soon as you want to hop between multiple chains. But the really cool feature now is that you have shielded swaps. And none of the core systems needed to actually change what they did. Osmosis provided provided swaps, and Namada provided privacy. But we can start integrating these systems using IBC in order to actually have very complex user flows where we can start in a really modular way combining all these different systems in order to get something that is, like, from a user perspective, much more useful than individual components. Let me quickly also walk through the architecture, how this actually works. This is sort of the heart of Namada is the multi-asset shield pool. If you're familiar with the sapling circuit on Zcash, this will look very familiar to you. You can really at a high level think we've added an extra, identify an extra field to the node types in the sapling circuits in order to have an asset identifier so that all assets can share a unified shielded set. What happens in sapling actually is that you can instantiate sapling for other assets other than ZEC, but I can identify as an external observer which sort of shielded set you interact with. Whereas in Namada, an external observer can only see that someone was interacting with a shielded set, but they don't know what actions were taken. This could mean that I transfer this to an address that I control myself. This could mean that I transfer this to an address that someone else owns. This could mean I wanted to execute some shielded swap somewhere else, or I want to submit some data to Celestia in a shielded manner. So this is really powerful actually as an abstraction because it can work with arbitrary assets. Yes, and so the basic idea is that you can sort of go into Namada transparently, then go into the shielded set, do whatever you want to do in the shielded set, go back out, if you want to take your assets back out, and then go wherever you want to go via IBC again. Yes. So this is sort of the entire architecture, and I won't go through the entire sort of slide, but just to highlight a couple of things here, Namada comes with cubic slashing, which actually means that if you should be really careful which validators you select. The high percentage of a validator set commits an infraction, the higher the slashing rate rises exponentially. So if you've ever been slashed on Cosmos, for example, slashes are constant. If 30% on Namada commits a fault, slashes are going to be tremendously high. So there's really now an incentive to actually start splitting your delegation across many different validators that run different security models. Yes, Namada on the hood just uses comment BFT, so you get fast finality BFT, you get all the IBC integration. The state machine isn't using the Cosmos SDK, it's written by hand in Rust to implement a bunch of the cryptography. Yes, and we also have a custom Ethereum bridge, mostly because we don't have IBC adapters to Ethereum yet. If anyone in the audience wants to do cool work, please work on integrating IBC into Ethereum. It's not that difficult, but it just requires engineering effort in order to get it done. And this is also true, really the way the interchain ecosystem or the multi-chain ecosystem is going to work is we should be building IBC adapters for other systems. For example, there's no reason why something like Near or Polkadot or any fast finality modern BFT wouldn't be able to speak IBC. Yes, now coming to shielded data availability. How does shielded DA actually work and why is it useful? Again, the model is roughly the same thing, which is a user's in the shielded set, they want to interact with Celestia, they want to be able to post some data to Celestia. The user has to generate a zero knowledge proof, ideally on an edge device. Within Namada, this instructs an Namada validator set to effectively submit data to Celestia on behalf of that user. And again, the interaction that the world observes is that the Namada validator set submitted data on Celestia. This could mean that this is an individual person, this could mean there's 100 people behind it, but the world doesn't know. And when you start thinking on what kind of rollups you want to be building, this is actually becoming incredibly important, especially for privacy-preserving rollups. If you have privacy-preserving rollups where individual users want to be part of this rollup and have to submit data to Celestia, it means that in the current model without shielded data availability, they would need to figure out how to safely submit those individual transactions to Celestia without revealing who they are. So in the current model, even if you had a privacy-preserving rollup on Celestia, users would need to be incredibly, incredibly careful, and this is almost impossible to achieve, that they can privately pay transparent fees on Celestia. With Namada, Celestia doesn't have to worry about this problem anymore and how you get private fee payments working. Rather, we can say, well, we have these two systems that each do their unique thing, but by combining them, you can start submitting using the feature sets of both effectively. So whatever feature set Celestia may even offer in the future, using shielded DA, you can always submit that data privately on Celestia. I think there's also an interesting other aspect to this where privacy has a lot of benefits, but it also has its complexity on an end user, because all of a sudden data moves from the center of the network, right? When you think of something like Ethereum, data all lives in this globally distributed, globally readable database. In a privacy-preserving world, this data starts moving to the edge devices, where individual phones need to hold this data. So one big question is, are users going to store all this data themselves, or are there going to be services where users can, for example, offload encrypted nodes to? And this is, I think, a future direction that I'm not exploring too much in this talk, but that is really interesting to think about for future research on how can we leverage data availability solutions to provide guarantees to users that they can get back their data, for example, their encrypted nodes, which they will need in order to access their funds. An interesting other research area here is oblivious message passing, or how can you query a data source like Celestia in a privacy-preserving manner, because one of the, in my opinion, the most valuable data set most likely in this space is actually Infura. because everyone has access to all the writes to the chain, right? Like if you scan Ethereum, you see all historic writes. But Infura is like one of the only companies in the world that has access to 99% of all the reads, which is the much more difficult to obtain data set in sort of in the world of blockchains. And so with oblivious message passing, we can actually start thinking on how do we have reads against full nodes that do not reveal exactly what kind of key in a Merkle tree I'm looking for. As in, like, right now I go to a full node and go, I would like the value of this key. With oblivious message passing, you can live in a world where you query a range of keys and it's not clear to the full node exactly which key I wanted to ask for. Yes, this sort of leads into the modular thesis a little bit on we should be splitting concerns. Not every chain needs to do everything. There's a clear benefit to standardization and specialization. If and only if we have decent interoperability protocols that can actually make this sort of specialization still composable. So I think we're clearly going to head into this direction, and sort of outside of execution, settlement, consensus, and data availability, I think we're also going to see more specialized chains around privacy guarantees, around sort of transferability, tradability. I think we're clearly heading in this direction, but this becomes much easier to build for effectively as an engineer, because so yeah, instead of writing everything, like if I think about this in terms of software, instead of writing everything as one large monolithic monorepo, we start writing individual libraries that individual other systems can start consuming. Yes, and this is sort of, I think, one of the last slides, privacy as a service. Namada is going to start providing this, where you can use Namada to drive actions on systems that you actually want to use for other reasons, but you want to retrofit as a personal choice privacy into those systems. For example, maybe some people want to trade a lot, maybe other people want to use Celestia a lot. Namada actually doesn't care. Namada just wants to provide really good privacy guarantees for whatever users want to do on other systems. And I think we're going to see this more and more, because there are lots of interesting ideas being built, and very few people have, or very few teams have the amount of cryptography engineering required to make these systems private, as in making every system inherently private is a very difficult task, because all of a sudden you need to start thinking like, how do I build proof of stake fully privately? That gets very, very complicated. It's very interesting, but it gets very complicated. And so with privacy as a service, we can rather say, we can build individual applications and individual dApps, and we can retrofit privacy into them in a very transparent way for users. Yes, if you'd like, there are more resources here, Discord, Twitter, the Namada testnet. Yeah, thank you very much. I should leave the clicker here.
Great job, Adrian. All right, next up we have Magnus, co-founder of Skip, talking about sort of modular user experiences, and definitely like an increasing trend of people who think about MEV now coming around to being able to sort of apply that mindset to improved UX. You're taking this? Yeah.
Hey everybody, nice to meet you. So I'm Magnus, first time public speaking for Skip, so we'll see how it goes if I crash and burn. But when I was a kid, I really liked this game Neopets. Anybody played that before? Maybe when they were a kid? Yeah, so little game, you know, you basically like raised these animals and you did things with them. And I remember the first time that I tried to play Neopets. I went home and I just typed in Neopets into my browser. And it didn't work, right? Because I missed the www dot and I missed the .com. And I was confused. I didn't understand, like, why didn't this thing just work? Like, I went back to my friend, I asked, like, how do you actually put this thing into your browser? And then once I learned, I was like, okay, I guess I just have to do that. That's just what you do, right, in the internet. And then comes a time like later in your life when you understand the internet, right? You understand TLS, and you understand DNS, and you understand the name servers and how they all route together, you probably get a little bit too lost in the sauce, so to say. Like you understand it maybe too well. But the internet still works, right? There's still that kid who just does that, puts it in, and everything just happens. Understanding it isn't required for making the internet work. That is to say, the internet has great UX, right? You don't have to understand it at all for it to actually work. And I'm going to transition that into sort of like IBC, which I would argue has shit UX. Should be clicking. Maybe? There we go. IBC is shit UX. Trust me on it. And I'd say this is sort of the same thing for crypto in general, right? You really have to understand the tech in order to make it work. You have to understand wallets. You have to understand the bridging protocol. Has anybody ever done an IBC transfer by chance? And I don't just mean like, using osmosis, which is like easy mode. I mean like, sort of like having to put in your channel ID and understand what paths it has to go through, and basically having to know the underlying protocol in order to actually use it. So one of the really, really, really annoying things about IBC UX is that you have to understand this concept of pathing, right? So if you want to go from one chain to another chain, you might not be able to take the most direct route there. So for example, in this case, if you want to go from Alice's source to Alice's destination, you can't go directly there. You actually have to unwrap it by going initially through the token origin, right? And so it's very different than the internet in that you really have to understand the underlying protocol in order to use it properly. And it makes sense why it's like this, right? Like you're picking up the security assumptions of each underlying intermediate chain. Therefore, you have to unwind it through those to sort of, basically have it become the token that it once was. So you end up with this situation, right, where you have all of these IBC denoms all over the place. They're all interwoven with each other. It's just like, look at all those tokens, right? What are they all doing? Why are they there? I don't need them. I don't understand what they are. And so I love this quote by Chris Goes. It's, do you think God stays in heaven because he too lives in fear of what he's created? It's obviously not an actual Chris Goes quote. But it is from Spy Kids, and that's sometimes how I feel when I'm using IBC. So we tried to solve this. We tried to make basically what that Neopets-like experience is for IBC, where you don't have to think about the www, the TLS, the DNS, the name servers. You just use it, right? You just use IBC in the way that you want to, right? So this is that same issue, right? So if like starting on chain A, you want to go to chain D, every path that you go through basically will change the token, right? It's like you and your friend are basically on the Upper East Side. You want to go to a bar together. I take the 4 train, you take the 6 train, does different number of stops, and you end up as different people. And you're just like, what's going on? That's essentially what happens to IBC tokens as they traverse the interchain. Different paths will actually change the token. And that, of course, does not intuitively make sense. And users will lose their funds if they don't follow this, right? They will end up in a denom that maybe has no liquidity, and there's no DEX, and maybe they don't even have the gas token. And so basically, interchain UX is screwed by all of these different problems. And it's true for Cosmos. You guys can learn from Cosmos. We've done many different things, and we've screwed up a couple of them. But when it comes to the roll-up world, it's going to become 10 times worse, absolutely. Because you'll have way more pathing, and you'll have way more gas tokens, and you expect users to understand all of that and have all those gas tokens. So basically, one does not simply send over IBC. You can't just use the protocol. You have to use it very specifically. How do we fix this? Well, basically, we need to do unwinding, right? So this concept of, if I want to go in this case from chain B to C, I need to first be unwound through chain A. And I can have somebody tell me, okay, here's a transaction that will actually unwind you through chain A or wherever you need to go automatically so that you end up in the right place. And abstract that into something super easy to use. Basically, you know, abstract that into a browser URL so that all the routing, all the DNS, everything else just happens underneath the hood. That's what we've built at Skip. Basically, this is, you know, somewhat of the structure of the API. The user gives the intent to transfer. We send back this multi-hop IBC message. Oftentimes, it does a massive unwinding flow. The front end sends back the user's signed receipt, and then they get a success. And so all they see on the front end is basically, I had my token here on this random chain. I don't know how wound it was. I wanted to go there, and maybe it's even a different token, right? And they just end up with that experience. But wait, there is more. So the ideal experience in our minds, and this might not be right, but this is what we believe, is you want to go in the future over IBC from any chain, any token, to any chain, any token. And that, of course, might require a swap, right? So now you've further complicated this workflow where you're not just routing the same token, you actually have to at some point change into a different token. And you want to do that in one click, right? You don't want to have the user have to go to different applications and figure them out and have to use them. So you want to just have this sort of all done in one transaction. So this also works with the Skip API. The way that we figured this out was there was some incredible middleware tech that was built inside of IBC called Packet Forward Middleware, which allows you to, once you get to a chain, it will automatically forward it to the next chain. And you can chain this together so you have multiple chains in a row, and then you use these things called IBC hooks that allow for arbitrary smart contract execution on any intermediate chain. So in this case, oftentimes what will happen is, you know, 3 unwinding flows, a swap on osmosis, and then more unwinding all in one transaction. So this is basically what it looks like. If anybody's interested in trying it out, we built this fun little front end called ibc.fun. And it's just what you think it is. Basically, it will show you the different routes and swaps that it's trying to do, and then it all completes in one transaction. So I don't know if this is going to play. Maybe. Looks like it's not going to play, but this is a demo of me actually doing it, going from osmosis to a different token, and just seeing sort of like how fast it is. It went over 5 different routes, which is, you know, in IBC quite complicated. And then, you know, it all sort of completes extremely quickly. So we're trying to figure out these other UX problems that we think rollups and IBC chains already have, right? And we argue that these main ones are these gas token issues where you have to have so many different gas tokens, and, you know, that's like a big ask for the users to have. This concept of sponsored payers, so basically, you know, you can subscribe to a wallet and they'll just figure out some of these issues for you. Maybe they give you like a gas tank model where you have all your gas in one place and they'll just swap it out into whatever you need. Best price disaggregation, and then also instant cross-chain settlement. You know, there's been a lot of conversations, I assume, about intents. I don't know what they are, but some people seem to. And how those might solve UX in the future, where you might just be able to give this intent of this massive cross-chain workflow, and then a third-party actor might be able to come in, solve that intent, and, you know, basically give you whatever you need on the destination. So if you're interested at all, the API is free. It's something that we made sort of as a public good. I think it might be technically interesting to just delve into sort of like the reality of IBC and, you know, what you can do with it. This is a problem that will be true for all bridges. This unwinding and winding problem will be true for Hyperlane, it will be true for many others. And if we want to have a permissionless IBC standard, or permissionless bridging standard, we really need to fix these issues, right? We really need to turn the internet into, or we really need to turn IBC into something like the internet, where you don't have to think about all of these different problems. You can just, you know, type in Neopets, and that's it. Thank you so much. Appreciate it.
All right. That was excellent. now we are going to pivot to a panel on Bitcoin, where we have Eric, Sunny, Connor, Sem, and John talking.
Ice cream, so good.
Yes, yes.
All right, so I don't know, has there been a lot of panels about Bitcoin or any talks about Bitcoin so far at this conference? Has anyone seen any Bitcoin talks?
Not specifically about Bitcoin, no.
So Sunny, I want to go to you first. I saw that you wrote a completely insane tweet a couple of weeks ago. I want to give you a chance to sort of elaborate on that. And you feel free to introduce yourself also. You wrote that proof of stake was a mistake. Could you, was that a joke, or is that something that you
It was a little bit of a, just in a moment of frustration, I guess. But it was mostly just around, like, I was frustrated with, like, staking derivatives at the time, where I just saw that, like, we built, or, like, how these, like, staking derivatives protocols are evolving is we're effectively turning our systems into proof of authority systems. And because, like, the staking derivative providers are just basically hand selecting the validators. And I was like, you know, we spent so much time designing, like, security mechanisms into proof of stake and, like, slashing and, like, making sure, like, there's bonding predictions. Like, we've just, like, undid all of them. And it's like, what was especially frustrating was just the fact that, like, core protocol developers are pushing these things. And it's like, wait, why did we spend all that time on proof of stake? We should have, if we wanted to, we could have probably just built a proof of authority system into the protocol, like actually maybe have token holders use governance to vote in validators and stuff like that. So I think that was like the main point I was trying to get across.
No, I think it's super interesting because we have in crypto lots of proof of stake systems, and we have the largest cryptocurrency is Bitcoin, and it uses proof of work. And I don't think that any one of us can for sure know how the economics of these proof of stake systems are going to end up, and how the centralization due to staking derivatives are going to impact these systems. So even though, like, you can have proof of stake as your preference, you can think it's much better than proof of work, but it's kind of nice that there's a proof of work system there that we can use as a backup plan if there turns out to be some issues with proof of stake. I think though, like, at least when I look to myself, if I think about Bitcoin and I think about how is that system going to reach like mass adoption or scale, it feels like the Bitcoin community today have significantly tied themselves to the mast of the Lightning Network. So the Lightning Network was invented by in a white paper in 2015 by Taj Dryja and Joseph Poon that basically connects a bunch of payment channels together and leverage that system to route payments across the network. And I was listening to a podcast with David Marcus from who was the president of PayPal previously, and then worked for Libra for a while, and now has a company called Lightspark, where they are trying to make Lightning work. And one of the things that he said is that in Lightspark, they have a functionality called Lightspark Predict, which uses AI in order to figure out how you predict which path you should try in Lightning to make a payment. And I would kind of say that if your payment system requires AI in order to just find a path so that you can send a payment, that's not necessarily this doesn't sound like a functioning payment system. So I want to maybe we'll. Is there anyone here that sort of has? Do you see necessarily a future for Lightning, or do you think that there's, if we want Bitcoin to work, do you think that there is actually a good reason, if we want to take the biggest cryptocurrency out there and we want to make it usable for payments, is there a reason to perhaps explore other layer 2 technologies on top of Bitcoin?
I will yeah, have an opinion about that. So I think Lightning and payment channels, generally speaking, makes sense for high throughput kind of use cases, fast, gives you really fast, high throughput payments. And I think it would be good for payments that the whole world doesn't need to know about. Because like with any blockchain, whether it's a layer 1 blockchain or a roll-up, you kind of have to tell everybody in the network about this payment, and they have to store it forever. And so for payments, like maybe machine-to-machine payments or other kinds of micropayments, something like Lightning or payment channels, generally speaking, I think maybe makes more sense for that kind of use case. But yeah, it still remains to be seen what that model really gets product market fit for.
I agree with that, especially because I don't know about Lightning technical problems and the progress on that too well, but definitely when we're talking about in the context of rollups on Bitcoin, at the end of the day, Bitcoin has a maximum of 4 megabyte data throughput every 10 minutes, and there's a limit of, even if you're leveraging a rollup, there's a limit of number of transactions you can compress, squeeze into that. As a result of that, Lightning definitely serves a pretty interesting purpose, especially in the case of Bitcoin.
Payments are the original use case for cryptocurrency. It's the least speculative proposed use case for cryptocurrency. And payment channels have some amazing properties. They can be extremely low cost. They are good as finalized instantly as soon as you receive it. You don't even have to wait for a block time. Even though in Ethereum and the rest of the blockchain scaling research has sort of started to focus on things like rollups now, and we sort of left behind payment channels, those properties are lost on rollups, and it's certainly worth trying to make the technology work if we can to get them back.
To be fair, if you can scale data throughput to the levels that your payment network can leverage it really well, and we know that we can scale data quite well in a way that we can't scale execution, so we can still have similar throughput systems with data scaled DA layers like Celestia, but especially in the case of Bitcoin, you just can't do that.
So Sunny, do you care about Bitcoin at all these days? Is it something that, I mean, I know that you work in the Cosmos ecosystem, and is there a sort of a vibe in that community that Bitcoin is a lost cause, or are there actually people that care about improving Bitcoin and coming up with solutions to improve the system? And how do you feel about it personally?
So for me personally, I spend a lot of time thinking about Bitcoin. I still, I got into Cosmos because I wanted to build the app layer for Bitcoin. I was like, I was working at Consensus for a little bit, and I was like, they're doing all this all this Ethereum stuff is cool, but what is this ETH shitcoin? And we got to build for Bitcoin, and Bitcoin is an app chain. I was like, oh, okay, good. This is simple. We're gonna do payments and issuance here, but then Blockstream was the one who came up with the idea of sidechains, and it's never really shipped it, right? And I just saw Cosmos was the place where people are actually building sidechains and app chains, and so okay, we're gonna issue Bitcoin on the Bitcoin blockchain, and then the BTC asset is gonna flow off into the Cosmos ecosystem and be the money of this ecosystem. And so that's kind of 5 years ago. That's how I got into Cosmos. Then got busy with shipping and building all the products and stuff. But now I think it's time for I personally really want to shift Cosmos back towards that original mission that was there for a lot of us. And so I really do think that the Ethereum ecosystem, it has this base money, and it has this huge ecosystem of applications around it. I do think that the Cosmos ecosystem has the second biggest ecosystem of applications, but we lack a base money. And I do think that this is I do think the future of Cosmos is to figure out how to bring Bitcoin and build this application ecosystem around Bitcoin. That's where we've been working with we're working with Axelar to build a proper decentralized Bitcoin bridge that bridges not just Bitcoin, but it'll bridge ordinals, it'll bridge BRC20s. we're talking with the Lightspark people about making so you can bridge via Lightning and stuff. So I do think that I personally think that Bitcoin is the future of Cosmos. Obviously, Cosmos is a very decentralized, distributed group of people and communities, so different people have different views, though.
I love that answer. Is it possible that I could get you to wear a Bitcoin builder hat?
100%. Thank you, thank you.
So we used to have a culture of like innovation and fun and building in Bitcoin. I don't know, John, do you wanna wear one too?
I gladly accept.
I think, like, honestly, the whole ordinals thing was really exciting to me, not because of, like, the technology behind it. It's not that, like, crazy or anything, but just the fact that it, like, brought this, like, renewed excitement to the Bitcoin community again. And, like, I think it's the first time in years I've seen Bitcoiners be excited about things, and I think it's just restarted this conversation that, like, I can reasonably see that at some point in the next 2 years, we're gonna see more soft forks into Bitcoin, get new protocol upgrades, which I'll admit, I did lose faith in like the rate of development on Bitcoin Core in the last couple of years, and I do feel this like sort of renewed excitement and like cultural shift in the community. Honestly, a big part thanks to like the work that you and Udi have been doing.
Yeah, I've heard a lot of people say that there's like sort of a renaissance of building culture coming back to Bitcoin. And one of the reasons that I want to talk about Bitcoin rollups specifically here is because we have this like massive modular ecosystem now where there's executioner environments and there's proof systems and there's all these different tools that's being massively invested in, innovated upon, that like if Bitcoin can just tap into all that innovation and try to bring some of that home, then we could sort of leapfrog the Bitcoin space several years into the future. So on the topic of Bitcoin rollup, I think maybe it's a good idea to sort of give a lay of the land so that people understand, are rollups on Bitcoin even possible? So we've had this conversation in different formats and different podcasts like 15 times, so I think we can just summarize it super quickly. So in Bitcoin, what you can't do, for example, is that if you have one transaction that says x equals 5, in another transaction you can't multiply that value by 2, so x becomes 10. Bitcoin doesn't have like state and variables and values in that sense. The only thing that Bitcoin has is unspent transaction outputs. So what you can do in Bitcoin is you can reference an unspent transaction output, you can combine it with a script, and now you have a new unspent transaction output. But you can't really reference other variables in Bitcoin, so you can't really build like a roll-up on Bitcoin today. But what you can do with Bitcoin, so for example, we put JPEGs on Bitcoin. So that means that Bitcoin works as a data availability layer. All you need in order to build a sovereign rollup on a blockchain is that you need some space to put that data blob. So in the context that we're talking here, it's like initially we're talking about using Bitcoin as a data availability layer in sort of the modularity sense. We can build sovereign rollups from that. And then there is this whole body of discussion around, okay, what upgrades would be necessary at the Bitcoin base layer in order to enable rollups. And then I think the consensus is that we would need some way to sort of store state on the Bitcoin chain, either through a covenant construction or something else. And then we would need a way to validate a fraud proof or a validity proof. So we would need, like in Bitcoin right now, for example, you can't look at the Merkle root and verify that a value belongs in that Merkle root. You also can't validate a zero knowledge proof. Bitcoin is like a super primitive calculator. You can only do like add two values together, and you can't even store that value anywhere. But you can use it as a data availability layer. So we're going to talk a little bit about sovereign rollups. So for those of you who don't know the difference between a sovereign rollup and a real rollup like Arbitrum or Starknet or Optimism, it's basically that the sovereign rollup doesn't have a bridge between the layer 1 system and the layer 2 system maybe we shouldn't even use those layer numbers anymore. I think that the modular space is trying to move away from that. But you basically can't bridge Bitcoin trustlessly into the second layer, the Bitcoin asset, and bridge it back. But you can use Bitcoin as a data availability system to store a bunch of transactions and execute the state from that and create expressive layers on top of Bitcoin, basically. So if we put ourselves in the situation that, okay, we think that rollups on Bitcoin are interesting, and the first step to get there is to build a sovereign rollup and then build some type of bridge, some trusted or crypto economic bridge into that second layer. So I think it's more interesting than going back to the conversation like how is it possible to build Bitcoin rollups? It's more interesting to talk about, okay, given the tools and applications that are out there today, if I gave you like a challenge and I said, okay, well, by the end of this year, we need to have a first sovereign rollup on Bitcoin. How would you, if you have that like as your mission right now, that's what you have to do, and you will get fired if you don't deliver on that. What tools would you leverage from the sort of the existing domain of modularity or whatever in crypto in order to reach that goal? We can sort of start here and then make our way to the end of the row.
Okay, perfect. To start, I want to de-emphasize the idea of real rollups versus sovereign rollups. Sovereign rollups just don't need a smart contract or any execution at the base layer to verify your fraud proof or your validity proof, but that only means that at the start, without like verifying that bridge, it doesn't have that bridge. However, the security guarantees of a smart contract rollup and a sovereign rollup are the same. We just create a proof of the sort that we read all the data from the base layer and we processed all the transactions correctly. Later on, these like sovereign rollups can also have bridges. So you can still derive all of the Bitcoin security and build an application on top of it. And the only thing that you would be lacking is the ability to bridge Bitcoin. And to be fair, that's a big missing point. So yeah. About the stack that I would use to build sovereign rollup on Bitcoin, I'm extremely biased. We at Sovereign Labs, we work on Sovereign SDK. So there are already teams working on a Bitcoin adapter to make Sovereign SDK built rollups deployable to Bitcoin. And so I would definitely go with that, and I would choose our ZK option. We provide both optimistic rollups and ZK rollups using ZK single round for proofs or ZK proving everything. But I would go with ZK because the block times on Bitcoin are quite long, so you don't take the full advantage of being an optimistic rollup.
So you guys are already are working with a team that is building an adapter to leverage Bitcoin as a data availability layer.
Correct.
So maybe to you, Connor, perhaps you could give a little bit of an intro to what Rollkit is. And I think that are you also working on a similar problem?
Yeah, Rollkit's also a SDK for provisioning sovereign rollups. It's meant to be quite customizable. You can put in any kind of virtual machine that is compatible with the ABCI interface, which should be any VM you could conceive of, because it's a very flexible interface. Rollkit also wants to support all different kinds of proving systems. We have fraud proofs for Cosmos SDK already. We hope to add different kinds of ZK proving schemes as well. And also we have a integration into Bitcoin already. We developed a implementation of the DA interface for the Bitcoin Taproot witness. That was done by Javed Khan on my team, who should be here and unfortunately couldn't make it, but we miss him. And as for design considerations for a sovereign rollup on Bitcoin, what features would you want? What token would you use? What kind of VM would you pick? Ideally, you would use Bitcoin. I think Bitcoiners want to use Bitcoin. I don't think they want any shitcoins. but you can't trustlessly do Bitcoin up to a sovereign rollup like we talked about. So would they accept some sort of trusted bridge? I'm not sure. If the answer is yes, then that's what you should do. You should have some sort of trusted bridge or ecosystem of trusted bridges to get Bitcoin up there so that they can use the money that they believe in. If they don't want to trust a bridge or a committee to attest to those bridge transactions, then you've got to make sure the token on the sovereign rollup is something that aligns with Bitcoin. Do something without a pre-mine, do something without insiders, maybe even airdrop it to the Bitcoin UTXO set when you launch the rollup. For features, there's a bunch of things you could do. You could add payment channels. You could give a Lightning Network to this thing, and it would have more capacity to open and settle those channels than Bitcoin does, because I think it has more block space. With the 4 megabyte Taproot witness, that's enormous. That's bigger than not bigger than a Celestia block, I can't remember, but it's pretty huge. You can do a lot on there. You could add privacy to it. You could add Zcash style privacy that Bitcoin base layer doesn't have. And it would have the security of Bitcoin. A sovereign rollup is basically an app chain, but with close to the full security of whatever it's deployed on.
Yeah, so I just want to stop here for a brief second and reflect over the fact that there are 2 modular builders here that have already built hooks into the Bitcoin protocol to start leveraging that as a data bank. So all that stuff that is happening like out there in the Ethereum world, in the Cosmos world, in the modular world, because we have these hooks into the Bitcoin base layer as a data storage, all of that stuff can start creeping back into the Bitcoin ecosystem now. So like Bitcoin builders, they're gonna have to, they're gonna get challenged by this whole other ecosystem that has been practicing and building applications for these layers for years now. Do you guys, Sunny and Light, do you guys see any risks with that? Is it maybe in Bitcoin's best interest to just stay as pure and as far away from all of that staking derivatives and MEV and zero knowledge proofs and complex math? Like, is there a risk that as we bring the innovation that has happened sort of outside the Bitcoin space, that we also bring with us the issues?
I think the point is that like you keep the Bitcoin core chain like as simple as possible. There's a few upgrades I would like to see, mostly around making bridging a little bit more trustless. But beyond that, I think like all the stuff like should be experimented with at the edges on these like new chains.
Yeah, from the research that I've seen, MEV tends to be stay on the layer that the transactions are actually executed. And so if you have like rollups on Bitcoin, the sequencers might be capturing MEV, but there is not really opportunity for the Bitcoin miners to get involved in that, directly like as the mining network. And so I'm not too worried about MEV in the context of either sovereign rollups or even like layer 2 rollups on Bitcoin. And like Sunny, I think the changes that we want to make to Bitcoin would be relatively minimal just to enable like trustless bridging. And then beyond that, I think that the application design space that is opened up by rollups is huge and would be really valuable to Bitcoin, whether it's more private transactions like Connor was talking about, or whether the focus is on scalability because you can do like massive like witness aggregation into zero knowledge proofs and get transactions down to like just like a dozen bytes or so, which would be huge for throughput and improving scaling. So yeah, I'm not too worried about it. In terms of like your original question about the stack, I think what these guys are building is it would be a really great foundation for like a sovereign rollup. I also think that there are interesting possibilities that are opening up, like if we don't have trustless layer 2 Bitcoins or Bitcoin bridges, we do have things like crypto economic bridges, like what Threshold Network has built, or Nomic, which is a Bitcoin sidechain in the Cosmos ecosystem. Once you can get Bitcoin onto, let's say, Nomic, you can use IBC to connect Bitcoin to any other Cosmos chain. And so you could either, build like a modular system there, where you move Bitcoin into the Cosmos, and then you could use Celestia as a data availability layer to have an even more high throughput chain on top of that. So I think there are a lot of possibilities that are either already here or like just around the corner, like as these systems start to mature.
So Sonny, I saw that you were nodding a lot. Is there any connection between this and sort of IB? Is there a way to connect IBC to Bitcoin using a rollup?
Yeah, I've thought about like what would IBC on Bitcoin look like, and really the point of IBC is to bring the trust assumptions of your bridge as close to the trust assumptions of your consensus protocol as possible. And I think the direction that I'm most interested in right now is mostly around drive chains. I think it's basically like, I think drive chains are the proof of work equivalent of IBC, where it's saying, hey, let the bridge be operated by, instead of the validators of your proof of stake system, but let it be operated by the miners of your proof of work system.
Yeah, I know that we have at least 3 fans of drive chains on this panel. So I want to talk about something slightly different, which is I've at least made an observation that if you look at the roll-up space in the Ethereum world these days, you see that, for example, Optimism has the OP stack, and ZK Sync came out recently with a ZK stack, and at the EthCC event, Starknet announced the Starknet stack. I think what is basically happening is that these different roll-ups that exist on Ethereum today are trying to modularize their specific stack so that other builders can deploy app chains and other instances of the same roll-up, which we have seen with example with Binance launching BNB OpStack and Coinbase launching Base, which is built on OpStack. And I think that the reason that these teams are doing that is because they want other builders to sort of use their tools so that everything that they build, everything that Coinbase builds on Base, everything that Binance builds on this BNB OpStack chain will become compatible with sort of the mothership. So everything that happens there, Optimism will just be able to integrate with no friction at all. So I'm thinking that is that a trend that you guys have seen also, that these sort of stacks are emerging, and is that maybe something that we could leverage for Bitcoin? Like, could we do something like taking OpStack and putting it on Bitcoin? Could we take ZK stack and putting it on Bitcoin? Could we take the Starknet stack and putting it on Bitcoin? And how would that? Is that like a direct like orthogonal thing compared to what you guys are building with these SDKs that are building sovereign rollups on Bitcoin? Or are there synergies here? Like, could you take ZK stack and then use Rollkit to put the data into Bitcoin? Or how could you take like a stack like that I think may emerge as really powerful software frameworks? Could we leverage those with the types of tools that you guys are building?
So you can totally take these stacks and modify them to work on Bitcoin. The key part is Rollkit and Sovereign SDK is inherently being built to be like for sovereign rollups to start, and then you can add bridges to them. And that makes it really easy to integrate it at Bitcoin because we're just using Bitcoin as a pure data ability layer. With Optimism, even with the integrations, OP Stack, even with the integrations they did to Celestia so far, Ethereum is the settlement layer, and then Celestia is like the data layer. They still require that smart contract interaction. So to derive full Bitcoin security would not be possible, at least, like, unless they do heavy modifications to the OP stack in a way that might currently might introduce like security vulnerabilities, because they're trying to stay as close to Geth as possible. But over long term, it's definitely possible. But they need to get out of the smart contract roll-up framework.
I'm actually like personally like a little bit less interested on like using Bitcoin as a data availability layer for everything. It's like I see the Bitcoin proof of work is actually a really good data availability system, because what it does is you put data on there and miners are incentivized to broadcast it as widely and as quickly as possible, because they want as many people mining on top of their block as possible. So it's really good as this like incentivized fast propagation layer, but also as this like hard timestamping layer. And I think like trying to put all your data onto Bitcoin is, I don't know, to me at least right now, seems like not a good use of like Bitcoin block space and resources. But I think putting the types of data that you want this sort of hard timestamping for is what's more important. So I'm an advisor to Babylon, and what they're doing is like say like, hey, okay, what can we actually benefit from putting on here? Why don't we put our proof of stake block headers on here? And that way we get this like strong timestamping system, and we basically make it so we can, by putting proof of stake block headers on there, you basically can solve these like long range attacks that you get in proof of stake, get the best of both worlds of proof of stake with proof of work. And I think like being a little bit more smarter of what kind of data, like I think different data availability solutions have different benefits, and like being smart about what type of data you put where. And so, yeah, block headers, I think that belongs on Bitcoin. Putting your entire block data, I don't see the point.
Yeah, Bitcoin ordering is very valuable to people. We've had Stacks, which is this thing that checkpoints its blocks onto Bitcoin, and Babylon, which is doing something similar. And when Rollkit announced the Bitcoin sovereign rollups, a lot of people were confused on what the difference is. And the difference is Rollkit puts the full blocks in the witness. But kind of, what's the point of that? It's not so clear. Data availability is talked about a lot in regards to rollups. Sovereign and settled, where there's an on or off-chain light client, where you have a commitment to the results of the state transition and some sort of proof that it's correct, and then you want to verify somehow that the data is available. And if you can verify that a lot of data is available without needing to download all of it, then it can be described as very scalable. Bitcoin doesn't have sampling, so if you want to verify data availability for Bitcoin, you have to download the whole block. That's the whole 4 megabytes. So it's not like Celestia, where you can verify the whole block is available with only some small samples of it. So there's a good argument that it's really the ordering that we care about and not necessarily the data availability.
And I like what you said previously, Connor, that if we wanted to build a roll-up system natively for Bitcoiners, for the Bitcoin ecosystem, like maybe you would try to do this even without introducing a new token. So are there other considerations, like if you were to build specifically for the Bitcoin ecosystem, are there particular use cases that would maybe be more interesting to build for Bitcoiners? Like, are there perhaps something on the privacy side? Maybe there are some things that doesn't have all that negative connotations that some Bitcoiners are worried about. Like, what are some? If we had, let's say we had an execution environment today that had expressiveness, that was secure, was either had the full data on Bitcoin or had some of the data, but was basically secured by Bitcoin and used the Bitcoin native asset. What would be some interesting use cases for that? We start with you, John.
Well, assuming a good trusted bridge for BTC, I think the use cases that are already popular on Bitcoin, just being able to do those maybe in a more scalable way. So like a Lightning channel management roll up where opening, closing, rebalancing your Lightning channels is like super cheap. That could be interesting. Privacy is also, I think, a significant pain point for Bitcoin users. Like if you've ever, tried to make your Bitcoin private, there's like these guides on the internet that are like 10 pages long, and if you screw up any of the steps, then all of your work is for nothing. And so, having like a zero cash, just easy button for privacy that just encrypts all your transactions, I think would be pretty useful. And then can't underestimate, I think, the utility of Bitcoin DeFi. It's a pretty big use case. I think over 1% of the Bitcoin supply is being traded or lent or borrowed against, on different chains. And so, yeah, just doing that in a way that where you also get the full double spend security of Bitcoin through the, Bitcoin DA / settlement layer, I think could be useful to a lot of people.
What about like a Bitcoin-backed stablecoin, like a USD that's backed by Bitcoin? Do you think that could be something that would be interesting to Bitcoiners?
Yeah, I think it could be, because right now the stablecoins that Bitcoiners have to use are like fiat stablecoins, backed by money in a bank somewhere. And so if we could actually use stablecoins that are backed by Bitcoin in a smart contract instead, I think that would be better. Like, we actually built one of, you can kind of consider it like a proof of concept of this on the Rootstock sidechain. It's the Sovereign Dollar. It's a Bitcoin-backed stablecoin.
And that's with over-collateralization, right?
Over-collateralization,
so we're not getting into like a Terra Luna situation with this, where it's going to end up with billions of Bitcoins getting sold because there's an algorithmic peg that sort of detaches. Right?
Yeah, it's over-collateralized. There's like efficient liquidation mechanisms, so it always stays, over-collateralized. At least that's the design, right? Like, there could be a flash crash and maybe black swan event, but yeah, it's not like a partially backed stablecoin. It's a fully over-collateralized stablecoin. But being able to do that on a chain that, gets the full double spend security of Bitcoin, unlike Rootstock today, which has its own independent security budget, can be reorged like independently of Bitcoin. I think it brings that kind of utility in a more, I think, Bitcoin native way.
Totally, but also to be fair, in any yes, these rollups will introduce general purpose programming to Bitcoin, using Bitcoin security, and I think the Bitcoin crowd, as I've seen at Bitcoin Miami, is extremely excited for that. But at the same time, since bridging Bitcoin will definitely introduce new trust assumptions, any Bitcoin-backed stablecoin will definitely not have the attractiveness as it would have had without any trust assumptions, for sure. I think what's more a bit more interesting, something that excites me, is that in a sovereign rollup, since you're reading the whole data space of Bitcoin and applying rules from there, you could also read into USDT transactions and represent USDT trustlessly on the sovereign rollup itself, and introduce liquidity in that way and build a DeFi ecosystem.
I'll be a little bit contrarian. Maybe we shouldn't do a general purpose VM. Maybe you just want enshrined DeFi, so that way you can avoid smart contract bugs, the fear of smart contract bugs, the upgrade authorities that people introduce as central points of failure to deal with those bugs, and have something that's more Bitcoin aligned and without all the things that cause Bitcoiners to push back so hard against DeFi on Ethereum.
That's such a great point. I actually wish that we had spent some more time talking about that, when we're talking about building ZK rollups and optimistic rollups on Bitcoin, we don't necessarily need to take the entirety of the EVM. We could actually go back to that thing that Bitcoiners used to say, that we're going to analyze what all these other altcoins do, and then we're going to take sort of the best parts, the things that we really like about them, and we're going to integrate them back home. So maybe we wouldn't necessarily want to take all the complexity of Solidity and the Ethereum virtual machine and try to cram that into Bitcoin, not only because there's sort of bugs inherent with that, but also because it's really difficult to prove the EVM if you're using zero-knowledge proof. Like, it's basically a system that's hostile to be zero-knowledge proof. And there are other virtual machines out there, like Cairo, for example. I had a conversation with Vitalik and I asked him, like, what do you think would be the best sort of virtual machine and language to run on Bitcoin? And I don't want to put words in his mouth, but I think he sort of was trying to point me towards Cairo as a better language to be zero-knowledge proven. So we don't necessarily, I think it's sort of a mistake if people think that we're talking about taking all the complexity from these smart contract ecosystems. There are sort of narrow versions of that that could be more focused on privacy or could be more focused on payments, only taking those. With that, we're kind of out of time. Is there anything that you guys feel like you want to say before we wrap this up? Oh, maybe that's it. All right, thanks everyone. Thanks for coming to the panel. If you guys are interested in building on Bitcoin, I'm definitely in the business of hearing your story, wanting to introduce more builders back into Bitcoin. I also have a company. We're hiring. So if you want to build roll-ups on top of Bitcoin, try to find me after this panel. And thank you very much for coming.
That was fantastic. Are we actually going to do something with Bitcoin, or are we just selling it to BlackRock? All right. We'll let the room cycle. Bitcoin was very popular. Who would have thunk? All right, we have Ethan Buckman up next, talking about modularism and money design, co-founder of Cosmos, CEO of Informal Systems. Here, oh, you've got a mic.
All right. Thanks, Zaki. Thanks, everyone. So here we are about to talk about the future of France, and all these losers just left the room, so they're going to miss out. But lucky for you guys. So I'm Ethan. If you follow me or know anything about me, you know I'm really into money, monetary design, trying to figure this stuff all out. When I told Nick, so we've been, excuse me, we've been working on a new project that we call Collaborative Finance, or Ko-Fi. It's our response to DeFi. When I told Nick I wanted to talk about Ko-Fi, he said, well, that's not really on topic. You should talk about something else. So I just changed the title to Modularity and Monetary Design, and of course, he was then thrilled. Now, the thing Nick probably didn't even understand was that Ko-Fi really is about a modular payment system design based on a system of intents over which we optimize with graph solvers that publish ZK proofs of integrity. So if that's not on topic, then what is, right? All right. Hi. Do I have a clicker or something? Yeah. Don't break the third wall. Is that what they call it? Don't smile at the photographer. All right. So, you know, I've long felt that money is the killer app. It's the ultimate multi-stakeholder computational use case, and yet we are still failing to actually have the impact. Oh, I'm supposed to stand where? Right here. All right. Thank you. And yet we failed to have the impact we'd all like to have, right? And so I'm going to talk a little bit about that, if I can get my clicker working, which I can't. Technical difficulties. Just keep talking. All right, so I believe what's on the next slide is a quote from me that says, if home is where the heart is, money is where the payments are. Because that's what I think money is for. Money is for payments. And we can talk about the modular structure of money, right? Everyone's familiar with the three functions of money. The unit of account is for denominating debt. The medium of exchange is for discharging debt here and now. And the store of value is for discharging debt elsewhere or later. It's a very clear formulation. It'd be great if we had such a clear statement of the modular functions of blockchains. What I like to point out is that, I wish I had to, what I like to point out is that between these different modular functions are tensions, right? And when we're building modular systems and modular designs, part of what they do is they allow us to focus in on the tensions between the different functions. So it's not enough to just say, okay, these pieces are modular, and so we've got this modular thing over here and that over there. There's real tensions between the functions that we need to tune to. And so I call the tension between the unit of account and the medium of exchange liquidity, which is much of what we're going to talk about today. And the other, I'm writing a blog series about all this, so you can check it out, but I won't go into it because I'm probably going to be running out of time. At some point, I'm going to need my slides to work, otherwise I'm just going to start rapping. All right, I believe the next slide says something like, okay, armed with a unit of account, we can denominate unlimited structures of liability, right? I can say you owe me, you owe whoever, right? We can denominate all this debt. But then the problem is, how do we ensure that we can actually discharge it all, right? You create all this debt structure, and then how are you going to discharge it all? This is the fundamental problem of the banking system, of money, of payments, of finance, that all this stuff is sort of built on top of, right? And next slide. It's a good thing I actually practice. So we call this problem liquidity, right? The ability to ensure that you can actually discharge your debts. That's what liquidity means. Liquidity is not how much slippage you're going to have when you trade one shitcoin for another, right? It's not, how many assets are available on some AMM. We call that liquidity because the purpose of trading is to acquire an asset so that you can discharge a debt, right? If all you're doing is trading just, to trade monkey pictures or to see the value of your assets go up, well, you're not doing anything real in the real world. The whole point of exchange and everything we're building ultimately needs to be in service of discharging debt, because that's where we ground ourselves in the real world and real trust relationships and so on, right? So we need to keep that in mind. Now, next slide. The way we solve or address the liquidity problem. Hey! Woo-hoo! Aw, look, they're so pretty, right? Here we go. So we did this slide. Just dwell on that. Meditate on this for a while, okay? This is pretty fundamental stuff, yeah? We did this slide. We are here. Okay. So what's a payment system? We define a payment system as a set of obligations, right? These are the debts, plus a liquidity source we can use to discharge those obligations, right? Now, if you think about that definition for a minute, you might be like, well, wait a minute. All these things I call payment systems, fintech, banking, blockchains, all of them are just about the liquidity source. They're just about moving assets around. None of them actually do anything to represent the obligations, right? So none of them are actually satisfying this definition of a payment system, which is a problem, because if we're going to build the next generation of payment systems, we need to address this. Okay, so let me briefly give you a critique of existing payment system. Now, we're working on a white paper for this Ko-Fi stuff. Is really what I'm presenting here. That'll be coming out in the next, 2 weeks, TM. But, so first of all, we'll cover this very, very quickly. None of these payment systems are designed from first principles. They're all just like cobbled together over the years, responding to, various problems. It's all just about asset transfer and exchange, but there's so much more to the core problem of payment and finance and what we're doing than asset transfer and exchange. We have to actually look at the underlying obligations. When we're talking about exchange, so much of exchange today, both in the banking system and in the real world, and in the banking system and in the blockchain world, it's all about market making and dealers. That's what everyone's trying to do, bring dealers on board, AMMs, liquidity, all this stuff. That is a new model that developed after the collapse of the banking system in the 16th century. Now, I promised Thibaut I wouldn't talk about the 16th century today, so I'm not going to. If you think that's great, like, oh great, he's not going to talk about history, you're part of the problem, because we all need to learn a little bit more history. And fundamentally, if we're responding to this issue of central banks, we all think, oh, we're going after central banks. Central banks emerged in response to the collapse of a prior international banking system that ran in the 16th century that cleared all the trade credit in Europe without almost any money at all. We need to understand that. We need to understand what happened, why it failed, and how central banks emerged out of that chaos to lead us from a world of clearing to a world of liquidity providing, right? Basically, since then, society has been structurally short volatility. All these dealers, all these market makers, they're short volatility. That is not a way to set yourself up for sustainability. It's a way to compound moral hazard at the heart of the system, yeah? So obviously they constantly fail because nature is not short volatility, right? And so at some point you blow up, and what happens? Central bank shows up, prints a bunch of money, bails you out, right? So that leads us to the fourth problem, which is, or the fourth element of the critique, which is the problem of issuance. Any payment system needs to grapple with the problem of issuance, whether you're a blockchain, issuing to miners, whether you're, a new currency like Osmosis, issuing to liquidity providers. providers, or whether you're a central bank in a banking system doing issuance when you make loans or when you bail out the whole system. And so what we want to do is try to understand issuance in terms of the underlying obligations, right? One way to think about it is that, hey, when a Bitcoin miner does some proof of work, right, they have shipped a service to the blockchain, and now the blockchain owes them. The blockchain has a debt to that miner, which it then discharges by issuing new Bitcoin, right? And so by thinking that way, it kind of opens up new possibilities for thinking about the problem of issuance. We think that's important because fundamentally we're going after two questions here, right? One is, how do we design a payment system to optimally discharge debt? And two is, who should have the right to issue and according to what principles, right? Now, a lot of people in the blockchain space are focused on problem two, and there's a lot of concern around tokenomics and issuance and how we do all this stuff, but there's almost no concern at all with option one. No one's talking about how we discharge debt, right? Hopefully we can start to change that. Hopefully you don't walk out of here being like, oh, he's crazy, none of that matters. And you're like, I need to focus on this debt discharging problem and issuance in that context. Because right now, who controls the issuance in the world? It's the banks when they make loans, they issue new money. And it's the central banks when they bail out the banks, they issue the base money. What we want to do is restore the capacity to issuance to individual communities, right? And we need, in order to do that and do that responsibly and sustainably, we need to ground it in the actual network structure of debts. Okay, this leads us to ultimately to what we're building, which we call collaborative finance. And collaborative finance we think of as a sort of semi-permeable membrane between the real economy and the financial economy. It's that layer in the middle, the yellow. MTCS is our core algorithm, multilateral trade credit set-off. Of course, that's a well-designed marketing term that users are going to love. But the whole idea is that we can protect people in the real economy in the bottom layer by focusing on the structure of credit and obligations, but we can still connect into the larger capitalist system, so we don't have to overthrow everything at once. We can sort of, do this iteratively. We can build a platform that allows lenders and capital providers, liquidity providers, lending protocols, et cetera, to plug in, but still do it in a way that's responsible and takes care of the real economy, right? And that's really what Ko-Fi is all about and what we're building. Okay, so let's actually talk about the design of the system. This is the background, even though I didn't talk too much about history. I'm gonna briefly just talk about the missing primitive, right? The main missing primitive is the obligation, right? The debt, okay? And we're gonna use balance sheets here. The world would be a better place if everyone spent a little bit more time learning accounting and thinking about balance sheets. So we're gonna do some very basic accounting here on stage. So on the left, we have Alice and Bob. We have their balance sheets, assets and liabilities, right? Not very complicated. This is a simple asset transfer, right? Alice has $20 in assets. She transfers it to Bob. Now Bob has the assets. There's no liabilities involved. There's nothing happening. This is what you do every time you send a payment to someone else, right? On the right, we have what an obligation looks like, right? So now there's a liability involved. Alice is declaring that she owes Bob, right? So she has a $20 liability to Bob, and that corresponds on Bob's balance sheet to an asset, right? We might call this, if you manage books at a company, accounts payable, accounts receivable, very simple stuff, right? The reason I'm pointing this out is because we're gonna build much more complicated structures that are networking these different obligations together. But there's two things I wanna highlight here. One is, when you do an asset transfer between two parties, right, from Alice to Bob, in general, we can say that is in service of discharging a pre-existing debt, right? You're not, okay, it might be a gift, but almost every time, Alice already owes Bob money, and that's the reason she's gonna send him the $20, right? Now, we're not representing that liability here. We don't represent it on our blockchains, but that's exactly what we're missing, right? And that's the whole point of what we're trying to do, to bring those obligations on chain so that we can do something more constructive with them. The other thing I wanna point out is that declaring an obligation, what we're doing on the right in part B, is really a permissionless action. It's very much like sending money. I can send Gary Gensler some shitcoins, and there's nothing he can do about it if I have his address. I can also declare that I owe him money, and there's nothing he can do about it. If I say I owe Gary money, then who's he to stop me, right? So it's a sort of permissionless declaration. It is an intent, if you will, to pay. Okay, so now we have these obligations. We put them together into a larger network, and you get complicated structures. You got single obligations, chains, cycles. If you've seen anything about Ko-Fi, if you're thinking about this to yourself, you're like, hey, wait a minute. If I can see the obligations, and there's obligations in a cycle, then we can clear any obligations that are in a cycle, right? And you can do that without any money at all. I owe Gary, and Gary owes, I don't know, Janet Yellen, and Janet Yellen owes me, and we can just get together and say, hey, we all owe each other. Let's just do set off, right? We don't need any money. We can just do set off, and that's what's possible when you start to open up the structure of the obligation network, and you look at the obligations. You can actually save everyone cash flow, liquidity. You can clear more debt with less money. That's what this is all about. Yeah. Okay, so once you have all these obligations, how do you actually discharge them? And generally speaking, there are 4 ways to discharge or to settle obligations, right? almost all of modern finance is built on the fourth one. It's called novation. It's when you actually change the structure of the payments graph, right? You do securitization or factoring or clearinghouses, you introduce intermediaries, you sell your debt, you factor your debt, right? All of this, you know, the economists claim this is all in service of like reducing risk and making things more efficient. Obviously, all of that was bullshit, and we saw that very clearly in 2008 when this whole, you know, house of cards came tumbling down. What we want to do is, as much as possible as we can, using the existing structure of the payments graph before we even consider novation. And it turns out there's quite a bit you can do. You can do set off, which we just talked about. That's clearing, right? I owe you, you owe me. Let's just do set off. Or we can do it in cycles, arbitrary size. There's assignment, which is just normal transfer. We just, you know, we'll use a fancier word because that's what we like to do. You know, I transfer you money, that's assignment, it discharges a debt. But then there's a very interesting thing you can do, which we'll call overdraft, right? This is where you say draw on a credit line. Someone makes some credit line available to you, and you can draw on that credit line to pay someone. So one way you can think about this is assignment is what you can do if you have a positive balance, right? You have a positive balance of some asset, you can assign some of those assets to someone else and use that to discharge debt. Overdraft is what you can do if you have access to a negative balance, right? Someone says, okay, I will allow your balance to go negative, and so your balance can go into negative territory. You can draw on that to pay someone else. This is what happens when you take out a credit line from a bank. It's basically a negative balance. It's what happens when you have a mutual credit system. In both of those cases, you actually have money creation happening, right? When you have a credit line from a bank and you draw down on it, the bank is actually creating new money. It's expanding its balance sheet and allowing you to use that new money to make payments. And banks are allowed to do that because they have licenses from the government, but why should they get to have all the fun, right? We want to seize the means of production of money back from the banks for communities and figure out a way to do that responsibly. And that's really what this is all about. But we can also do overdraft without money creation, right? A pool of investors could come together and say, okay, we're going to pool our Bitcoin and our Osmo and our Atoms into some pool here. You know, we'll do it over IBC. We'll put it in this little Ko-Fi chain. And, you know, we will make it available to people to draw on to pay their bills, right? And we can do it because we're going to have access to this network structure of obligations. We can do it in a much more intelligent and optimized and risk-reduced way. So it's important to keep these different things in mind. The last thing would be novation. We're not going to focus on novation because we want to avoid it. We want to do as much as possible of set-off, assignment, and overdraft before we hit novation. Okay, the last thing we need to put it all together is, as promised, the system of intents. Okay, so we already touched on obligations. We sort of beat them to death. Obligations are an intent to pay. That's kind of obvious, yeah? So then to really round this out, we need tenders and acceptances. So a tender is an intent to use some liquidity to discharge your obligation. So I have access to some dollars or some Bitcoin or some atoms. I think I upset Sunny here. I didn't pump Osmo enough. So I have access to some Osmo, maybe he'll stay, and I say, you know, I'm willing to use my Osmo to discharge my debts. Wouldn't that be great, Sunny, if people could use Osmo to pay their bills? And then an acceptance is the flip side of that. It's saying, I'm willing to accept some Osmo, or I'm willing to accept some Atom, or TIA, you know, if you will, right? Right, Nick? Yeah. I'm willing to accept some TIA to discharge debts owed to me, right? That'd be great. I like TIA, I like Nick, I like what they're doing at the Modular Summit, and so I'm willing to accept some TIA. And so you can start to collect all these different intents, all the obligations, the network structure, the different tenders people are making, which means the different kinds of liquidity they're willing to use to pay their bills, all the acceptances, the different kinds of liquidity people are willing to accept in payment of their bills, and we can put it all together into a graph structure, and then we can run a solver over the whole graph. Right? And we can run solvers that draw on decades of you know, advanced theory and algorithms in graph theory, essentially, to find optimal results. So we can actually optimize to discharge the most amount of debt with the least amount of money while respecting everyone's preferences, right? Solving over a system of intents. Y'all love it. All right, so this is what it ultimately looks like, right? So we have our graph here, we have a bunch of obligations. We have at the bottom this VB, this is our liquidity source, right? You can imagine it's Osmo, it's TIA, Atom, whatever you like. And we have the A on the left, that's the assignment source, and the O, that's the overdraft source, right? So those are positive and negative balances that people are able to draw on. And then on the right, we have repayment and deposit, right? That's where the money goes back to after it's sort of used. It either needs to be repaid or redeposited. And basically, we can use the same algorithm we use to find cycles. We can use the same algorithm with liquidity to find even more cycles, right? So the addition of liquidity into the network, even a little bit of liquidity, a small amount of tenders or a small amount of acceptances, allows us to essentially close more loops, right? So more people can benefit from their debt being discharged, okay? There's a lot to digest in this slide. You'll have to read the white paper. We'll go into a little more detail here. Here we have two different liquidity sources. We're going to put overdraft aside. We'll just focus on assignment here, right? So we have A owes B owes E. We have D owes B owes C, right? So an obligation chain. Now, we have access to fiat. We have access to crypto. And we have B. B doesn't want to use dirty fiat. He doesn't want to use shit coins. He's only willing to settle in gold bars. But he's happy to do set off, right? If you owe him and he owes you, he'll do set off with you, but he doesn't want your dirty fiat, he doesn't want your shitty crypto, he only wants gold. Now, what's gonna happen? A has a tender that says, well, I'm willing to use fiat to pay my debts, and C has an acceptance saying, I'm willing to use fiat to discharge my debts. D is willing to use crypto, and so is E, to accept crypto. And what ends up happening is B benefits from both of these things. So B is benefiting from A and C using fiat, and from D and E using crypto, without even knowing about it. D doesn't want anything to do with them. He doesn't have to touch either of them. All he's going to handle is a set-off notice that says his debts are reduced, right? And his debts are being reduced because other people are using fiat and other people are using crypto, right? This opens very profound new ways to bring crypto into the real economy, where so long as there's a small number of people willing to tender crypto and accept crypto, others can benefit from that without having to touch it at all. So long as they're willing to touch a set-off notice, which is just an accounting entry, okay? So this offers, really, really new ways for crypto to impact the real-world economy, to be used in real-world payments, and to benefit real people without them even having to touch it, which is, I think, a nut that we haven't been able to crack really until now. This is another example. This one's a little bit more complicated, but also quite profound, where we were not able to close the loop within fiat or within crypto. We have to combine. See, on the previous slide, we didn't need both liquidity sources, right? If we just had fiat, we'd close the loop ABC. If we just had crypto, we'd close the loop DBE, right? In this slide, we're not able to close either of those loops. We need to use both crypto and fiat together. And in this system, because the difference here is basically, in the previous one, D owed B, you can see there's sort of there's not the same overlap, right? So here you actually need both sources of liquidity to be able to discharge everyone in the path. And so you're able to complete a new cycle over both sources. And so the more liquidity sources you bring in, even with a small amount of tenders and acceptances, assuming you have a large obligation graph, you're able to discharge way more debt, which is very, very, very powerful. So ultimately, you put this all together, you get something like this, right? So here's based on real data simulated with 3 different liquidity sources. We could say one of these is fiat, one of these is crypto, one of these is mutual credit. That's the holy grail. Mutual credit is communities being able to issue their own debt, their own currency to discharge their debt, right? And you get this stunning visualization of how everything flows in the network so that all the debt, as much debt as possible, can be cleared with the least amount of money while optimizing over and respecting everyone's preferences for which currencies they actually want to use. With that, I'm perfectly on time, which is kind of amazing. Thank you so much. I'm Buckminster. You can learn more, kofi.informal.systems, and check out the white paper when it's out.
Thank you, Ethan. All right, up next we have Ismail, co-founder of Celestia. You should all have heard of it. And he's going to be talking about the past, present, and future of the Celestia architecture.
Hello, everyone. I'm Ismail Kofi, co-founder and CTO of Celestia. I'm going to talk a little bit about the architecture of Celestia, how it currently is, and give like a glimpse into the future. Whoop. They're not mine, yo. How do I fix this? Oh, okay. First, so on the agenda, I wanted to talk like 2 parts. Like the first part is I'm gonna recap the Celestia architecture, and in the second part, as I said, I'm gonna talk a little bit about like future directions. So it's not like a full-fledged roadmap, but what could be on the roadmap next year or so. Okay, so first of all, what is Celestia? I think most of you know, but for those who don't know, I'm gonna explain it from a high level, but also how it's implemented roughly. So Celestia is like the first modular blockchain network, and what it does is it decouples consensus from execution. So what does this mean? So in classical monolithic blockchains, usually how every chain works is a client verifies 2 things, right? It verifies that the header has consensus, and it also verifies that all the transactions are valid, right? Like it executes the transactions, makes sure the state transitions are valid. And then in Celestia, though, it only verifies if the transactions are available. It still validates that like the header has consensus, right? But it doesn't execute the transactions. It doesn't validate that what is posted on chain is actually valid. It just it just ensures that these messages that have been posted on chain are available, right? They are opaque blobs to Celestia. Like every application can post their blob onto Celestia, their message, and it's just ensured that these are ordered. There's consensus on the order, and then everyone can verify themselves that these transactions are available. So that's the main differentiator, and I'm gonna explain a little bit on how this works as well. You might ask, like, where does the execution happen? And the execution in Celestia happens in so-called rollups, right? Instead of this world computer model where like all the transactions are validated on like one chain, the state transitions are validated on a rollup. And you might ask, like, how does that work in practice? The light clients, for instance, they to validate that like a header is contains only valid state transitions. There's two approaches to this, which is like via fraud or validity proofs, right? Like in the Ethereum world, these fraud or validity proofs are posted on Ethereum, or they're settled on Ethereum. But like in Celestia, as there is no execution layer whatsoever on the main layer, these can be on like a different layer, like on a settlement layer, or they could be on the peer-to-peer layer. I just wanted to stretch this, as many people still perceive rollups as like enshrined with like with an enshrined settlement layer like on Ethereum. So now that we covered like how execution works, how the main chain works, I wanted to like mention the 4 guiding principles with which we designed Celestia, or like goals that we wanted to achieve. So it should be possible that a block is deemed valid only by checking block availability, right? Which means you can like verify a header as a light node without having to download the transactions, just by verifying the availability. The second principle is application message partitioning, which means every application only has to download their data, right? Like they don't have to download all the transaction data of all applications, only the transactions that are like necessary for their application. And then there's application message retrieval completeness, which is the same thing, but which means that they can verify that all the like application messages, they downloaded all of them and nothing is missing. And there's also application state sovereignty, which means that all they need to care about is their state transitions and their, basically their state portion, and they don't have to execute other transactions of other applications unless there's a direct dependency. So next I want to talk about like how is this achieved roughly. I don't want to go too much into detail, but like there's mainly three key ingredients here in play. One is erasure coding of block data. Another one is a namespace Merkle tree and data availability sampling. So let's dive a little bit in. Erasure coding is a technique that is very well known, which is basically used like in CDs, where you can like recover data. So you add parity data and you can recover data even if parts of the data are missing, right? So how this works in Celestia is the data is encoded in a certain way, arranged in a certain way. The original block data is split into equally sized chunks, and then you add this erasure coding in this square construction that is depicted here. The details do not matter. What matters is that you, this enables basically that you can with like a portion of the data can always recover the whole data. So here we also commit, when like validators create a block, they also commit to the erasure coded block and not to like the original data only, as it is with like other chains. And so every like row or column here basically forms a Merkle tree, and these Merkle trees get committed to in a bigger overarching Merkle tree. And that Merkle tree is not like a simple, like traditional Merkle tree. It is very similar though. The main difference is that a namespaced Merkle tree is used, which sorts the data according to their namespace. Like each application can have their own namespace, and the data gets posted on Celestia, gets prefixed with a namespace, right? Like it gets sorted, and this is the data structure that ensures the property that I mentioned earlier. You can like only download your portion of the data, your namespace, and you get like a completeness guarantee of that as well. The third and most important ingredient that makes it possible for Celestia to ensure availability is data availability sampling, right? So as I mentioned before, the block is erasure coded, here depicted slightly differently, and then light nodes or nodes or clients can download only a small portion, like 1% of the data, due to that erasure coding to guarantee like almost 100% certainty that the data is available. Yeah, and so from a very high level perspective, this is how we built the system. We took Tendermint, right, and we modified, Comet BFT called today. So Comet BFT, previously Tendermint, we took that, modified it, and we added basically the data commitment that I mentioned earlier. We also used the namespace Merkle tree for that data. And the third component that I mentioned, the data availability sampling, is done in a different layer, in a different peer-to-peer network. We call the DA networks heavily reliant on Bitswap and libp2p. Huge shout out to the Node team that built this. No one has built this before. It's a huge effort. And yeah, that's a high level architecture overview. So, so let's go to the more interesting part, which is like, what are future directions for Celestia? How could like a future roadmap look like? Or at least what could be some highlights here? So I mentioned this erasure coding, right? This is required for rollups to ensure safety, right? Like in the sense that you have to be sure that the data that has published has not been tampered with, like there's no validator that is like committing to garbage essentially, or something else, or some invalid data. So how do we ensure this currently? Currently, we have a fraud-proof type that is called bad encoding fraud-proof that every node can generate that like downloads either the whole block or even a row or like several rows are sufficient. They can like verify that the data matches the data root and can generate a fraud-proof if that's not the case. That has the downside that theoretically light nodes need to have to wait for such bad encoding fraud proofs to not happen to ensure like full finality of the block, right? An alternative approach is to use KZG commitments. I think if you saw Avail's talk yesterday, that's a technique they employ, which gets rid of the bad encoding fraud proofs. The question is, can we do better than this? I think we can. So with an alternative approach here is to use a ZK proof of the erasure, like to use a ZK proof that proves to you that the erasure coding and the construction of the data root was done correctly. So you can still compute quickly like the data root as before and send around the proof if necessary, if like you require finality, right? So that's a research direction if anyone is into like ZK proofs, this is something you could look at. And I will later share a research forum link and the GitHub link. Another direction or another topic that we certainly will look at after launch is a trust minimized bridge, or like a two-way bridge from and to Celestia. So currently, if you wanted to use the base layer Celestia token on your rollup as a gas token, you have to use like other bridges and to use like other chains or third parties to get the token out and in to your rollup and back, right? Ideally, you would like the UX of this would be more seamlessly, such that developers can use the TIA token directly. So one naive way to do this, one way to achieve this, is you could enshrine like a general purpose execution environment onto Celestia that that acts as a bridge, right? That has the problem that it wouldn't be really neutral in the sense that you'd have to choose an execution environment, and also you'd basically reintroduce, like you would tamper with the original vision, which is like having only data availability and consensus. It turns out that you can do this without enshrining an execution environment. Mustafa came up with this idea where you basically leverage that ZK snark verification is more or less like looks very similar to cryptographic signature verification, right? You also have like a public key, and from that, like if you look at how ZK snarks work, it's like from the public key, it basically looks the same. So the user flow for how this would look like roughly from a high level is that a user would send a deposit of TIA to a verification key address. That's like a key address, like a public key on address owned by like a ZK program. So you deposit TIA to there, it gets like escrowed or burned, the transaction gets confirmed, and then the TIA would get credited on the rollup. And so you moved out you moved TIA into your rollup seamlessly. So this rollup will need to track the state of that verification key address. And so the more interesting part is like, how do you bridge back? You would send TIA, a withdrawal transaction of your TIA in the rollup, right? If the transaction gets confirmed by the state machine on the rollup, you generate a ZK proof. And that ZK proof like kind of simulates or acts like a signature on the verification key address on Celestia. So that would trigger the withdrawal of TIA. That's very high level. The devil is in the detail. There's a lot of like choices to make here. John would say a lot of implementation details. And indeed. Another hot topic is how to fix MEV, or rather how to apply current state-of-the-art MEV research and techniques to like the modular stack, right? There are several teams working on this. I think Skip and Flashbots are the most noteworthy here. The speciality or like the difference here is that MEV can trickle from the rollup into the base layer. Like the base layer validators could delay or like even censor batches from the rollups, right? So the question really is like, how do we apply solutions to MEV to this like more modular stack, especially given that there's like a very heterogeneous application layer? I think Evan's talk will cover this in greater detail. Don't miss it. It's like this afternoon. He will speak about how to break the proposal monopoly. Don't miss that talk. So this is like the long-term goal here that we want to achieve is 1 gigabyte blocks, 1 million rollups, and 1 billion light nodes. So often when we mention this to people, it's like 1 gigabyte blocks, that sounds insane, right? And it kind of does, but we won't achieve this immediately anyways. It will be on demand. But we do believe that this is, like, as it becomes necessary, we will tackle this. And the question really is, like, how? I think we're very confident that we can go to, like, 100 or something very, very quickly. But to actually get, like, closer to that 1 gigabyte blocks goal, we will have to optimize Comet BFT's peer-to-peer layer, right? Like, the mempool is not made for super large blobs, and the consensus reactor, like the gossiping mechanism, is also not made for that. There's a lot of, like, low-hanging fruits and optimizations that we will do. One of them is already started, which is like the content addressable pool, cat pool. Callum implemented this already. Similar to the peer-to-peer, like the node peer-to-peer layer needs a lot of improvement to achieve this. Mainly block sync and DASing. Like, there's a lot of optimizations to be done, mostly very implementation specific. It might turn out that, like, in the future, in like several years, we have to merge the DA layer and the consensus layer again, like architecturally from a software perspective. And we might have to employ a technique called internal node sharding to achieve like the throughput on the consensus layer. Another topic that I want to stretch is we want like 1 billion light nodes. How do you achieve this, right? So we want all light nodes to run on all devices, like on all kind of devices. But I think the device we should target the next is the browser, because this is what, like, people are used to interact with in their wallets, and like they send transactions through like MetaMask and everything. What we want to achieve is running Celestia nodes, DASing light clients in the browser. So there's two approaches to this. One is having a different compile target for Celestia node Go implementation. Another one is having a Rust implementation. For the sake of time, I'm not going into detail, but if you want to hack on this, please talk to me. Yeah, there's plenty of other open problems and research directions. A few were already mentioned, for instance, by Yuma yesterday, the ZK quantum gravity bridge. Yeah, and I think one thing that last word that I want to mention is that we need to focus on developer usability, and if you want to do usability research for developers in the modular stack, please also reach out to me. Yeah, you can engage here with in our research forum and on GitHub. These are the main things. Thank you very much.
Thank you very much, Ismail. Yes, gigabyte blocks. I want a gigabyte block. I don't know what I'll put in it, but seems fine. Next up, Sunny is going to be talking about mesh security.
Hello. I, in fact, will not be talking about mesh security. I'll be talking about some other stuff, but it'll show up a little bit at the end. I think I've just been sending mesh security as the title for all the talks that I haven't come up with a talk for yet, and you know, they're like, oh yeah, that sounds good. No, but I'm going to be today. Thank you guys for coming. My name is Sunny. I'm one of the co-founders of a project called Osmosis, and we're going to be talking a little bit about how Osmosis will be interacting with the modular ecosystem. So a little bit of background for anyone who's not familiar with what Osmosis is. Oh, yeah, that's better. Anyone who's not familiar with what Osmosis is, we are a DEX built on the Cosmos SDK. We have all sorts of, you know, we just launched, we have liquidity, swapping ability. We launched the contrary liquidity very recently. You can do all sorts of, have assets from over 50 different blockchains on the Osmosis blockchain. We have over $100 million in liquidity. We have all sorts of like pro trading tools, like basically the most advanced developed DEX in the Cosmos ecosystem. And yeah, liquidity from all different places, both from within Cosmos and outside of Cosmos. Out of all of the assets, like 4 out of 5 biggest pools are from non-Cosmos native chains, right? And along with just the DEX itself, we have this ecosystem of applications really meant to build this full unified DeFi experience on top. So, beyond just your basic spot trading, you have your margin trading, you have your perps, you have your launch pads, you have your fiat on-ramps, you have lending protocols. So basically a full integrated DeFi experience. Everything, the goal here is you go to Binance.com, you have all these trading tools, you have all this things in one unified experience. Osmosis is going to provide that in a decentralized way. So, and as by being this liquidity center for the Cosmos ecosystem, we are sort of the center of IBC traffic today. So if you look at on any metric by users or by IBC traffic by volume, Osmosis is sort of the center of that and has found itself as this IBC hub and liquidity hub of the Cosmos ecosystem. And so now, very soon, hopefully, we will have a new entrant to the Cosmos ecosystem, right? The Celestia blockchain will be launching. And as part of the Celestia blockchain launch, the goal of the Celestia blockchain node implementation is to be as simple as possible, right? Obviously we need this thing to, with Celestia, we're gonna have this beginning of all sorts of new modular chains and rollups building on top of the Cosmos ecosystem. And there seems to be this thing about oh, app chains versus modular, and I think this is some weird dichotomy, because really the whole point of app chains is this idea of modularity, right? It's saying hey, we don't need to put everything into one blockchain. We can, break out what you need. Osmosis, we're trying to be a DEX. We can say hey, we don't want to deal with bridging. We are going to completely outsource that. That's not our problem. We're going to go find someone else to work with. We're going to go work with the Axelar team or the Wormhole team, right? We're going to go outsource bridging completely. This is part of the modular idea, right? Or if it comes to things like data availability, or if we need to base money, it's okay, we're not building that. We're going to outsource this. This is all it's all modular. So. So what I was saying was, yeah, so the goal of the Celestia blockchain is to act as this app chain and to be as simple as possible, because obviously, we got to run it on our Kindles and we got to keep the nodes as light as possible. And because of that, the Celestia code base is actually very, very minimalistic. You'll see that it actually imports very few modules. Ishmael just talked about how how can we avoid adding a general purpose VM or anything to this chain. So the one module that it does have, though, one of the few modules that it does have, obviously, is the IBC module, which is great, right? And so this is this decentralized, this permissionless bridging protocol that allows you to send tokens, data, assets, anything between any IBC-enabled blockchain. And so IBC is growing. It is, built on the Cosmos SDK. There's other chains as well now. Now we finally have it on Polkadot. We have it on the Penumbra and Anoma stack. So, IBC is slowly growing. But with Celestia now and this ecosystem, the modular ecosystem that's being built on top, we have a whole bunch of new frameworks being built, right? You have the OP stack now, right? You have Rollkit, you have the Sovereign SDK, you have Eclipse, and it's it is going to take us time to go and build out IBC for every single one of these, because the goal of IBC is to really build in your bridging protocol at the same security level as your consensus system. It uses light client proofs, and it will take time for us to get there. Obviously, the goal is we want IBC everywhere, but and there are people working on this, right? Polymer is working on adding IBC, ZK IBC to all of these sort of different stacks. But it'll take us some time to get there. And so right now, how do we do this? We're going to have to rely on other bridges, right? And so this is kind of where. So the question is, how will all these rollups and chains and sovereign rollups and everything on all these different stacks access liquidity, especially TIA liquidity, right? Because they need that TIA to pay for their data availability. How are they going to get that TIA to there? Well, this is where Osmosis comes in. So Osmosis is, really expanding on its bridging support. So obviously we support IBC today. We work very closely with the Axelar team. Wormhole just announced yesterday at OsmoCon that they're launching Worm Chain, which is going to be a Cosmos SDK-based chain. And then the important one here is Hyperlane, right? So Hyperlane seems poised to be the the first bridge that's available to a lot of these different stacks because of the way that it's been designed as this, very modular bridging system where you can choose what kind of security system you want. And so we are working on adding Hyperlane to the Osmosis chain, because of its app-defined security model, we can write it as a COSM-WASM contract, and with this, we're going to be able to use Osmosis as the connector between Hyperlane and IBC. So now you have this flow where finally you can say, hey, how do you get TIA from Celestia onto something like Eclipse or onto an Eclipse-based rollup? Well, you can IBC from Celestia to Osmosis and then Hyperlane from Osmosis to Eclipse. And this will be, and the idea here is that we're going to use Hyperlane to connect to all of these sort of different rollups and get TIA onto them. Now, well, what do you do when you're at the center point of transportation routes, right? Well, you build a trading center, right? You build Constantinople, right? You're at the crossroads. You build a trading center there. That's what we're building with Osmosis. So we want to be the place where we build up as much TIA liquidity and liquidity for the entire modular ecosystem and provide these services and product that we've been building for the Cosmos ecosystem, but expand just beyond that. And so one of the things that I'm really interested in is protocol-owned TIA, because if anyone remembers a couple of months ago, the Arbitrum chain basically came to a halt because some dev account didn't have enough ETH in it to pay its data availability and stuff, right? So we should be moving to a world where, no, you shouldn't be relying on some foundation or some dev team to be paying for your submission proofs to your DA to Celestia, right? You should be actually moving towards a system of protocol-owned TIA. And so, there's a bunch of different ways that we can do this. So one, we have this protocol called StreamSwap, which is basically a auction system built on top of the Osmosis chain. And I think a lot of the new projects that are launching can do these stream swaps. It gives you this initial distribution, but you can do it for TIA. So that way you have this initial distribution of your token, but now your protocol owns TIA in its community pool or treasury, and it can pay for its own DA without directly from itself. We also have built this thing for the Cosmos ecosystem called fee abstraction. And what fee abstraction is it's meant for transaction fees. So what you can do is you can take a chain like Stargaze, right? Stargaze is an NFT platform built on Cosmos. People can start paying their transaction fees in stars, but they can also pay their transaction fees in any token. They can pay in USDC, they can pay in Osmo, they can pay in Bitcoin. And what we've done with this fee abstraction module is Stargaze can accept these fees in all these different tokens, but what the chain will do by itself is it will send all the tokens to Osmosis, swap them to its own native token, and then send them back to the Stargaze chain so that way they can be distributed as fees or burnt or whatever they want to do. So this module is available. It's available on our GitHub. You can go to github.com/osmosislabs/fee abstraction. You can import it into your Cosmos chain today, and any Cosmos chain can start accepting fees in any token. Okay, what's the next step? The next thing that we're going to build with this is DA fee abstraction. How do you let all of these rollups pay, let's say they don't want their own protocol-owned TIA in their treasury, but what you can instead do is say, hey, a chain like Manta can say, oh, we are going to hold our own native token, Manta, but we need to pay our DA. They can send it to Hyperlane to Osmosis. It will automatically swap it to TIA and send it to the Celestia chain in order to pay for the DA. And so we are working with some teams to actually build this out in production now. Another way that beyond just for fee abstraction, with this whole modular idea, a lot of these chains, we work very closely with the Argus team. We can build this idea of outposts where they don't have to build their own DEX infrastructure for their own chain. They can actually provide things like swaps and everything over IBC. So let's see if this works. This is a demo that we built of the Cosmos swap, which is basically, this is a swap on the Juno chain. You're swapping Juno for Osmo. You make a single transaction on the Juno chain, but what it's doing is it's actually sending the tokens to Osmosis, swapping them to to Osmo, and then sending them back to the Juno chain. So basically, Juno doesn't need its own native DEX. Let's say you have a DAO on Juno or whatever you're trying to do, you can tap into Osmosis's far deeper liquidity. And so the Evmos team has also built a similar version, similar concept for the EVM. The Skip team has, you saw them present an hour ago about IBC.fund. You can basically swap from any chain to any chain on any token on any chain to any token on any other chain over IBC, and we'll be working on integrating Hyperlane into the system as well. Yeah, all through Osmosis. Anyways, so these are some of the ways that Osmosis is planning on integrating more deeply into the whole modular ecosystem. One of the other things I'm actually really interested in is, obviously I do have to talk about mesh security and how we want to incorporate data availability into mesh security. So, the premise of Cosmos, and I think a lot of the thesis in a lot of the modular ecosystem is this idea that every chain is the L1 for its own internal state and an L2 for its foreign state, right? This is sort of the whole idea behind these sovereign rollups. And so, Osmosis is the settlement for the Osmo token, but it acts like an execution environment for any Axel that is bridged IBC to Osmosis. And so as part of IBC today, we do these sort of light client proofs where two chains are going along, you send an IBC packet that includes some sort of light client proof. But what we want to do is eventually make IBC or, the security model between these chains better than just light client proofs. We want to start to incorporate things like fraud proofs. And finally, now, thanks to things like Rollkit, we actually have fraud proofs for the Cosmos SDK. Now, the thing is, fraud proofs have this huge time delay to them, right? You have to wait the entire challenge period, and the UX that people have come to expect in Cosmos is very fast bridging, right? You can IBC between two chains in a matter of seconds, and that's sort of one of the things that people really love about it. And so we don't want to build in this, fraud-proof window into the IBC bridging protocol because it'll just massively deteriorate the UX. But how we can use fraud proofs is in mesh security. So mesh security is this idea of restaking where you can say hey, validators are going to give certain guarantees about they're going to be restaking their Osmo to. Yeah, okay, so, and as part of this, what we've done is, the initial version of mesh security is mostly about Tendermint fraud proofs, so it'll be able to detect, hey, okay, this validator did something malicious in the consensus protocol, we're going to slash them. But the way mesh security is implemented is actually as it has this interface called a slasher contract, and you can write arbitrary slasher contracts, right? You can do it for things like, we're going to do mesh security restaking for an Oracle protocol, and if one validator's Oracle price is too far away from everyone else, that is a valid slashing condition. What we can also do is build Rollkit fraud proofs as a slashing condition, right? And so I think that eventually every Cosmos chain will start to use Rollkit style fraud proofs, right? And so that's great, but then how do you make sure that you have these fraud proofs? The idea is that okay, we're not going to block IBC bridging on it, but if a Byzantine state machine sends an invalid packet, in the future, they will be slashable for it. But to make them slashable for it, we need to make sure there's data availability. So this is what we can block for. We can at least block on data availability before accepting IBC packets. So let's say chain 1 or say chain 2 wants to send some assets to chain 1. What it can do is generate a transaction. It will post the data onto something like Celestia or any DA system, and the validators of chain 1 will be running a data availability sampling like clients of Celestia. So in the validator software, we should be having this DOS like client built into the software. And then what they will do is when IBC data is sent from chain 2 to chain 1, the validators will basically use a vote extension to approve whether or not that they actually got they'll validate that the data is available. So they're not going to actually validate the fraud proof itself. They're just going to validate the data is available so that someone in the future can submit a fraud proof to the mesh security slasher contract if needed. Anyway, so thank you guys so much for listening, and I hope you learned a little bit about Osmosis and mesh security and what we're building. Thank you.
Thank you very much. Continuing our sort of theme of Cosmos-themed panels, myself, David from Galileo, Ismail, and Jack are all going to talk about the Internet of Modular Blockchains. Oh, and Ethan.
Looks like, yeah, there is an order.
I'll take that. Give me that one.
Cool, awesome. Happy to be here with everyone and with a few Cosmos OGs. Today I kind of want to talk about the Internet of Modular Blockchains, setting the stage in the past and talking about a little bit of history of Cosmos, which I'm sure Ethan will be happy to do because he loves history.
Only from the 16th century.
That's right. So, fast forwarding from the 16th century a little bit, Cosmos came about somewhere in 2017 and set this vision for an internet of blockchains, a future that would encompass thousands, hundreds of thousands, millions of blockchains. And to accomplish that, they came up with the first modular framework for blockchains, which is a composable suite of software primitives in the Cosmos SDK, what's now Comet BFT and IBC, so that we can live in a world of millions of interoperable blockchains. So what I'd like to do today is talk about the future of those three different components and how different new primitives like data availability and what's going on at Celestia with separating consensus and execution fit into what was the original Cosmos vision of kind of a modular future. Maybe, Zaki, if you don't mind talking about, for a few moments, the state of Tendermint and where we see that fitting into this future.
Comet.
Comet.
Comet. Comet BFT.
Everyone.
Comet! Yeah!
Yeah, absolutely. So I guess all right, my main thought process is, so in a lot of ways, this whole software stack was like designed in an integrated way with interoperability as like the end goal. So we picked a consensus algorithm that had an efficient light client that didn't need new advanced cryptography techniques or new advanced like zero-knowledge proofs or new cryptographic primitives like BLS signatures, all of which were not very mature at the time, but would still give you high-performance light clients and bridges. But we're also starting to see sort of and so, we built the system. I think like I'm talking a little bit about lunch about how, we sort of, the system was built with Bitcoin as like its only real reference point. So like, how do you build a next generation system from Bitcoin? Now we've gone a lot with the Bitcoin was very much the inspiration. We are now sort of way past that. In so many ways, and really seeing the limitations of that system. It's been a big breakthrough getting ABCI++ out the door, which was the first big change to the consensus API, and is a system that like no one else is offering. So it is interesting that we still are able to like push the limits of the possible on top of this stack, but there's a lot of work to be done, and like. Where this stack, and what Ismail was talking about, right? The P2P layer was not expressive enough to build Celestia. So you had to build a Frankenstein of two P2P layers to build Celestia. And so as we kind of advance towards the future, I think we're all going to have to figure out sort of where this software goes from here and how it sort of more or natively encompasses these different use cases.
Thank you. So continuing to consider these pieces individually for the Cosmos SDK, do we need to consider alternative hosts for the SDK? And how do we 100x Cosmos with those primitives?
Yeah, want to call out Marco and his team, who are doing great work on helping to expand the Cosmos SDK to help support more underlying data availability and other consensus algorithms. That work's extremely important, and then on top of that, also more VMs. And when we talk about modular, this is what it means. You want to be able to pull the pieces out, plug new ones in, and easily swap out those components. And I think that the sort of innovation of Celestia was making consensus, breaking that down into different parts, and allowing those components to be swapped in and out. And that does require large changes to some of the software, because I think when you're building something, it's really easy to make assumptions and just bake things in, and it takes a little while to unwind that. But a lot of that work's been done by the SDK team right now.
I think it's going to be a really interesting question to see, if the most value, the most number of in the Cosmos SDK is coming from Comet BFT as a host or Rollkit as a host in a year, 5 years from now. It's going to be a big. I think that's those sort of one of the existential questions.
Yep. So going back to kind of base layer and security, Ethan, maybe you can touch on kind of the merits of mesh security with all Cosmos blockchains that are IBC connected versus kind of data availability and consensus with Celestia, and how those two interlink.
Sure. Yeah. I mean, I think what's happening here is, look, we had to first create the interchain, right? So we had to stand up a bunch of. I mean, once upon a time, the multi-chain was a sort of blasphemous idea. We had to convince people proof of stake was going to work. There could be many chains, that sovereignty mattered, and so on, and that what we needed to do was sort of go bottom up, build a general purpose interoperability protocol for these individual chains to start to connect to each other. And now that we sort of have that, we can start to explore the different ways to actually share security over that interchain that now exists. And so all of these sort of different solutions, using a common data availability layer, using things like mesh security or interchain security or so on, they're all sort of different ways to explore, different areas in the trade-off space for sharing security over the interchain, right? And I think the reality is we don't really know yet how it's all going to shape out. There's going to be some kind of complex arrangement of all of these different solutions, and ideally chains will be able to sort of choose for themselves which ones they want to experiment with, and if they're even able to experiment with multiple of them at the same time, right? So mesh security certainly holds forward a promise of allowing sort of tighter economic integration between different chains and allowing them to sort of strengthen each other's economic security by sharing stake. Data availability offers a sort of different way to to offload or outsource a certain element of security that's less about sort of sharing between many different chains and more like, okay, let's use the security of one big chain for a particular function, outsource to that, and then focus on on what we're doing. But I can even imagine that there might be some way that sovereign rollups or something using DA, Celestia as a DA layer, might still find ways to sort of anchor other definitions of security to each other and share. And I think frankly, I think we still have very poor definitions of security. We use that word as if we know what it means, but it means so many different things, and there's many different elements to it. And so I think a big part of what we need to do in this sort of new phase now that the interchain's here is to actually get clearer definitions of what we're talking about and the kinds of security, what that means, what kinds of guarantees are really being offered, and how people can actually reason about them.
Yep, thank you. Ishmael, I think your views would be really interesting here, given that you were one of the original Cosmos members, and now you're internally at Celestia, and how your views on the interchain vision have evolved being inside of Celestia now, and how you see that going forward.
So how I see it is that actually Celestia is the continuation of what we built before, right? The first component of the interchain was the Cosmos Hub, so to say. And basically what we're building is what the Cosmos Hub could have been, right? It's a version of the hub that has actually a purpose in the interchain, or in this vision of application specific chains. It actually serves a concrete purpose, which is offering, like the service offering of Celestia is essentially just ordering your transactions and data availability, right? So yeah, I think it's very very logical continuation essentially, and I think I agree with Bucky that there's like a lot of there will be a lot of like experimentation happening, right? And Celestia will be, I'm sure like Celestia will play a crucial role in there, and like it will enable a lot more experimentation, particularly because you offload the execution to these like applications or like the app layer. You enable much more like experimentation with like zero knowledge stuff and like different VMs essentially, which I think will be way easier if compared to having to stand up your own like Cosmos Zone essentially. Yeah, I think that's basically covers it.
Yeah, thank you. I think that the continuation of the experimentation is really something that I'd like to press harder on, which is more for developers' experiences to be able to customize as granularly as possible to build the best application experiences. And I think part of that is RollKit. I'm wondering if you could talk a little bit about RollKit, that coming out of Celestia, and what that means for kind of the internet of blockchains.
Sure. So RollKit is basically a drop-in replacement for Commit. So it's like it takes the same abstractions as Commit BFT or previously Tendermint, which is like the main abstraction here is ABCI, which is like application blockchain interface. It is an interface between the consensus layer and the application, right? So we took that abstraction such that Cosmos SDK developers can continue like using the Cosmos SDK as they're used to, and or like people who want to use ABCI and like build applications in other languages. Like there were teams building in Haskell, in Rust, and like other languages. Penumbra is building like in Rust, for instance, and Anoma. Like all these builders that are used and familiarize themselves already with the stack, with the Cosmos SDK, they can like continue doing that while are not being forced to spin up their own Cosmos Zone, right? Like they don't have to spin up like a proof of stake chain. They can use RollKit as like a sequencer software that posts data to Bitcoin, as we've seen before in the panel, or Celestia, or Polygon Whale, right? Like it's a general, like more general piece of infrastructure that we build such that the ecosystem can flourish and like experiment with different data availability layers.
Yeah, awesome. So 100xing Cosmos is something that I think we're all interested in doing. Part of doing that is connecting non-native IBC chains. Jack, maybe you can talk about some of the work that you and the Strangelove team are doing, extending IBC outside of Tendermint. And maybe we can take that a step further and talk about new clients for IBC and how we get to that future.
Yeah, sure. I think also like there is this strong place for Comet or other classically BFT consensuses within this world. We're starting to talk a lot more about shared sequencers and some of these other pieces. And I think one of the beauties of the way we've built this stack is these modular pieces, these primitives can be sort of like mixed and matched in all kinds of different ways. And the experimentation that's happening now is helping us optimize that developer experience, make it as easy as possible for developers to spin up their own systems and then go sell services into this interchain economy. You know, Celestia is kind of bringing new primitives to the table, but also a novel combination of existing primitives, and they're selling that as a service to chains over some of these basic interfaces. I've got some more talk this afternoon about modular IBC patterns, and I'm going to dig a lot deeper into some of these topics, but in IBC, there's this concept of a client, and the client does all the authentication. Hey, do I know which chain I'm talking to? Did users send these packets over on these other chains? And that abstraction is really general enough to put all kinds of cryptography in. And whatever the trust assumptions of your system are, you can encode them into that client. So with the roll-up world coming, there's all these new trust assumptions, there's all these new models for how to verify the state from these roll-ups, and the work that we need to do with IBC to ensure that this internet of blockchains continues to be connected is to build out all of these different trust assumptions into these clients so that it enables IBC everywhere. You know, I think that with optimistic roll-ups, we're likely to see a lot of the IBC traffic go through shared sequencers or other committee-based solutions. Compiling the fraud proofs and all of those things is a little bit too heavyweight right now computationally, because you need to run the full state machine over on your counterparty. And it's a lot easier to go through a Tendermint committee that's a shared sequencer. But once the ZK rollup technology matures a little bit more, I think we're going to see that become the dominant method in a lot of ways. And that model fits much more nicely in IBC, because all you got is this little ZK proof, you shove it into the client, and you're good to go. You couple that with the Celestia data availability sampling light client as well, and then you can fully prove the state of that chain. So, you know, bubbling it up a little bit, where we are right now is like all of these primitives work, they're just entering production, but I think, David, to your particular question about bringing that mass adoption that we really need to see and really enabling developers, the work over the next year is to sand the rough edges off of the developer experience and allow developers to launch one of these rollups in 5 minutes in any one of a number of languages. And, you know, all of the pieces that everyone on this panel here builds are a huge part of that system. And it's really cool to see it coming together.
Yeah, thank you. So right now we're at a point in crypto where there's a lot of infrastructure, a lot of new infrastructure being built, and all of this is in service of building killer apps. And whether that killer app is money, as Ethan suggests, or it's something more Web 2 oriented, social or not, we need maybe a little bit more infrastructure to make these experiences better. So maybe we can go down the line, and I'll ask you, what's missing?
I'm going to take a contrarian piece here and say, I think a lot of the infrastructure that we need is here today. And I think especially with breaking consensus into different pieces, a lot of people have talked about Celestia and data availability as the end game of blockchains. Like, I do truly believe that that is the case. So I think really what's missing is compelling developer experiences and ease of use for all of these products. Because at the end of the day, infrastructure is a product. And products need users, and if it's really hard to explain how all these things work, then we can't bring in the users. What a product does is take a really complex idea like money and Ko-Fi or data availability and puts it into a very simple developer experience where the developer with a few lines of code can express this very complex idea in an instantiation in the real world. And I think that that's really what's missing right now. Like, we've built out the infrastructure. We don't need 5 more consensus protocols. Like, let's use what we have because it's plenty fast enough.
Great. I would agree. Zaki, since you have such a great taxonomy of the now hundreds of, close to 100 blockchains that use Tendermint, maybe 65 or so connected IBC chains, application specific or not, what applications are missing for IBC chains that would bring in those new users that would then create the flywheel for more developers to come in?
I mean, I think there's an interesting thing that's happening right now, which is like there was like, as a practical matter, a real lack of applications in the internet of blockchains. So we like built out this interchain vision, we had staking, IBC transfers, it was all, okay, great. You saw all of these new chains spin up. We basically had one popular application, which was Osmosis. And then there were a lot of applications also in the Terra ecosystem. And like a lot of the interchain application development was happening over in the Terra ecosystem. So Terra ecosystem explodes last year. takes out a lot of the application ecosystem in the interchain, and then you end up in this sort of like we've spent this year where there's kind of like nothing to do but stake. Now, I think in the last like few weeks we've seen just this like enormous number of new applications. Some of them are come from that Terra world and are launching on top of Osmosis now. You have teams that are funded by various accelerators and DAOs all launching. So there's actually now quite a lot to do with your assets. There's seems to be like a renewed enthusiasm for NFTs on Stargaze, and all of these things are maturing rapidly. Like the user experiences are almost acceptable. They're about to become actually acceptable with sort of the APIs that like Skip has built. So on the whole, I think we're kind of at an interesting threshold point where one of the biggest challenges that like Cosmos needs to overcome is sort of reactivating our user base. We have a user base that has kind of, built a relationship with the software that's basically like, oh, okay, I just like stake and occasionally sell my staking rewards or whatever. Now there's all this new exciting stuff to do about with the stuff with your staking rewards, et cetera. Now's the time to like actually get them to go out and experiment. Again, this is the time to like go out adventuring in the interchain, and I think that's one of the biggest challenges. Another big challenge, though, is all of the growth tooling to do that. Like as a product builder, you actually have to go out and reach users and communicate with them, understand their needs, get them to engage, build growth funnels. That infrastructure is also being built out in Cosmos.
Yep. Ethan, what's your biggest hot take in the Cosmos ecosystem, whether that's technically, architecturally, or from a user perspective?
Putting me on the spot. That a lot of it, I mean, it's not surprising, but I still think a lot of it is really like vapid. It's so much just like assets. What are we doing with our assets? And we might as well be bankers, That's what bankers care about. And we're supposed to all be here to like change the financial system, but we're just kind of rebuilding it. Yeah, it's transparent and it's more decentralized and open, and that's really important. But what's even more important is the underlying structure of debt, really, that we're that we're replicating. And so I think until we really break through the like number go up and have like real applications that aren't just about that, we're not going to make it. So maybe you all think I'm not going to make it because I'm the guy pushing back against speculation. I mean, obviously I understand speculation is important for bringing in users and excitement and hype and narrative and memes, and that's the stuff that sort of makes the world go round. But I'm still looking for applications that sort of move beyond that aren't just about finance. And I think there's an opportunity now with the sort of impending collapse maybe of the social media empires. There seems like an opportunity to get in there. Of course, it's also fragmenting, which is sort of interesting, but I think that's an opportunity that this community needs to figure out how to address. Now, arguably, we need more scalable infrastructure to do that. And so, what's the thing that's missing infrastructure-wise? I was going to answer for Ishmael and say Celestia launch, but he can answer for me too. But otherwise, I would tend to largely agree with Jack that there is a ton of infrastructure here. It's just about making it more usable and accessible for use cases that aren't just about speculation, right? Like if you talk to some people, I was just talking to someone yesterday at OsmoCon who was like telling me how they're kind of embarrassed to tell their friends that they're in crypto, right? And this is like a serious, developer in crypto building like infrastructure and real stuff, but it's like embarrassing. And I still hear this from people. Sometimes we try to hire people from Web2 and they're like, oh, crypto, that's just a bunch of scammers, and right. And so there's still that. Yeah. So there's still. Some of us are proud of it, we all like degens, whatever. We'll show you, but so I think there's a real image problem. I think that image problem comes from the lack of sort of more real applications, and that's on us to find those applications, and it's hard. I mean, the early applications are going to be speculative, and that's okay. But sort of moving beyond that, I think, is the next big challenge for all of us to make this work. So,
I do think that's actually like one of the benefits of moving to this data to like modularity that is sort of underappreciated, which is one thing that I don't think we fully grasped until like we saw it live was that the incentive structure of building Cosmos SDK chains meant that you had to build like liquidity and narrative around a token long before you had a product that was useful to anyone at scale. And so I think like one of the most exciting things to me about like sort of these modular architectures is you've seen this in the Ethereum world where people are able to launch apps, build an app, build an application, build an environment, build a community, build a lot of excitement. Typically, a lot of excitement about the coming future airdrop, but nevertheless, that's a different sort of expenditure of energy than having to sort of build liquidity around a token right from the get-go. And I think we're going to, and sort of the modular infrastructure and the way in which you sort of pay as you go for using that modular infrastructure rather than having to like build this like huge upfront cost. I think a lot of it was always described as like, oh, it's really hard to get validators. I think most of us have experienced that getting validators is not that hard. There's like hundreds of them, and they're all looking for some new thing to speculate on, which is your token. And they're all, that's the structure of their business. But like having to devote time, attention, energy to like liquidity of an asset and narrative around an asset before you have a product is just a huge disservice to everyone and like feeds into only building speculative applications.
Yep, I would agree. Ishmael, maybe you can talk a little bit about, as we're seeing basically every ecosystem or L2 converge on these modular frameworks, Cosmos having started from a different perspective, which was interoperability first, Ethereum having started at share security first, how you would position Celestia against other DA solutions, building on Ethereum versus building on Celestia and other Cosmos-related blockchain primitives.
Yeah, I think Celestia is the least opinionated, right? Like it's like tries to be as neutral as possible by not like enshrining a settlement layer, for instance. I mean, for like other pure data availability layers, the main differentiator, I guess, like is that we're probably the first, like that would go to market and like the first that like has certain features like data availability sampling live and running on like a testnet. So I can't predict the future, like on how this like ecosystems will play out. But I'm I'm a bit biased, but I'm obviously convinced that like the feature set, the team, the being like early, like I mean Mustafa came up with the paper in like 2019. The groundwork was done in like 2018. We've been talking about modularity long before it was like a buzzword or conferences being made, right? I think that is the main differentiator is like the tech and the cloud that we have.
Yeah, just to tag on to that, if you think back to the 90s, we had Microsoft was the dominant operating system. And that was like this one ball of closed source software that nobody really knew how it worked. It was incredibly tightly coupled. And they built this whole ecosystem around that. And Linux came around. That was a set of composable modules that allowed you to plug in any hardware and easily integrate that. And Linux like grew a lot slower, but it's ended up taking over the market for operating sources and computing. And I think that this is very similar. In Cosmos, we've come at this from modularity first, and Celestia's kind of taken that to the next level. But in Ethereum, they started with this idea, and it still is the fundamental idea in Ethereum, and you see this with the L1, L2 dichotomy, L3s even, people are talking about now, that's being pushed. The centrality of Ethereum within that vision has always stayed. ETH the asset and ETH the chain. Both of those instantiations are what everything else in the Ethereum ecosystem sort of aspires to filter down to. And when you build those assumptions deeply into your software, it makes building actual modularity much, much harder. And I think that that's the advantage we have is we've built from that place from day one. We've learned all the hard lessons on how coupling makes expansion difficult, and we've had to push through a lot of those software barriers and like help make better interfaces. And you know, yeah. Anyway, it's a slightly unformed thought, but yeah.
Yep. Zaki, what's the future for general purpose L2s on Ethereum, say? We're all in Cosmos because we think that rollups or blockchains themselves will be application specific. So what's the relationship between Ethereum base layer, L2s, L3s, and why developers would need a Gen Perp L2?
So I think like my general view of general purpose L2s is they are meeting a need for rapid prototyping. Ethereum itself, as Ethereum has gotten more expensive and has developed a lot of, and has frankly like become a playing ground for like large dollar value real use, right? So like large counterparties do use Ethereum to like move large amounts of money and use like a set of DeFi building blocks to do so. The rapid prototyping sort of environment of experimenting with new applications. I think like one of the hardest things, like, you know, one of the biggest challenges we've had for Cosmos is it's probably not the first thing that a new team should be building is an app chain. Like a general purpose environment is actually probably a better place because you have to sort of don't have to invent the world, and you have to like you can figure out your product market fit. You can figure out who your user base is. You can build your community. And so I think the model of DYDX is really like the model for the app chain world, where DYDX, the app chain is DYDX v4. And there was V1, and there was V2, and there was V3. And V1 and V2 were a general purpose product built on the Ethereum blockchain, using it as a general purpose ledger. V2 is an application specific L2, or V3 was an application specific L2, and V3 is an app chain, right? And they learned along the way what had product market fit, what were the key features, what did you actually have to target and build, and that then, you know, making that 1 year investment where they eventually stopped improving the existing legacy product and built the app chain version of it make sense because they had like all of this knowledge and all of this experience built in. And we're all going to see how that turns out, but that's a more plausible like way of getting there. And so I think like sort of like now you have like a bunch of you have a bunch of general purpose Cosmos chains where you have functionally like where you have Neutron and Archway and Osmosis and like all of these new general purpose chains where people are rapid prototyping new applications, and some of those new applications may eventually pave the way to be independent app chains. But that's sort of how I see the relationship. And most of the modular teams seem to have bought into it across it, where they are launching general purpose chains now and toolkits for building your future application specific chains.
Zaki, do you see a path for going from like a Web 2 app first to then an app chain, like instead of starting from like the EVM kind of environment or something like that?
Yeah, I mean, I think the only the real challenge is like, I mean, in all ways, like building decentralized software is just a lot more difficult, but like the biggest challenge is self-custodial monetary systems are such an important value, and that's really what you have in whether it's the app chain world or the smart contract world is like, can you plausibly build but you know, also, you know, as a, you know, where most of us are, or like, you know, most of us are Americans or exposed to like sort of the Western system, which takes, you know, where you have a lot of financial regulation the minute you have custody. And that's also a big sort of barrier to building. So I don't know, like you'll probably see more, like I've been watching what's happening with this like Unibot thing. I don't know if anyone, I think more of the degens in the audience probably are following it, but it's basically like, it's literally like it started out as an application where you're basically just like, where there's like, you're just like giving your private keys to a Telegram bot, right? And like moving money through that. But it does seem to be like developing into like a real thing.
To come back to Bucky's point earlier, like I think it would be nice if developing, like starting on Web 3 would be as easy as on Web 2. Like as Zaki said, it's like much more difficult currently. But like as Jack also mentioned before, like I think what the infrastructure that's missing is like to make that easier. So I believe that will be the case. Like it might be that there might be trade-offs, right? Like there will be trade-offs, 100%. But like just from the usability point of view, I think it will be possible to have something like AWS kind of style where you code your thing, you click a button, and your chain is running, right? Like that is like not too far-fetched at all. There are teams working on that right now. So I think that will be possible. And then there's no reason to start at Web 2 if you plan to be like a decentralized app afterwards, right?
Yeah, right. I think just to like, there's a couple orders of magnitude more developers outside of crypto than there are inside of crypto. And I think a big part of that is the developer experience that's been most pushed in crypto is this EVM developer experience. As somebody who's worked in Web 2, it's not a great programming language to work in. And I think another advantage we have as an ecosystem is we've got this proliferation of other VMs and programming languages that you can write in. JavaScript with Agoric, Go with the Cosmos SDK, Rust with Wasm, and many, many others. And that is, I think, going to be key to longer-term developer adoption. Offering these developers something that they're familiar with, meeting them where they are. And yeah, that's also going to be key.
So developer experience is one thing, user experience is another. I'm curious how you guys see wallets playing out in an internet of thousands and thousands of blockchains. Are wallets application specific? Is there one to rule them all? Is there a WeChat style wallet for crypto? What are your thoughts there?
I mean, a kind of far out idea is that wallets are just top of funnel for applications. So wallets go find the users and bring them in. Exactly how they do that, I think there's a lot of white label solutions out there already. And you could imagine a convenience store launching their own wallet that has their loyalty program that's run in USDC, and that filters back down into the interchain. And wallet is this term that I think we need to unbundle a little bit, but I think the way that we talk about it most is that sort of top of funnel of the users. There's obviously the custody pieces, there's the technical infrastructure that's needed to make that happen, and all of that stuff is really cool. But at the end of the day, it's about eyes and clicks and tokens, and that's users.
Zaki, if you could snap your fingers and make one thing happen in the internet of blockchains to accelerate growth and adoption, what would that be?
Well, I think it would have something to do with the wallet conversation. I think we don't really, I don't feel like I have, as a builder, a detailed understanding of consumer behavior regarding wallets. The way consumers behave with wallets mostly doesn't make sense to me. And things that don't make sense to me is like, why is MetaMask so sticky? Like, why is that so sticky? And why is it that the user feedback, but like at the same time, like, why is it that like users are like, hey, I use Kepler and now you want me to install MetaMask to use the Sommelier app, and I don't want to do that either. Like, very confusing to me, like what exactly it is, because I don't personally experience it. And like one of the biggest challenges I think we have in general is that a big part of like where application builders lose contact with their users is in the wallet infrastructure. Like, we have this third-party piece of software that we don't really have control over. Like, we push a user into it, and then like we maybe see the output, but we don't know what goes on inside of it. And it's like, it's a real blind spot in understanding sort of consumer behavior. So like, what wallets have to be like such that users will mass adopt the interchain is, I think, like one of the, that is like one of the biggest pieces, and we just have lots of theories. And those theories now need data to sort of validate them. And it's hard to get visibility into that.
I think that in the same way, I was talking earlier about the Ethereum community having this core ideal of everything kind of filtering down to Ethereum and how that shapes their worldview. In Web3, so much of what we do is a reaction to what we all really don't like about Web 2. And I think we have a lot of blind spots when it comes to some of the good things about Web 2. And what Zacky's talking about with tracking users is a great example. When you're an app and a user clicks through the Wallet Connect, there's a lot of missing analytics in that flow that don't allow you as an application builder to understand what the user behavior is and how you can help improve those user experiences. And it's the same thing with the programming languages thing. Like, we need to meet those users where they are. And yeah, that's a key missing.
I think the thing that's Skip is with IBC.fun and then their announced Kepler integration is, like I was saying, like one of the biggest pain points of Cosmos right now is that like there's this website tfm.com that no one has ever heard of, but it makes the IBC UX 100x better. And it's like mostly what I use to interact with IBC now. I used to use like the Osmosis deposit page or whatever and those sorts of things. But now we have, I mean, like that experience, much of that experience is now coming also to be integrated into Kepler. How will that change behavior? I think is going to be a huge like data point.
So how do we bring those users in for things like TFM or IBC.fun if we don't have any insights into that behavior? If we're in blockchains and most wallets are pseudonymous unless they're doxed, how do we gather any insight into top of funnel business development for applications and preserving privacy on the other end?
I personally think like I mean, tracking users in the browser, like opt-in is an option, sure, like telemetry and stuff. That would certainly give us insights. But I think like it could start even much simpler. You could like just do usability research, talk to users, do focus groups. It sounds very like naive, but I think you will catch most of the flaws of like our thinking of how users interact with things and they're actually interacting with things. Like I think you'll catch like 80% of that just by like doing proper usability research. And I think that should be done independently of like one ecosystem. It shouldn't be like driven by like, oh, we want to like figure out MetaMask, we want to figure out Kepler. It should be independent of that. Like here is a user, they want to interact with like an app or Web3 or something, and it should be independent of these ecosystems, in my opinion. I think that would already move the bar much higher.
This is kind of an aside, but Zoko from Zcash is one of the people I've seen do the best job of this. Every time he meets somebody for the first time, he has them install a Zcash wallet on their phone and then sends them Zcash. And he times every step of the process and keeps a record of all of these. And like this type of focus on user experience is missing in a lot of places.
I think there's also like a kind of an interesting question. Like, I don't think we're really clear on what the top of the funnel is for the modular ecosystem. Is the top of the funnel like ETH L1 users or like monolithic blockchain users? Is the top of the funnel like social media? Is the top of the funnel like Web 2 application users?
It's Tron payments in Asia.
Quite probably, yeah.
Not a joke.
You're right.
A quick survey, how many people in the crowd, raise of hands, has a Kepler wallet? That's a pretty decent amount. Okay, maybe 80, 90%. Zaki, let's close on this. Tell us how to get into the Cosmos ecosystem. What is the path of least resistance as a user?
Kato and Squid. Those are the things. Like Squid Router is great for bringing assets from any other ecosystem, onboarding from lots of places. Kato is a great experience for onboarding from fiat. If you're in like sort of depending on jurisdiction, et cetera. But I honestly think that like again, one of the missing pieces, like I know a bunch of Ethereum people got excited about Bad Kids and wanted one. They were all like, how do I onboard onto Cosmos? And I was just like, Squid. and it's like it's that easy an answer. I think more support, like with like the worm chain and like Noble coming online and stuff like that. There's going to be more options to that, but that's right now the best.
You couldn't get them to install Kepler?
They did. No, Kepler was fine.
Okay.
They couldn't figure out how to
Get
get
the asset,
assets
yeah.
into Kepler.
Okay.
And this is like those core pieces of infrastructure that have gotten built out. One of those is swap and forward on osmosis, where users can send an IBC packet in, have it swap automatically, and send those assets out. So in this particular flow, you want to buy bad kits on Stargaze with stars. You need those stars somewhere, and you need to make those IBC transfers. But the automation makes that easy. It makes it a single transaction on Ethereum for the end user, and they end up on the chain they want in the asset they want. That's a key experience.
Yeah, and I don't think we're that far from being like, I have ETH, I want a bad kid, and like you don't have to do anything other than like sign an intent or an order or whatever, and then there's like the infrastructure will just take care of it. We're really not that far from that future.
Cool. So if you're in Ethereum, go to Squid, transfer some assets over, buy a bad kid. If not, go to Cato, install Kepler, come on over to Cosmos. We have a lot of fun, boxing matches included. I'm sure everybody is hungry and looking forward to lunch, so I want to thank everybody on the panel for all of your time and you guys for being here, and have fun today.
Thank you, David, for moderating.
Hello, friends. Welcome to day 2, afternoon or morning of the Modular Summit. This is also known as PBS.day. In fact, in PBS.day, we will be talking only about peanut butter. Just kidding, not that one. Public broadcast, also not that one. No copyright infringement. Proposer, builder, separation. We have a naughty speaker today who is recoining it into prover, sequencer, separation, something along that line, not sure. So it's up to you all to listen to their digest of the architecture of a particular market structure that specifies the roles of the protocol actors and non-protocol actors, and trying to resolve an inherent conflict of interest of those who have the power to be the information fiduciary as well as the responsible for the execution. So without further ado, we'll first start with Tarun giving us a grand unifying theory of MEV, last I heard. And starting from there, we'll dive into PBS land.
Thanks. Okay. I think maybe these will show up. There we go. Cool. Cool. So yeah, so we're going to talk a little bit about something I've been probably working on for a few years at this point, which is to try to really come up with a good understanding of what the word MEV means. And if you try to really formally define it mathematically, it turns out to be quite a bit difficult. But it turns out there's a bunch of different components to it, and this is the second of some number of parts. I'm not sure how many there will be in the end. You know, oh, I guess this is, these are the old ones, yeah. But, so basically the idea is that, you know, understanding what MEV is from an incentive mechanism standpoint involves really understanding many different applications, right? There's, of course, the most common type of MEV with AMMs, but AMMs, of course, add a ton of different properties that make it easy to understand them. There's MEV for liquidations in lending protocols and perpetual protocols. There's MEV for front-running NFT auctions. All of these things have different sort of levels of understanding for the user. And in theory, right, blockchains are supposed to provide auditability properties, verifiability properties, and other things that form to users. So you might say, how is there uncertainty that can come from these things? So I like to think about the uncertainties as falling on a spectrum. And the spectrum is sort of defined by how much the payoffs that users are taking vary and are uncertain. And PBS is aiming to kind of change some of that uncertainty amongst the first 4 categories, which are ordering, inclusion, atomicity, and relaying. So ordering uncertainty is I submit a transaction to a blockchain, and I expect a certain payoff. I expect to pay a certain price for a trade. I expect to sell an NFT for a certain price, but my realized outcome is not that. Inclusion is censorship resistance. Like, if I send a transaction, does it actually get in the next block? And it's slightly more severe than, say, just liveness, which is I eventually get my transaction in. I may want to have some time preference on how fast my transaction is accepted. Atomicity is, of course, the idea that I can compose 2 things and it's executed as sort of fill or kill, like the entire transaction is executed or single transactions are executed. Relay, which I'm sure you'll hear a lot about today, is the idea of having, you know, a networking layer and some sort of agents who convey transactions, who may be more trusted than you think. And I think that's certainly the one part of the PBS system that we'll hear today has some of the incentive problems from many different speakers. And finally, since we're at the Modular Summit, we should also remember the highest payoff uncertainty for the end user can come from a DA layer. If a DA layer doesn't work, doesn't behave as expected, you can have arbitrarily bad payoffs. Your rollup is not working as expected. And one question you might say is like, what does it mean to move from left to right on this diagram? So just as an illustrative example, and this is more a statistical learning theory perspective on this, is I have sort of a class of payoffs. That's the script curly f. I have sort of some functional, say like a variance or some type of deviation. And I have some sort of notion of the types of uncertainties. And I say, what is the conditional expectation of that functional? And what does it look like? What's the worst case? So one definition of MEV you could use is any sort of mechanism that creates payoff uncertainties where unsophisticated users lose value relative to sophisticated users. And the uncertainty is the key to the unsophisticated users' expected payoffs. So of course, there have been sort of multiple different ways that people have tried to go about this. It's not lost on me that everything in the communist side is only a paper and not a product, and everything in the capitalism side is a product and not a paper. So just as a funny aside. But the communism side is things where the mechanism designers or the protocol designers are trying to enforce a lot of constraints on what types of orderings are allowed to be conveyed to the blockchain. And the capitalism side, the blue pill, is how do you make a competitive market for transactions? So Flashbots sort of created that initially. I guess arguably the spam in the Ethereum mempool prior to Flashbots was the first version of this. And then it sort of expanded, and now we see this whole ecosystem built around this, right? So we have the red pill, we have the blue pill. Are there really only these two options? Well, one thing that, both purveyors of all parties will tell you that, hey, our mechanism reduces uncertainty for users. It reduces payoff uncertainty. It's easier for unsophisticated users, ... or it's more efficient for the system as a whole. But neither of these types of mechanisms, neither the full ordering complexity piece nor the economic piece actually can remove these uncertainties for users. So maybe we should take a step back and try to understand what fairness looks like in general. So I found this actually very nice old paper from the 1970s from Hal Varian, who's the chief economist at Google now, on distributive justice and welfare economics and theories of fairness. And the TLDR of sort of the principle of fairness he uses, the maximum payoff for any particular individual is not so much greater than the average payoff, average welfare of any individual. And that's sort of the maxim for how to measure this type of uncertainty. I look at the maximum payoff that any user gets. I look at sort of the average payoff people get. And as long as those two things are relatively similar, you're relatively fair. And you could argue that the communist, the order fairness things, focus on one side of this, but they're very payoff agnostic. So they kind of can't tell you anything about whether you're getting the worst case or best case. They just say, hey, well, validator said you got this transaction first, so I guess I'm putting in first, maybe. And the economic mechanisms sort of focus on maximizing payoffs, right? Maximizing revenue that goes to validators, maximizing revenue that goes to the system. But it doesn't really capture the externalities necessarily as well as you might think. And so one question is, how do you get this balance between maximizing revenue, which obviously can be good for the stability of these systems, especially if they rely on arbitrage, versus making sure the expected welfare for all participants on average is not so far away from the worst case. So one important thing to think about is maybe fairness should be done on an application-specific level. So the analysis we'll talk about is from the perspective of there being sort of fixed universe of transactions. So adversary or malicious validator could have added or removed transactions before we analyze it. And the only actions that the malicious adversary can take are reordering transactions. So maybe it's, I have a bunch of sandwich attacks, I'm reordering them so that the most expensive ones are first, so that the later ones have to pay a higher price. And the key thing that we'll talk about is we're going to view these as these kind of payoff functions that depend on a permutation and give you a value, a real number. And that's sort of the fundamental objects we're looking at. So in AMMs, you have kind of this very smooth payoff. With enough liquidity, reordering doesn't really change the price impact enough, and you can kind of smoothly vary how that looks. But then on the other hand, we have liquidations, right? Liquidations are very not smooth. You know, if the price never touches a certain point, there's no payoff to the user, to say a searcher. Of course, the price touches a single point, you have a jump and discontinuity in your payoff. And so what we'll see is that these actually turn out to be the fundamental basis of all the payoffs of this form, where you're looking at reordering. So let's maybe try to demonstrate this in pictures. So we take an AMM, like a Uniswap, a CFMM, and now consider a set of transactions. There are 7 transactions here, and there are 4 transactions that are price goes up 1 unit. Those are the green bars. There are 3 transactions that are price goes down 1 unit. And as you can see, if I permute the green and red arrows, I get different price trajectories, right? And so you can see the first one sort of is like, you know, up, up, down, 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 up, up. And then the second one is up, 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 down, down, down. And at each point, you can say, given a permutation, here's the price trajectory created by this ordering. And so the x-axis is sort of the index as the transactions are processed. So one of the first part of the towards the theory sequence sort of showed that for AMMs, this thing is actually bounded in a very interesting way, in that provided you have a particular liquidity constraint, the worst and expected behavior are only separated multiplicatively by a factor of log n. So that sort of is actually pretty good. It means that realistically, I'm not going to get that much worse of a price, even if I'm sandwich attacked. And that paper also showed some examples where people get better prices if they're sandwiches, where someone takes a worse price, but the end trades in the block get better execution. And so there's sort of this somewhat surprising thing, of course, that these sandwich attacks, these things that, you know, the Ari Jules of the world would call robbery, can actually help the welfare of the system, which is like a totally interesting and surprising result. But the thing is, this doesn't really dictate all the other types of MEV, right? It doesn't tell you anything about NFT minting. It doesn't tell you anything about liquidations. It doesn't tell you anything about cross-chain. So we'll start with a Gedanken, like a thought experiment. And the thought experiment is, suppose we construct, you know, this is not necessarily a good DeFi protocol, but this is just one that you can analyze. And so you'll see why this is important. But imagine I have an AMM, I have 2 N DEX trades. Half of the trades are +1, so half are the green arrows. Half of the trades are -1, down arrows. And given a permutation, I get one of these charts, right? One of these 3 things. You can see how like permuting the indices gives you different price trajectories, right? And if the price trajectory touches the red line, the liquidation has a payoff of 1, and if you never touch the red line, it's 0. So the idea is this is a very simple thing where I like say, I give you some trades, I look at all the permutations, if it ever touches a particular point, then you realize a gain, if you don't, you realize a loss. So what you can do is you can kind of look through the sets of permutations and say, okay, does this one give me a loss? No, yes. Does this one give me a loss? No, yes. Does this one give me a loss? Yes. And I somehow found some Mortal Kombat fonts online, and I wanted to write, you know, like, you know, the finish him, finish her thing. I figured writing Liquidated in that font would be fun. So one very, very interesting fact is any payoff function that you can write in a blockchain that is a function of these reorderings of these permutations can be written as a linear combination of these liquidation games. So any payoff, that means for any application, is written as a sum of these different liquidation games. That's sort of something that's very unintuitive, that these kind of very abstract things that you find in DeFi for people taking leverage somehow are a basis for the set of all payoffs you can get. But the interesting thing is the liquidations are much worse than the AMMs. In the AMMs, we showed this thing where it's bounded by log n. But in liquidations, I can construct something where it's actually the ratio of the worst case payoff to a user versus the average case is O of n factorial, which is obviously significantly worse. With needless to say, that's not really an ideal thing. So that sort of says this idea that the space of these, welfare metrics that you're measuring on users can vary quite a bit. And again, a lot of the kind of things people have made and said that would fix and make things more fair don't solve this problem. Like, none of the ordering schemes in the communist column actually can correct this. So you might say, okay, well, what do we do to actually measure how fair these things are? Is there a way for me to say, give me your function and tell me what the difference between the maximum payoff and the average payoff is, and give you some guarantees on fairness? And so we'll see that sort of some analog of a Fourier transform is the way to do this. So one thing, kind of just as a reminder, or if you haven't seen it, well, what is the traditional Fourier transform? So if you think about sound waves, what you're doing is you may have this turquoise curve that represents the analog sound signal you're hearing, but you can decompose it into high frequencies and low frequencies. So maybe high-pitched voices and low-pitched voices represent the red and blue curves. And the Fourier transform lets you take different segments, break up the curve into pieces, and say, okay, this is the sum of these different components. You might say, what does that have to do with MEV? It's like a smooth curve and someone singing and all sorts of things like that. But the interesting thing is, it turns out all of these payoffs under reorderings, you can write as these sums of liquidations, and the analog of the sinusoid curve, the single pitch, is actually a liquidation. And so the high frequency modes are liquidations where there's very few permutations that can trigger them, very few reorderings. And the low frequency modes are ones where there are many permutations that trigger them. So you can kind of think of it as, when I expand out a payoff, I am looking at how constrained I realize that particular payoff. And again, as I was saying, this is sort of a fundamentally important thing, is that something that we understand relatively easily and that people do in practice, liquidations, actually generates a set of all payoffs. Now, this expansion might be very big, right? I have a sum over a subset of subsets of permutations. There's 2 to the n factorial of those. So there are many of these you might need to expand it. But the key is that this is a basis, like it represents the core set of all these payoffs. And I put examples of people involved in the algebraic versions of Fourier transforms as pictures. So one question is, how do we interpret this Fourier transform? Like, what does it really mean? So one way of thinking about it is the Fourier coefficient, f hat, and these are sort of heuristics. There's a lot, the Fourier transform over finite groups is quite a bit different than the continuous one, is if a set is large of permutations and the Fourier coefficient or that set is large, that sort of says the permutations the function achieves its average value on those. If the set is small but has a very large Fourier coefficient, you're near the maximum value. And so the idea is that this is why the spectrum of this thing captures what the maximum and average values are of these functions. So, there's a bunch of things you might need to talk about these. We're definitely not going to talk about them. And since it's a Celestia conference, I had to put Jacob always says weird aphorisms, such as none of these words are in the Bible. So He's mad at me, though, for picking this picture, but it's the first thing you find when you Google his name. So you might say, OK, great. I have this Fourier transform. I can take any function you give me in a blockchain. I can sort of write it as a sum of liquidations, and that's like what the user gets paid. But that's great, but like, what does that tell me about bounding the difference between the max and expectation? Many of you may have heard of things mimetically like uncertainty principles, but uncertainty principles exist outside of just physics. In fact, they exist in information theory in general as these sort of lower bounds on localization. So if I can squeeze a function and make it very sharp, I can't make its Fourier transform super sharp also. And a very nice thing that turns out, and this is exactly why we're, all of the stuff we're talking about earlier is important, is A, liquidations generate all the payoffs. B, the Fourier transform gives you a way of going from your payoff to the payoff represented in the basis of liquidations. So the Fourier coefficients really give you how to expand it in terms of liquidations. And C, the uncertainty principles give you a bound on the max over the expected value over the max value, which is the difference in payoff for users. So this gives you an explicit way to quantify this type of fairness. And you can kind of think of this inequality as showing you fairness bounded by sort of these spectral properties. I didn't want to go into any more details of this, but you can read the paper. But I'll just give you a very, very tiny kind of understanding. But the idea is if you allow a large enough number of permutations, there's sort of a notion of the size of the number of orderings you allow is sufficiently large relative to the Fourier transform, you actually avoid the maximally unfair payoffs where the expected value is extremely small relative to the maximum. On the other hand, if your sort of sets of orderings don't have sufficient overlap with your coefficients, you'll get a lower bound on unfairness. You'll always be at least some amount unfair. And this sort of shows any of these types of ordering mechanisms, whether they're the time-based ordering in Arbitrum, whether it's pure fair ordering sequences, whether it's sequencing rules, they all only work for certain payoff functions, right? They only work if they restrict the set of orderings to some set of to a certain size set of orderings. But that means they distort any payoff functions that depend on orderings with a larger size. And so you get this kind of sort of Shannon sampling limit of like the payoffs are tied to your ordering algorithm. You sort of can't get a free lunch of like offering things like first come, first serve and satisfying every possible payoff function, which is what this says. The second thing is you could think of this as like a sampling theorem. So the sampling theorems are, the most practical time you've ever encountered one of these is when you've, maybe listened to an MP3 that sounds really shitty, and then you go, get a vinyl and you listen to it and it sounds great, and you're like, oh, why does the MP3 sound bad? Well, the MP3 didn't sample enough frequencies for it to resolve correctly versus the analog. And this is sort of a sampling rate. It says like for a payoff, you have to have resolved enough frequencies for you to be fair in that payoff. So what this sort of suggests is the communist version of the world, the fair ordering type of stuff, things that are sequencing rules, is always going to preference certain applications over other applications. We always talk about MEV as being sophisticated users taking advantage of unsophisticated users. I would posit that the communist ordering world is sophisticated application developers taking advantage of unsophisticated application developers. All you're doing is changing who the person who's enduring the penalty is, because the application developer is defining the payoff function, and if they don't understand how all this works, then they may have defined one that's extremely unfair on purpose. And now you're forcing the application developer to understand that, whereas that's not as true in the unrestricted ordering case. But what this says is application-specific orderings tied to these functions, can be better in practice. And maybe that comes from marketplaces like Suave, things that allow each application to specify some sets of rules, as opposed to having these global sets of rules. And yeah, it's much better than sort of some of the useless communist versions of things. So what's part 3? Well, everything here is like a formal theoretical thing. There's a lot of n factorials everywhere. Not all of us love Sharp-P complete problems, ... So the next part is approximation. Can you come up with measurements that you can make on real functions that give you some notion of measuring how much the max and expected MEV are up to some error in production, and monitor these types of metrics and see how well people are performing? And it's a paper. So with that, I actually finished 30 seconds early, so if any question. Yeah, so you gave this point about CalSwap, great point. When I talked about the O of log n thing, CalSwap is achieving that. So that's what I'm saying, log n is not that bad, right? Like if there's n trades and I'm able to not get front run, but I may have to pay in the worst case log n more in price multiplicatively, it's not that bad. Paying n factorial is much worse, right? So like that's the idea. Like this is like a way of quantifying how much the worst and average are. And the point is, once we can approximate these better, you can run these on live systems and say like, oh, actually this particular payoff is like not that fair. You should like loosen the orderings or shrink the orderings. And the marketplaces can then adjust after that. Anything else? If not, thanks. I'm around all day, so.
I am Zucky. You've probably seen me already. So this talk is like sort of a appeal to people who are protocol developers mostly, but a little bit of sort of philosophy of protocol design, and generally like my thoughts about like what constitutes a full node and the sort of changing definition. So I've been working on building blockchain like protocols for 10 years. I've written a lot of, I've contributed and worked a lot on different layer ones. That's basically my background. And my general thought is that, okay, so we started out with this like piece of software that didn't come from essentially anyone in the present community, Bitcoin. And Bitcoin worked a certain way. And every blockchain network that has been created since has been in some ways inspired by the Bitcoin full node, by like that original Bitcoin software. And its core property of the Bitcoin software was you have this notion of a full node, and in the original Bitcoin sort of concept, every full node was a miner. So you had this whole network of miners. Everyone was connected to each other in an ad hoc basis, so there were no like special roles. It's just network of nodes, this flat topology, and that is how we've sort of imagined every blockchain since then. But this hasn't been a true description of blockchains, basically for as long as I've been involved in them. So instead, there have been parallel networks, like sidecar pieces of software, specialized nodes everywhere. Like we couldn't use blockchains today if none of this existed. So blockchains would be completely unusable. That's been true since, since like 2013, 2014, right? You've had like Bitcoin has something called the fiber network. The fiber network does fast block propagation between with a completely different block propagation algorithm between mining pools. There's mining pool software, which is incredibly important for the operation of Bitcoin. You have things like MEV-Boost and Flashbots. So what this has emerged is an enormous difference has happened between the actual protocol, like the protocol that our users use, and what's in the full node software. And that makes it very, very difficult for anyone to like reason about, maintain these entire systems. So just like to kind of, so Bitcoin is actually like a pool-driven block propagation system. There's no widely distributed MEV tooling, but like mining pools are in charge. The like network that actually matters is the network between mining pools. The transaction propagation system is how mining pools end up ingesting transaction. The de facto Ethereum network is a network that has a consensus system and a peer-to-peer layer, and a mempool that does not actually matter because MEV-Boost builds most actual blocks. And there's an entirely other network between block producers and relayers and block builders that is essential to the functioning of the system and is potentially vulnerable to exploits, but isn't part of the core protocol. And then in Cosmos, we have this thing called protocol-owned builders, where validators build and check blocks together with consensus-enforced rules to do value extraction. And it's actually cool because in Cosmos, we do seem to be moving to a large extent towards more parts of it, the software being in like the core binary, which is good and more maintainable, but also like sort of represents better the expanding complex. But we've had a lot of problems because our full node software was never designed to do this. So like questions I would ask is like, why do we write blockchains that have mempools at all? It's really unclear why we do this. Bitcoin was basically designed with this idea that like any node in the network could, will once in a while produce a block, so we need to disseminate by flooding transactions everywhere. We have, we really care about the resilience, censorship resistance, and self-repair properties of P2P networks, but it's probably the most poorly tested and specified property of any piece of blockchain software. Like you have all of these papers that clearly specify like the consensus algorithm, the rules, the attacks. No comparable sort of material exists for the P2P networks. So yes, why don't protocol nets put these overlay networks in the core protocol? So the networking layer is the least expressive part of the stack. We have like these crazy expressive smart contract languages. We have the ability to we have very complex and sophisticated consensus protocols, but we don't really have much expressiveness in this part of the stack. Every blockchain team reinvents the wheel. They run into things that they can't build with like the existing software, so they'll like slap on an overlay network and like add it to the nodes as the way things, and like sometimes those will have centralized parts, like in Cosmos when we have Skip, and Skip has become sort of canonicalized into some of the Cosmos networks, but like it's not something people think about as like part of the Cosmos protocol. So yes, we have these like Frankenstein blockchains. Ismail was talking about how Celestia has this like Frankenstein P2P network, which is part Tendermint P2P, part libP2P. And people are always building these things with like other custom components. So I do think that like PBS is just largely a good thing, and the formalization of PBS, because it's driving more innovation and attention towards these areas. It's driving, I think, and forcing the P2P like engineers to like do more on the networking level. It's forcing us to consider the entirety of the block of the network and the protocol as a whole, and it is it's sort of getting us closer to a world where the entire blockchain behavior is like more formally specified. But again, like we've been seeing attacks. So like I would argue that the direction of moving from like MEV-Boost, which is a form of protocol builder separation, but not an enshrined one, even though every single Ethereum consensus client implements it, is sort of a worse solution than enshrining PBS in some form. And we've already seen attacks on nodes and losses of funds and security incidents in the MEV-Boost system, and that would be better dealt with if it was part of the core protocol. Just like kind of the other thing that I would observe is that, so in the spirit of modularity, app chain builders want a lot more control than like traditional general purpose L1 builders ever had. L1 builders did not expect that they would be able to control the MEV for their applications. Tarun was just talking about this like trade-off between sophisticated and unsophisticated users and sophisticated and unsophisticated application developers. Well, if you have a application-specific blockchain, like you don't have to deal with that trade-off because like the team is this application team is the team that built the blockchain. So if they're sophisticated, they will end up wanting probably a lot of control, and they'll want to have their own sort of fairness policy, and they'll want to be able to like punish and slash and observe. And so as people are building toolkits for modular blockchains, people are building toolkits for L1s, I think we have an obligation to start building in more tooling into these systems to allow this kind of control to be expressed. And like the fewer ad hoc systems that people have to build where there's like no abstraction in the full node, the better things will be. So yes, the fundamental goal of modularism is lowering the cost of innovation. It will hopefully result in more shared infrastructure. There will be more libraries. There will be more binary like pieces of software. There will be more examples of building systems where like this block production and pre-consensus part of the network actually exists in the protocol, in the core software. As we have like vendors for things like shared sequencing and intense mempools and execution, like the more they can share components, it'll lower the cost of all of this. You know, the sustainability of all of these pieces of infrastructure as like the market fluctuates up and down should be a concern to everyone and is a big part of the long-term stability of the space. So that's it. Thank you very much. Thank you. I just got a Bad Kids shirt. You should get your own. Is Vitalik next? Robert, then. Okay. Robert? Danny? Okay. I'm getting conflicting information. Does anybody have the, like, what's the MEV here?
The MEV is here. So I think unfortunately, one of our speakers, due to bureaucracies, had not been successful in getting into the Schengen area, so she has to dial in for us. But I think this is an unfortunate reminder of the boundaries and that we live in and the world we live in and what we need to fight for.
All right, I can see myself. And is my slides up? Cool. Now I can see it. All right. Hi, everyone. My name is Danny. Unfortunately, I cannot be there in person, but I'm really glad to be here to share this analysis, or more like a data review about our current state of order flow, block building, latency game. I'm a data scientist at Flashbots. Cool. I'll go through my agenda next. So I'll go through how a Ethereum's transaction lifecycle today look like with an MEV supply chain theory, or you can call it transaction supply network. And then the next is we'll look at how the order flow market look like with the PBS or like MEV Boost, MEV supply chain structure today. And then we'll look at how the block building market look like and how different builders, their behavior look like in data, and also the latency game and time aspect of the block bidding market. Next, So we have two diagrams here. So quick intro about MEV, and I assume everyone heard about MEV and PBS since you're in PBS Day here today. But what is MEV supply chain? In the past, in the proof of work day, if you're making a trade, the miner had the full control about if they want to insert your trade or if they can insert any other trade of their own or per their benefits to be before yours or behind yours. In the proof of stake date, nowadays with a even more concerning problem about MEV can cause centralization on stake and therefore cause centralization of the network, we introduced the PBS proposer builder separation proposal, and MEV Boost is the implementation from Flashbots about it. And the vanilla model of it is basically splitting the miner row into 3 rows. From searcher, they will send bundles to builders, and then they will send the builder. The builders will bid for the full block and then propose to the validator. Validator will pick the highest value and then basically get the header of the block and then settle it to the chain. And then nowadays, with another thing called order flow auction, this structure can even look like the one below, where searcher is sort of separated from this chain. Basically, they take a new row as a bidder of the order flow auction. But again, the flow goes like user submit a transaction to the wallet go through RPC, potentially broadcasted to a bunch of searchers or bidder, and then they will try to search for the maximum extraction of this order, and then submit a bundle to builder and then to validator. So this is a very, important structure that we should remember about the analysis, because I'll go through each layer of the market. Next one, please. And so how does exact a user's transaction or order look like on a concrete example of an order flow auction? We can use Flashbots MEV share as an example here. So either user or wallet can submit in representation of user or a RPC provider. They can basically send to a Flashbots Protect RPC, basically an endpoint where you submit your transactions through, which then actually make your transaction go through a private mempool, and then it will broadcast to a bunch of matchmaker services, which is the MEV share services, which will then broadcast the transactions information based on users' privacy setting to a bunch of MEV searchers, and they will try their best to see, okay, I'm trying to background this transaction without basically hurting users' price, and see if I can make any profits from making another transaction behind yours. And then they will compete to send bundles to the MEV share services, and then the service will try to compare what's the highest value, so to submit it to the builders. In the past, Flashbots started with submitting the bundles to Flashbots Builder, but for improvement on the inclusion of the transactions, we also recently released a feature about allowing user to submit to any of the builder of their preference. In this case, it will make the user's settlement to be faster and better. And then the builder will broadcast to a bunch of relay, and then relay will then see who has the highest bid, and the validator gonna take the highest one. Next one, please. Another example to make it a concrete concept on a DEX orders lifecycle today. Here's a lot of interesting thing to point it out. So when a user comes into a DEX or a DEX aggregator, what they will do is basically they will try to check across the different liquidities on chain and off chain from their professional market makers that is quoting and making the RFQ order for the user. They will compare the price with Uniswap. They will check what's the best price for Uniswap, SushiSwap, all the other AMMs, and then they will compare. Okay, this is the best order. I'm going to send this to the public mempool likely, as in the past how we operate. The AMM orders, if they sent into public mempool, then will be broadcasted to everyone who's listening to a node. And so here there's a bunch of MEV searchers, or basically you could call them whoever is like accessing the public AMM orders will try to arbitrage you or search on this and submit bundles to builders. Another route is that if now DEX aggregator or basically the applications submit their orders into a private mempool, aka OFAs, then they will have their OFA searchers trying to background you, in a much better informed and actually protected way, and then submit through bundlers and to the block builders. So what are we seeing here? All these highlighted red blocks here, if we go next slides, turns out today in our current state is that pretty much the same entities. The RFQ providers are market makers who are like professional trading firm. The toxic flow that is taking the arbitrage on AMM liquidities are market makers. Map searcher, block builders are pretty much from a bunch of big trading firms. It doesn't sound so good. Next slide, please. And with the coming change in our Ethereum network, potentially account abstraction bundlers and maybe Uniswap X fillers can again become the same players. That's some psyops. Next one, please. So yeah, one conclusion or first observation is that the order is flowing right now through a bunch of monopolies who are basically accessing each layer, or basically they are touching the order flow in each layer of the markets. Next, please. Right. So another observation here is that with some data analysis we collected in the past, earlier this year we were trying to do a monitoring on the public mempool, and we saw that there are a bunch of transactions that got settled through different block builders. We're never seeing mempool or in the public mempool, which means there's a adoption going up for the private order flow by different builders. We can pretty much see from January to March, it grew from like 1, 2, or 4% up to 7% per block builders. And this data, I assume, will be only higher after all the OFA launch in April. Next slides, please. Another angle of this data set is that when we look at different OFA order flow auctions, transaction flow percentage out of all the EVM transaction percentage, we can see that pretty much like Map Blocker and Flashbots Protect or Flashbots Map Share are having around like 5-6% of EVM transactions out of all the transactions. Calibra also have a few thousands every day getting settled. So yeah, another observation is that private mempool will have adoption going up along with the adoption of order flow auction. Next one. And then we look at the block builder market share. Here, the current summary will be basically, it's a 2080 market where basically a few leading winners are taking the majority of the block inclusion share, including rsync builder, builder 69, beaver build, flashbots builders, and along with them, there are a lot of new small and strategic builders coming out, including like Titan, F1B. We also have Bloxroute and Block Native playing in the block bidding game for a while as well as important players. So pretty much we can see a diversifying of the participation of this block building game. And then if we would summarize their behaviors in the next slide as a different type of builder, so we will be able to see that, next slide please. So we'll be able to see that we pretty much can see a bunch of builders. They can be defined as neutral builder. Flashbots runs nonprofit builder, which means pretty much it's a very naive setting in terms of how you are transferring the profits in the line. We're basically transferring everything to the proposer and include everything in our bidding value. It's mostly basically a bundle merging algorithm as of today. There's also a strategic builder who are also neutral, but they may take more approach to be more competitive. For example, they may keep some profits from some more profitable block when they know that potentially they're bidding higher than anyone else. They may subsidize the block value when they know they're maybe slightly lower, but they can win by just subsidizing a little bit. They may attract also private order flow by subsidizing and become better at inclusion rate. And then we also have another big type, which are, I would say, like they're the most competitive today as a block builders, which are searcher builder. If you remember earlier, we introduced this concept of like In the MEV supply chain, there's searcher who are basically checking all the order flows MEV value or potential extractable value, and then trying to bundle transactions with them as their own private transaction flow. And then the next, they will basically be able to submit their order flow to their own builder, and basically to have a very exclusive amount of transaction, which are highly MEV valuable, so to compete with the block value, which means all those things are making them very competitive compared to others. Next slides. If you are trying to analyze their behavior on chain, they may seem different. For example, if you are a typical builder, you're pretty much gonna put your address on chain as a recipient first, and then you will appear as a miner basically for this block as of today. But then in the end of the block, you will try to transfer as much as profit you're bidding for the validator to receive as a transaction in the end of the block. But if you're a zero profit builder, you pretty much don't even need to touch any of the profits. You would maybe even just set the validator's fee recipient as the miner of the block, basically let them to receive everything to basically also save some gas. Next, please. And when we look at the open data set that MEV Boost is streaming for everyone from each relay, we can pretty much see that builders, they have different behavioral preference in terms of which relay they are connected to or submitting their block bidding to. But pretty much every builder would want to have a higher or better coverage of different relays. And then most of them submit to the 3 major relays like Flashbots and Builder 69. But we also see rsync and Bloxroute, they are submitting to 5 or even 7, pretty much like every relay. So to make sure they're competing at their best. Next, please. So there's a few more metrics here that's very interesting, which is like when we talk about the time aspect of the bidding, it's a whole latency game for you to be competitive and taking the basically like sniping at the very last second, right before the validator is checking which block is the most profitable. So we call this validators get header timestamp, which is basically whenever the validator is checking, okay, what's the available best bid I'm getting right now. And they're checking with the relays. And it's very interesting to see that different validators here, they have different behavior in terms of when they will prefer to check the get header. Some may have very consistent data points of when they're gonna check it. And that actually very interestingly result into builders' behavior, which is basically they will never actually bid from the very beginning of the slot, but only at the very few minutes, very few seconds, which is when the validators will check the get header. Our Flashbots builder in the past were pretty naive to check since the very beginning of the slot, but we made some improvement after this realization, and we updated the bidding time to be the same as we're on, like -3 seconds pretty much. Next one, please. And another aspect is that if you check how frequent each builder can update their bids as basically their bidding latency, next slide, please. We pretty much see that this is a box plot of different builders' updating time for the latency, basically a bid updating latency chart. If we zoom to the next one, we can pretty much see the number here that on the very left and on the very right, Beaver and rsync are the one that has the highest performance, where they can update their bids within 200 milliseconds or 100 milliseconds, which makes them to be able to react very fast towards the market. Whenever they see a price shift, say on centralized exchange, their searcher will be able to prepare a new bunch of arbitrage transactions and then update their block from their builders. This also caused a very interesting observation in the next slide, is that with some improvement in some relay, like optimistic relay from ultrasound, which is basically allowing the builder to skip a few hundred milliseconds by adding some collateral deposit, we are able to see that searcher builder especially can benefit from this improvement largely, If we see here, the blue line is the win rate of their optimistic submission. And then the orange one will be the normal one. So it can be even like 7 or 8 times higher when they're submitting optimistically. But yeah, again, like right now, today, only Searcher Builder can benefit from this improvement because they're only one that can react this fast and update their strategy. A few last metrics about the relays. Relay also, as of today, they are supposed to be the one that's not taking any profits from the MEV supply chain, but also taking a very important role of validating the blocks they are receiving from the builders. As of today, a bunch of players are running a bunch of relays. The biggest one are Flashbots, Gnosis, and Ultrasound. We can see pretty much Ultrasound is the leading one here with a bunch of improvements, taking a quarter of the market share, and then it's Flashbots. Next, please. One very important thing is for Relay is that the adoption from the validator side, basically how many validators are checking the bids from the Relay is pretty much a metrics here to show Flashbots has the highest adoption as a Relay, and then Blocksprout Max Profit, Ultrasound, Gnosis. Next, please. On the time scale, we can also see that like across different slot time, we can see like per every 100 slot, we can see Flashbots having around like 90 and a little bit higher adoption by all the validators across a 100 slot. And then the next is Blocksprout Max Profit and Gnosis and Ultrasound. One last metrics here is that we can also see that the diversity of diversity of the builders, basically how many builders are submitting the bids towards a relay matters in terms of like how many total submission you will get naturally. And also we can pretty much see Ultrasound and Flashbots are leading towards the right and also are leading towards the higher market share. So we can see a pretty strong signal here of the correlation. So next, please. That's a data review of all the layers of the market structures. And my final note would be, if you're an Ethereum user, you should definitely check out the Flashbots Protect RPC today, and so to avoid uninformed MEV and potentially get refunds from our OFA service, MEV Share. If you're an MEV searcher, I have a few memes for you in the end. If you're a MEV searcher, please send us bundles if you click through the next 4 slides. Okay, cool, thanks.
No memes today, unfortunately. Sorry, Danning. Okay. I'm Robert Miller. My slides will hopefully appear at some point in the future. And until then, you are stuck in silence with me. I'm told they are running, okay. So I'm Robert Miller. I have a talk here, obviously, and in thinking about what to talk to you all today about, I thought first, should I say something about PBS? It's pbs.day, and I thought, no, you probably have heard something about PBS before at this point. You know about it. Someone else will talk about it. Then I thought, should I talk about Suave? We just released a new blog post outlining an architecture, introducing the MEVM. I thought, well, I'm not sure that's the most interesting thing, since you can go and read my blog post on how the MEVM and our latest design for Suave works. And looking at the past schedule that I had this week, it seemed that there are a lot of new chains and domains that are interested in integrating PBS, and they're interested in knowing about how Suave can support them if they do support PBS. And so that's sort of the premise of my talk, is how does Suave support many different domains, heterogeneous domains that have different virtual machines, different ways of ordering, and what is the architecture that enables that? And I'm gonna begin by giving you a little bit maybe these slides are a little different than I expected. But I will begin by giving you some context on the thinking behind Suave and where we were a few years ago when the early ideas of Suave started to coalesce for Flashbots, something like late 2021. So this is kind of the first idea. MEV is fundamental. It's fundamental to every domain, and that's for a few reasons. The first is this ability that blockchains give you to make commitments. And you can commit to pay for some arbitrary state, and that then alters the incentives of the party that's ordering transactions. Second is that we use this ability to commit as a part of a common design pattern in building permissionless systems. So these commitments are a fundamental part of something like DeFi. In liquidations, you give a permissionless bribe to anyone who will update the state of your collateral when prices have moved. Or in CryptoKitties, you give a permissionless payment to anyone who calls a function to update the state of the system. So this permissionless bribe, this permissionless commitment that anyone can capture is kind of this common design pattern to the systems that we're building. And lastly, MEV is fundamental because even if you don't have MEV on one domain, there exists MEV between the boundaries of different domains, and that creates value extraction opportunities. You know, if there was no MEV on Ethereum, there would still be MEV between Ethereum and BSC, as an example. So that was the first idea. Second idea, MEV has these negative effects. So rational actors pursuing their incentives, pursuing these permissionless commitments that make you money, are going to create negative externalities in their wake if you don't deal with it appropriately. So that's things like priority gas auctions, spam, latency wars that lead to wasted block space, network load. At the limit, it can destabilize consensus itself, which is where MEV began with Flashbots 2.0. Economic centralization of validators integrating with trade firms, and sandwiching, et cetera. There's all sorts of ways in which MEV can have negative effects if you don't properly deal with this. And we unfortunately have a slightly old version of my slides, but we will roll with it. So what do you do about this? What Flashbots is trying to do is our project called Suave. So that stands for the Single Unified Auction for Value Expression. It's our project attempting to address this really ambitious problem of MEV being fundamental to every single domain, it having negative effects, and there being many different types of domains in the future that have heterogeneous different designs. So there are non-EVM chains, there are chains that will order with first come, first serve. And we can't just copy paste Flashbots and other people's MEV infrastructure to every single domain. How do we offer MEV solutions to many different domains in a way that is actually decentralized? And what I want to get across today is that there's these two key ways that Suave addresses this in the broadest way possible. And again, we're rolling with an old set of slides, but that's fine. So the first is the MEVM. We just announced this last week. It's this modular, expressive, composable programming framework that allows developers to leverage credible and private compute. And I'll dig into that a little bit more in a moment, but what that means is you can take what is currently centralized off-chain MEV infrastructure and turn it into a smart contract on a decentralized blockchain. And the second is what we call execution predicates. This is arbitrary preference expression on the execution you desire. Again, we'll dig into that. So first, the MEVM. It's a modified version of the EVM that Flashbots is launching. We've taken the normal EVM, we've added new pre-compiles to it for MEV use cases. That's really useful because by exposing every primitive in the MEV supply chain as a pre-compile, you can program your MEV infrastructure as smart contracts on a blockchain, which you think is really cool. And moreover, you can do it within the familiar developer tooling of the EVM. You can do it in Foundry, you can do it in your normal developer environment. And it really lowers the barriers to entry of deploying new applications because anyone who knows Solidity can do it. So how does the MEVM work? This is what the architecture looks like. There are a few stakeholders, a few components. I'll run you through each of it. So at the core of Suave is this MEVM chain that we're launching. Again, it's standard EVM with extra pre-compiles for MEV use cases. That's things like take a transaction, simulate it, return me the result. We have a confidential data store in the middle. You can think of this as a data availability layer where encrypted data is stored because there's too much data to store it all on chain. So this is decoupled from the chain state itself. And we have an execution node. This is not a consensus node, but it's tightly coupled with the chain. It's a node that provides private and credible compute that can be called by the MEVM's precompiles. And the way that these different stakeholders interact with Suave is developers define contracts like order flow auctions, block building algorithms, centralized RFQ routers maybe. Users send what we call bids. That's a combination of contracts that they authorize to access their private data and some private data like a signed transaction. And executors, who are your arbitrageurs, your searchers, builders, are looking at bids, seeing how you can interact with them, and trying to backrun them, merge them, do MEV things. Finally, Suave produces blocks for proposers that are listening to them. To dig into the notion of execution nodes a little bit more, because this is a really important concept, the actual chain, Suave chain itself, stores what bids are pending. It doesn't store any private data that's stored in this off-chain confidential data store, but it registers a user's bid. So it's a user saying like, hey, I have this private transaction, I want it included on chain. And it also registers these contracts that developers have programmed their MEV applications in. And those contracts, when the user authorizes them, are executed within what we call execution nodes, where an execution node will read the code of a smart contract and execute it accordingly. I'll give you an example in a moment. But as an example, a smart contract might say, simulate this transaction and allow a searcher to try to backrun it. And if the searcher successfully backruns it, send that on to a block building algorithm. We run these execution nodes in trusted execution environments like in SGX to provide some level of integrity and privacy to it that isn't contingent on centralized trust in a party like FlashBots. This is an example MEVM contract, so it's standard Solidity with a couple extra precompiles. So you can see here, the fifth line, we get Ethereum state, something that you normally can't do within Solidity. We're deploying this on Suave chain, but we can have access to the latest Ethereum mainnet state. It takes a bunch of bundles that are sent as inputs, simulates them, so it's simulating ordered lists of transactions against Ethereum mainnet state. We're getting the gas price of those, sorting them, trying to apply them to a pending block. So it looks really similar to Solidity because it literally is, but it is able to leverage these new MEV precompiles that call out to the credible private compute provided by the execution node in a trusted execution environment to let someone program a block builder, which right now is this monolithic thing off-chain in Solidity on Suave chain, which we think is pretty cool. And one of the ways that we are thinking about scaling Suave to many different types of domains is that you don't need to only run EVM type execution in execution nodes. So you can have an execution node that supports WASM, or you can have an execution node that supports any weird roll-up VM that exists, and then users can program their smart contracts to call out to that within native EVM on Suave chain. So you can do block building for non-EVM chains so long as you have these execution nodes for different domains. So for every given VM, we'll have execution nodes that folks will run in these trusted execution environments. And you have this single unified platform for writing MEV infrastructure that can access many different types of execution nodes. And it's one way that we are attempting to address MEV across many, 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 many different types of heterogeneous domains. The other way that I think is really interesting to talk about is this notion of execution predicates. You may have heard this as intents or preferences before, but this lets users define arbitrary conditions that they want to be executed for. So in familiar MEV use cases, I want to pay X if transaction hash 0x Baba is included in block 100. I want to include I want to pay only if this array is included. Or things that you can't do today, which might be interesting for some use cases, like I want to pay if my contract emits a log. And why I'm talking about this is because this unlocks new searching strategies that you can't do with current MEV infrastructure today. So as an example, I want to pay 1 ETH if you call my contract and it emits a log, provides an incentive for either latency or spam searchers to try to hit your contract until it's successfully called, right? So you could deploy this contract on Suave, have a corresponding contract on a low latency domain, where spam is the dominant strategy, and it provides an incentive for this marketplace of people to spam your contract on your behalf. So democratizing MEV search on other types of domains, even if they're not natively integrated into PBS itself, which is very interesting. Or cross-domain, I want to pay for X state on Ethereum and Y state on Arbitrum, gives this incentive for atomic execution across 2 different domains. And since you are programming this in Solidity as a smart contract, you can get as bespoke as you want with these execution predicates, which is really interesting because searchers can express, or users can express, conditions that are more complicated than anything the market currently supports at the moment, which either incentivizes people to collaborate together to execute on these conditions, or it incentivizes the creation of new infrastructure to be able to support more complicated types of predicates. So that was my talk. Slides got a little bit screwed up, so I had a little bit more content, but that's okay. So thanks for listening. That's how we plan on addressing many different domains for Suave, regardless of whether you are PBS or not PBS. We have a couple different callouts here, so if you're interested in integrating as a rollup, please reach out. If you're a developer interested in building MEV applications on Suave, please reach out as well. Wallets, if you're interested in MEV redistribution, searchers for private order flow, and that is a QR code if you want to work at Flashbots. So thank you so much, really appreciate it. I think we have Mike coming and talking about PBS next.
So thank you, Bert. The correct sets of slides are up on mev.salon. So if you go to mev.salon, you can find the entire day's agenda with the correct version of the slides. So for the alpha that you missed. Next is our chapter 1, the Ethereum L1 PBS, starting with Mike Nutter on PBS R&D roadmap.
Hey everyone, how's it going? Cool. Looks like the right slides. Oh, this isn't the right slide deck actually. Let's see. Okay, this looks promising. Oh no, this is the wrong slide deck. Tina, one sec. Tina, this is the wrong
Our slides have been reordered.
Yeah, well, at the meantime, you can have a sneak peek preview on mev.salon. Just click on the slides. You can help yourself. So while we're fixing some technical issues here, curious, at Modular Summit, how many of you all here are working on Ethereum stuff? Raise your hand. All right. What other ecosystems are you working on? Nice. Wait, is that Ethereum ecosystem? Ooh. Well, that's fair. Anyone else? Ooh, okay. Sizable contingency right there. Hi, friends. Are we Ethereum aligned? Do you want to do an impromptu lightning talk of 2 minutes of Solana PBS? Let's go. Okay, now we have our favorite milady.
I don't know about favorite milady, but a milady. All right, hello everyone. Oop. I'll go back one. Cool, yeah, so my name is Mike Neuter. I work at the Ethereum Foundation, and today I'll be talking about Ethereum PBS R&D roadmap. So a quick sketch of my talk. I'll first go through what we define as PBS. This is kind of a buzzword lately, so I'll define it in terms of what we mean for the Ethereum consensus layer. And then I'm going to run through kind of rapid fire style 5 implementations of PBS. There are some overlaps between them. We can kind of see the similarities, but I'll present each of them kind of in their own right. And then after that, I'll try and synthesize by pulling them together, explaining the design trade-offs between each one, the timelines, and yeah, kind of try and connect the dots in a way that hasn't been done very well yet, because I think a lot of the proposals and the discussion has been scattered across different forum posts and Twitter threads. So yeah, that's kind of what we're going to go through. Cool, so defining proposer-builder separation in Ethereum L1. This is a post from Vitalik in June of 2021, so this was already over a year before the merge. And the idea here is to keep the proposer set, which is kind of the decentralized set of validators that are selected through proof of stake to propose blocks for a given slot. And we want to keep them relatively unsophisticated. So we want it to be kind of accessible for people to run these validators at home on consumer-grade hardware without much sophistication. On the other hand, the builders are the people who are going to construct very valuable blocks. And what this means is they're capable of extracting a lot of MEV. This might require liquidity on different exchanges. It might require a lot of compute-intensive algorithms because there's a lot of different permutations of transaction ordering to try. And so these will be highly sophisticated actors. And the goal is to decouple these two roles to avoid the centralization pressure. And what I mean by centralization pressure is that if we don't kind of formally decouple these two roles, then there's very likely to be a world in which builders collude with large staking pools. Staking pools are incentivized to do this because they can kind of benefit from the builders who are really specialized at extracting MEV, so they get higher rewards. And the builders basically collude with them, and yeah, the reason that the collusion is able to be kind of credible is because the staking pools have reputation. And this reputation isn't something that would be accessible to the kind of everyday solo staker. And this kind of fits into the broader picture of the Vitalik's endgame post, which is the idea that block production is going to be highly specialized. We kind of have to accept that and firewall off the centralization from the decentralized validator set in some way. So that's what proposer-builder separation aims to do. Cool, so this is the first of the 5 designs I'll run through. And, oh, I should say the designs I like to categorize in terms of in protocol versus out of protocol. And what that means is if it's in protocol, then it's something we change in the consensus layer spec. It's part of like the honest behavior of being a validator in the Ethereum proof of stake network. Oops, sorry. Oh yeah, this is right. But if it's out of protocol, then it's kind of like this sidecar thing that the consensus layer isn't aware of, but maybe many of the validators are making use of. So MEV Boost is what exists today. This is the software that was written by Flashbots right after the merge. And the idea here is that there's a third party to facilitate the relationship between the builder and the proposer. And this third party is called the relay. They broker the trust between the two and conduct this auction to give the proposer the highest paying block from the builder. So builders are sending blocks to relays. relays forward the headers onto the proposers, and the proposers commit to a header without actually seeing the block. So the trust assumption from the builder to the relay is that the relay doesn't steal the builder's MEV. The proposer trusts the relay to serve them a valid header because they're signing some header to a block without actually seeing that that header corresponds to a valid list of transactions. So the trust is brokered there, and the way they relays interact with this is they run this sidecar software called MEV-Boost. So MEV-Boost kind of interacts with the consensus and execution layer clients and outsources the block production rights to this external block building infrastructure called the relay. And we see very massive adoption, like great product market fit for MEV-Boost. So 95% of Ethereum blocks are being built using this infrastructure. Immediately after the merge, it kind of skyrocketed from 50% all the way up to nearly every block being built through MEV-Boost. Cool. The next design I wanted to talk about is kind of the original 2-slot PBS design. And I would say for the past 2 years about, this has been kind of historically what people referred to as enshrined PBS or in-protocol PBS. And this is a post from Vitalik, and he presents this idea where you separate each slot into 2 blocks, basically, or 2 slots. So there's a beacon block. The beacon block contains some commitment from a builder to build a block, and the intermediate block, or the builder block, actually includes the set of transactions. So kind of logically, we're just splitting one execution layer, update, one set of transactions into 2 blocks, and it's this kind of commit reveal scheme that we use in MEV-Boost. It's just authenticated and kind of authorized through the protocol itself. And the way the attesting committee works is the attesters are the people who vote for different blocks, kind of saying, I think this is the head of the chain. And the attesting committee is split between the first block and the second block. And yeah, the partition happens. And the kind of TLDR of this is that it actually weakens the security properties of the consensus layer. And I won't go into the details of this now, but because of this, we thought of a new design, and this is pretty recent. This is a few weeks ago, and it's called the Payload Timeliness Committee. And this is another in-protocol solution. I should say the previous solution was also in-protocol. So these are changes to the consensus spec that facilitate the PBS implementation. So this is quite similar to Vitalik's 2-slot design. The difference here is that we have a consensus layer block similar to before. It contains a commitment to a builder bid. The builder bid just basically says, like, this is how much value I'm willing to pay to produce the block in your slot. And it also contains the header, which is like a commitment to the list of the transactions. So this is voted on with the attesting committee. This is all like as it happens today. The only difference is there's kind of a hole in the block where the execution payload will go. And the builder reveals the execution payload once they're confident that the builder block, or that the block that the proposer proposed will become on chain. And then we have this thing called the Payload Timeliness Committee, which actually makes these votes to the timeliness and the availability of the payload. So it's quite similar to before. The differences are mostly in the fork choice rule, but the important thing here is we think this has like better reorg properties in terms of securing the consensus layer. Cool. Now I wanted to present one other kind of out-of-protocol solution for PBS, and this is what we're calling optimistic relaying. And the difference here is that instead of kind of doing the in-protocol version where you go through EIP process, you modify the consensus spec, you update the client software, and then you perform a hard fork, we have this relay infrastructure that's already running. We already have 95% of blocks using the relays, so we can make the relay, optimistic. We can make the MEV-Boost relay ecosystem look slightly more like the enshrined PBS version by changing the code that actually runs on the relay and reducing the relay responsibilities. So this diagram shows the block submission flow for MEV-Boost. And you can see there's kind of a lot of tasks that the relay does and a lot of latency involved in those tasks. So the builder submits the block, the relay validates the block against the execution layer, and then publishes the block through the consensus layer client. So the idea is, how can we make this look more like ePBS? And when we say ePBS, that's enshrined or in-protocol PBS. Like, how can we take the infrastructure today and evolve it towards what we want it to look like in protocol? And the idea is we can just work from what we have today and remove some of the relay responsibilities. So optimistic v1, we say, okay, take the block validation out of the system. This saves some latency. It also makes the relays easier to run because now they don't have quite the operational and compute costs of simulating all these blocks very quickly. And the way we protect the proposers is we say, if a builder ends up submitting an invalid block that wins the auction, we'll have some builder collateral and we'll execute some out-of-protocol builder slashing. So we'll just say, okay, we're going to use the builder collateral to refund the proposer. No problem. Like, that's how we get around the removing the validity check from the submission. The second version of the optimistic relay is actually removing the block download from the fast path. So in the same way before, if the builder submits a block or doesn't end up sending the entire block contents to the relay, we say, okay, we're going to slash the builder. That's a penalty that will be able to use the collateral to refund the validator. And the end game version of optimistic relaying, and these diagrams are kind of wordy, so don't worry too much about the details, but the end game here is that the builder and the proposer actually interact through the P2P layer. So they gossip, the builder gossips the bid, the proposer gossips the signed bid, and the relay essentially just takes a snapshot of the mempool of the P2P layer at given timestamps and attests to the accuracy and the timeliness of different events. And really, if you kind of break it down, this is kind of what the payload timeliness committee does, but it's just being done by the relay itself, and the relay holds the collateral rather than the protocol. So this is kind of the molding of the relay responsibilities and the relay efficiency into something that should potentially be more compatible with Enshrined PBS. Okay, and the last PBS design, and again, bear with me, the remainder of the presentation is about drawing the connections between all of these. The last one I wanted to talk about is called Proposer Enforced Protocol Commitments. Again, this is an in-protocol implementation, and it represents a much more general framework for allowing proposers to commit to things in the protocol, and it's actively being worked on by Barnabé and Diego. And the idea is that you use block validity to enforce commitments. So proposers commit to doing something, and if they don't fulfill that commitment in the block that they produce, that block just won't be valid according to consensus rules. So the kind of cool thing about this general framework is that PBS can be enshrined through these protocol commitments. So you can have a proposer commit to a builder, and then if the proposer block doesn't include that builder's bid, then the block won't even be considered valid. So the difference here is we check the block validity, we use that to enforce the proposer commitments rather than the testing committee. Cool, so that was kind of a fire hose, but hopefully the next few slides will help connect the dots and draw the relationships between all these things. So on the top row, I have 2-slot PTC, Payload Timeliness Committee, and PEP-C. So those are the in-protocol versions of PBS. The bottom row is MEV-Boost and Optimistic Relay, which are the out-of-protocol versions. So PTC and 2-slot are really closely related, but basically we trade off what's called reorg resilience, or this is part of like the consensus stability, the consensus safety. We trade it off for builder safety. So we're saying, okay, we want, if we're choosing between these two, basically we decide how much we want to give the builder assurances versus how much we want the protocol to be, to have certain properties. To go from PTC to PEP-C, we use block validity instead of a committee. So this is kind of like who is doing the enforcement of these commitments and these checks, and PEP-C is doing the commitment at the block validity level. On the bottom, oh, I should say also, this is the heart diagram, so hopefully that will become clear in the next coming clicks. The bottom we have MEV-Boost, which evolves into the optimistic relay, and this is just relay evolution, and this is kind of already happening. Some relays are running optimistic, some relays have private closed source versions of their software, so this is kind of like already in progress of happening. And if we want to go from 2-slot to PEP-C, we can kind of view it as a more general version of doing PBS. So PEP-C doesn't put any constraints on what the exact mechanism you use to do the PBS. It just says have some way for the protocol to enforce commitments from the proposer. Now the left side of the heart is as MEV-Boost evolves into 2-slot or the Payload Timeliness Committee, we can kind of think of that as just enshrining the existing commit reveal architecture of MEV-Boost into the protocol. So that's like the enshrinement path for those two things is through that evolution. And then the right-hand side of the heart is evolving the optimistic relay into the payload timeliness committee. And this is essentially just, as I was saying before, replacing the relay responsibilities with the payload timeliness committee responsibilities. And the cherry on top is MEV, burn, and inclusion lists. So these are kind of two additional features that are hopefully going to be part of the protocol. I'll give a quick overview. MEV burn is the idea that we want to take MEV and instead of giving it to the proposer, we want to burn it. So kind of provably destroy it through the protocol. And inclusion list is a way we can say we want a certain set of transactions to be kind of force included into a slot. So this is a mechanism to enforce censorship resistance. And both MEV burn and inclusion lists depend on one of two slot payload timeliness committee or PEP-C. So that's why the three dotted arrows kind of come down and show the dependency between those two and one of the in-protocol solutions. And the key takeaway here is that you can't do either of those things with an out-of-protocol solution. So that's kind of one of the big cons of having this out-of-protocol software. Cool. So that was kind of like a mind map of the relationship between all of the 5 designs. I also thought it would be cool to kind of go through a few specific categories and compare the designs kind of directly versus each other. I clumped optimistic relaying and MEV-Boost into the first column. The second column is just payload timeliness committee or 2-slot. And the third column is PEP-C because PEP-C is kind of its own variant of a design space. So the first axis, I guess we can evaluate them on, is the time to ship / the protocol diff. So the MEV-Boost relay is already running. Optimistic relay roadmap is kind of in progress. This is something we can do now. Oh, I should say the 3 colors, green, yellow, red. Green is kind of the good outcome, yellow is the medium outcome, and red is the bad outcome. So that's why I call it the traffic light matrix. So yeah, MEV-Boost is already running. It's kind of already in existence today. PTC we think of as a relatively minor diff. Like it's, there's a big change to the consensus layer, but it's not so dramatic that it requires a whole consensus layer rehaul essentially. And PEP-C is really dramatic insofar as it allows proposers to commit to kind of arbitrary things. There's a lot of design considerations around what those commitments look like, how those commitments are like encoded on chain, et cetera, et cetera. And you can kind of think of PEP-C as almost like an enshrined eigenlayer. So there's all sorts of kind of tail risk, at least associated with kind of opening up the doors and letting people to commit to arbitrary things as proposers. The next axis I wanted to present was decentralization. So MEV-Boost is kind of by definition centralized. There's only about 8 relays that handle all the blocks, and that's kind of part of the expectation is that there's only going to be a few relays and a few builders that connect with those relays. PTC is extremely decentralized in that it shouldn't change the validating role at all. Basically, being a validator changes, like the role that the validator plays in the ecosystem has very minor differences. So in that regard, it has the same decentralization properties that we have today from the validator set. And PEP-C I put as yellow because there's a world in which PEP-C involves many more commitments. Those commitments might require higher compute, higher bandwidth, and as a result, there might be kind of a competitive advantage of joining a staking pool that is able to run more infrastructure in the same argument, or the same vein of arguments that present eigenlayer as a potential centralization vector in the system. Bypassability. So this is the idea that there's kind of some way to get around the mechanism that we design and for builders to collude with proposers. Typically, the process is builders colluding with proposers to avoid any kind of tax imposed by the system or any inefficiency imposed by the system. So MEV-Boost, I say, is not really bypass, or it's green in that regard because the builders already have close relationships with the relays. The relays kind of do the builder's job of connecting to the validators. So there's not really any incentive for builders as currently existing today to go around the relay, because the relay is essentially like subsidizing the builder's job for them. For the PTC, I put it as red because there's kind of no way to enforce that the proposer actually uses the mechanism that we put into the protocol. The relay infrastructure would probably still exist. They could just outsource their block production to the relay rather than using the P2P layer to get their blocks. PEP-C I put as yellow because there's a world in which the enforcement of the commitments and the set of commitments that a proposer can make makes it harder for the builder to circumvent the protocol. And in that regard, it might be better in terms of bypassability. In terms of censorship resistance, I put MEV-Boost as red because there's basically no way to do inclusionless. There's no way to force through transactions in today's relay ecosystem. But both PTC and PEP-C are like very, very like out of the box compatible with inclusionless, and that's the censorship resistant design that we're looking forward to in the future. Yeah, the next one is flexibility. So in terms of what you can do with the relays, I put it as yellow because it seems like there's a relatively large amount of things you can do, but since it's out of protocol, you can't enforce things like MEV-Burn, you can't enforce things like inclusionless. So the relays can evolve, and it's kind of a latency game where the relays are maybe competing with each other, maybe updating their software in a closed source way, but in the same vein, they're not able to do anything through the protocol because it's this out of protocol software. The PTC flexibility is red because really we're just saying we're going to take an opinionated stance on what we're going to include in the protocol. And it's going to be this commit reveal scheme, very similar to MEV-Boost, and we're just going to kind of make it happen in the short to medium term. PEP-C, on the other hand, is maximally flexible because you're saying these proposers can commit to any arbitrary thing, essentially, and we want to give them the flexibility to decide if they commit or if they don't. And those commitments are going to be enforced at the protocol layer. Okay, two more. Unknown unknowns. From the relay perspective, I don't really think there's any unknown unknowns because we're already kind of in this regime. For PTC, we think the spec change would be relatively minimal and something that we can envision kind of in today's world. PEP-C I put as red because I keep calling back to the eigenlayer thing, but we're just really not sure what people will commit to. We're really not sure how those enforcements will go. It has kind of increased slashing potential. There's just a lot less we know about the potential tail risk events that this type of system enables. Lastly, MEV-Burn compatibility. This is something that I mentioned in the heart diagram, but the idea here is that in order to do MEV-Burn, you need one of the enshrined versions. So you can't use the relays as existing today. You need to do either PTC or PEP-C. And to wrap up, I thought just kind of like a TLDR vibe check on each of the three. I would say that the relay approach is kind of move fast and break things. This is like the Silicon Valley style of we're all going to play this game, we're going to compete, and may the best relay win. PTC is more like, let's get something in the protocol. Like, the relays aren't very sustainable. There's talks about relay funding issues and sustainability around the current existing framework. Like, it doesn't feel like we're in an equilibrium in any way. So if we decide to go ahead with PTC, we could get something in protocol in the next months, hopefully months. And that's the goal of the middle column. The PEP-C version this is kind of an aesthetic thing. It feels correct in terms of protocol being maximally flexible and maximally idealistic in some way of letting the proposers to commit to things. But it could be opening Pandora's box. So we're unsure what we're getting at. There's kind of these tail risk events that I mentioned earlier, but it could be the right approach in the long run. So yeah, thank you very much, and that's all.
Well, since you did very well catching up on time, let's take one question. Well, looks like everyone is an expert in the future of Ethereum. All right, well, next up we have Vitalik giving us a talk about zooming into the builder role, what more builder can do, and the future state of PBS, what could it be? But I had to ask, since Danning's memes were cut, so would you please give us a PBS meme to make it up?
Real-time meme challenge. This is difficult. I do not claim guaranteed success. But okay. So to get right into things, yo dog, what's up? Who here thinks it's the ceiling? Who here thinks it's the ceiling that's up? Who thinks it's the sky? Who thinks it's like a cryptocurrency? Okay, well, let's just talk about aggregation. Okay, so the aggregation, basically the core idea here is you have n things, and you're trying to take n things and turn them into one big thing, which is less than n times as hard to verify, right? So, sorry, it's hard to speak and be yelled at for my poor microphone performance at the same time, but okay, so, no. One more reprimand and I'm throwing this out and you'll have to listen to me speaking quietly. Okay, so what is aggregation, right? It's converting n things and turning them into one thing which is less than n times as hard to verify. Now, why do we want to do this? Well, because we care about scalability. We don't want to pay like $80 a transaction or even $0.80 a transaction. And we want to like cut down on-chain verification costs, right? There are a lot of different use cases of aggregation, and so in the Ethereum consensus layer, for example, we have BLS signature aggregation, and there's many kinds of aggregation that we'll have in the future. So some specific areas where we are thinking about we might have aggregation. ERC-4337, right? So this is this off-chain protocol by which users can send in user operations that have validity conditions that are different from the validity conditions of a regular Ethereum transaction. You might have a smart contract wallet validation. It could be a multisig, could be some custom Winternitz Lamport signature, could be whatever. And those conditions get verified, and it's this kind of off-chain ecosystem for like basically making these custom smart contract wallets work. But these user operations all have to be wrapped up in a transaction, right? Because Ethereum, the base protocol, only accepts transactions. Now, before ERC-4337, in the dark old days, we would have protocols but which every single user operation would get wrapped up in a separate transaction, right? So I send a user operation, and then whoever I send it to would wrap that user operation in exactly one transaction, and then that transaction would go on chain. Every transaction would have a 21,000 gas overhead, so it's not very efficient. It also was not a very open protocol. In ERC-4337, we have a custom mempool where users send user operations into the mempool, and then bundlers exist in that mempool. Bundlers grab up all the user operations they can see in that block, and then they publish that on chain, right? So this is a form of aggregation, right? Because the object that went in, the cost of verifying that object by itself would be n plus 21,000, right? And whatever the cost of the user operation is, 21,000 for the wrapper. But if you take, like, let's say k of these and you put them together, then the cost is just going to be n times k, because you still have to process all the user operations. Actually, sometimes a bit less than n times k, because you can benefit from like warm, cold storage reading gas stuff. And then plus 21,000 only once. Right? So there's some pretty significant gas savings from taking user operations and putting them all in the same transaction. This is a type of aggregation, and you know, this is something that's actually being done even in the builder ecosystem today. BLS aggregation. So this is a thing that actually has been recently kind of in proof of concept mode. It's been added to ERC-4337. There's a piece of code called BLS Wallet that actually does this. But the basic idea is we, instead of using ECDSA signatures, we use BLS signatures. So Why do we want to do this? This is especially valuable in a rollup, right? Because in a rollup, the computation is done off-chain, the data is still done on-chain, right? And so the computation becomes vastly cheaper, the data does not become cheaper at all. And ECDSA signatures on their own are 65 times n bytes. Okay, fine, I'm using n to refer to the number of objects now. And then with a BLS signature, if you use G1 points for the signature, then the signature can be 48 bytes for an arbitrarily large number of operations, right? And so if you have like 100 of these per block, then for each one of them, the amortized cost will go down from 65 bytes per operation to like half a byte per operation. On the computation side, it actually does get a bit more expensive because instead of doing fairly easy elliptic curve stuff involving adds and multiplies, like I think at ECDSA, recover as like something like 3 multiplies or somewhere in that range. And instead you do a pairing, which is like pretty heavy duty stuff. But as I said, on rollups, computation is cheap, data is expensive, we're saving on data and it's great, right? But how do we actually like do BLS aggregation, right? Because the Ethereum protocol does not currently have an execution layer BLS capability, right? And so if you imagine n different users, each of those users is going to send their own BLS user operation, and their own individual BLS signature that they created separately is going to be 48 bytes long, right? Then what we want is we want the thing that goes on chain to be 48 bytes. We don't want it to be 48 times n, right? And so there needs to be some kind of actor that is grabbing up all of these user operations, going into the user operations, grabbing out the BLS signature, adding them all together. See, that's, some kind of, mechanism in the middle. It's a big plus. And create one aggregate signature, 48 bytes, and that aggregate signature can be verified against the aggregate public key, which is created by taking all of the public keys of the individual users and also adding those together, right? So this requires 2 types of weird stuff, right? The first type of weird stuff is the off-chain adder. The second type of weird stuff is the mechanism for verifying these signatures, where basically instead of doing what Ethereum protocol does today, where you verify each of the signatures in sequence, the protocol or whatever super protocol we use somehow would have to take these signatures, then when you walk through each one of the user operations, don't immediately just like verify pass fail it, but actually record the BLS signature. Like, first of all, you'd verify it locally, make sure it verifies individually. If it doesn't, you throw it out, right? But then record it. And then if you're doing this inside the block, you just record it, right? Then keep walking through all of the user operations, add up all of these signatures, and then at the end, do the one check at the end, right? Because adding 2 signatures is like very cheap. It's like hundreds of times cheaper than, even an ECDSA operation, right? So this requires like a different workflow where it's like walk through the operations, then do a check, and then execute everything. Now, ERC-4337 actually already now has an extension to do this, but this is, again, a type of thing that I call aggregation. Snark aggregation. So this is the future, right? So BLS is like very specific. What if I told you that in the future, we're going to be able to take existing ECDSA signatures, potentially even signatures that are made with existing tools, and replace them all with a snark that just says, here is a signature, and here is a proof that, or rather, here is a proof that there exist valid signatures for all of these things, right? So this way, you could replace an unlimited number of ECDSA signatures with like one snark, and you could even apply this technique to other mechanisms, right? So who here has used a privacy protocol? Privacy protocols are good, right? Now, privacy protocols cost a lot of gas. This is one of the bigger challenges hampering their broader adoption, right? Because inside of one of these privacy protocols, every transaction requires you to have a snark that goes on-chain. Now, the snark, 500,000 gas, 20 times more expensive than a regular transaction. At current gas prices, that's going to be, I guess, about 20 gwei multiplied by 500,000 gas. So that's 10 million gwei, which is 0.01 ETH multiplied by 1900, $19 transaction fee. Who here is willing to pay an extra $19 to make your coffee more privacy preserving? I'll do it as a gimmick, you know. Yeah, so, this is like not good, right? But what we can do is, well, we can use a snark to prove the validity of all the snarks, right? And so even if you have 100 different users using privacy protocols within a block, you just take their proofs, you prove them all together, and you have one proof of the proofs. And now you have like all of the proofs of all the private stuff within a single block, right? Now, what does this require? It requires aggregation, right? You need to have some actor in the middle that it basically takes all of these objects and replaces them with an object that proves the existence of all of those objects. So this is all really nice. This all increases scalability, and this is all really good, right? So what does this all depend on? It requires a builder ecosystem. By the way, who here remembers the cartoon character that this meme is based on? Bob the Builder! Yay. I don't know, see, Bob the Builder needs more love, you know? Like, well, we have like Barbie these days, and we have like, what else? Yeah, there's all, all the Barbie songs, and like, we need a Bob the Builder movie. Like, can we like do like an on-chain Gitcoin bounty for a Bob the Builder movie, and then like use Zoopoll to vote on the best one? Real-world crypto applications, please. So, yeah, we need builders, right? Builders are, the heroes of Ethereum block production, right? So, okay, fine. I'll see. I wonder if this style of mic holding is better. So, the block building ecosystem is actually really big, right? Like, we all kind of know that, Bob the Builder is an abstraction, and in reality, there's like dozens of construction workers, and then there is the people driving the trucks bringing resources over to the workers, and then there's the janitor, and then there's a whole bunch of other pieces of infrastructure, and there's like really big teams that make up a construction company, right? So block building ecosystem looks pretty similar to that too, right? So basically, you have a bunch of searchers, and searchers all have their own different strategies for creating bundles that contain different types of transactions, and then they all go together to a block builder, right? And then the block builder creates a block and then publishes it today to relays, in the future directly to validators. And like, this is roughly how things work right now, right? And so one natural question to ask is, well, if we have a builder, if we have this kind of ecosystem, then like, who's gonna do the Snark aggregation or the BLS aggregation or ERC-4337 aggregation, all of these things? The most natural guess for the long term is like, we'll have specialized searchers, right? So we'll have like a searcher that speaks the 4337 protocol, and then we'll have a searcher that does BLS. We might have a searcher that does Snark aggregation. They might even end up talking to each other. There might even be some multi-layer ecosystem where first you do the aggregating for the 4337 or for the BLS and the Snarks, and then you put that together into a bigger 4337 aggregate, and that goes into a block along with non-4337 stuff. But like, I expect it will move towards something specialized like that, but I also expect, in the shorter term, there's definitely going to be builders that just like do this stuff directly, right? And there's like, I expect going to be a growing array of these aggregation sub-protocols that gather these kinds of aggregate messages. So challenges in these ecosystems, right? So we want an open mempool, meaning a protocol that anyone can participate in, right? Not, open in the sense of like anyone can, see your stuff and use advanced machine learning algorithms to like figure out when, okay, what should I even say here? Okay, figure stuff out about you that you don't want to figure stuff out about yourself. Right, we want a protocol that anyone can participate in for both users and for builders and searchers, right? We want it to be open for users to send in their user operations. We want it to be open for searchers to participate, and we want it to be maximally open for people to bring in new aggregation protocols. Now, that does require them to kind of accept permission from one builder or one searcher, but it should not require like global permission from the ecosystem. So that's a goal. And we want to try to avoid centralization, and if centralization happens, we want to avoid censorship. Now, one of the challenges is that economics is weird, right? So in particular, the issue here is that a lot of these types of aggregation that I talk about, they have a high fixed cost and they have a low marginal cost. So what do I mean? What I mean is that if you think about like Snark aggregation, right? If you put a Snark on chain, the cost of a Snark is about 500,000 gas. Now, that Snark can represent lots of things. If that Snark represents one thing, it's 500,000 gas. If the Snark represents 100 things, it's also 500,000 gas, right? It's fixed cost. Now, the other part is that it has a low marginal cost. The marginal cost does exist, right? Because if you're a prover, then you have to like run more proving cycles, right? Like if you have to prove 5 more things, the cost of doing the proof is 5 times bigger. Now, this is, this is a cost, but generally these off-chain costs are, I believe, already lower than on-chain costs, and I expect these costs to continue to trend lower as we have more specialized proving techniques, as we have more specialized hardware and all of these things, and I expect gas costs to be much harder to reduce, right? The amount of gas on the Ethereum L1 has increased by a factor of 5 over the course of 7 years, but the efficiency of provers has increased by a factor of like thousands over the last like maybe 4 years, right? So when you have things that are high fixed cost and low marginal cost, like economics get annoying, right? It's like public transit systems, right? Like when you have a fixed cost to run a bus, and it's like even like sometimes it might even happen that like the system can't pay for itself even if it makes total sense for the system to run, because the system has to charge one price, and it turns out that if it charges a high price, it excludes too many people, and if it charges a low price, it doesn't capture enough of the value, right? And you're stuck, right? And so, you have like weird things like this, and unfortunately, these kinds of like fixed cost, low marginal cost economics do tend towards centralization, and sometimes centralization may be an argument for saying like we want to give up on this whole higher layer idea and we want to just like protocolize it, but the problem is like this stuff is so early that it doesn't make sense to protocolize it, and like how do we navigate that trade-off in the meantime, right, is basically the challenge. Another really fun use case, proof aggregation for ZK rollups. So let's say you have a rollup, and actually, who here is part of a rollup team? Who here is part of a rollup team different from the rollup team that the person over there is part of? Who here is part of the rollup team that's different from both of these rollup teams? Okay, I can see, I see a few raised hands. Yeah, so like we have at least 3 rollup teams here, right? So the problem is each of these rollups are going to have to submit proofs on chain, and submitting a proof on chain is itself something that has a high cost, right? So if you look at a ZK rollup, it has to submit a ZK Snark on chain, 500,000 gas. If you're a Stark, then it's like closer to 5 million gas, and this is expensive. What if we had multiple rollups, and these multiple rollups could cooperate and basically replace all of their individual proofs with a proof of the proofs, right? So you just have one proof that proves that all of the proofs that they want to submit are actually correct, right? So this is kind of what the diagram says, right? You have like 3 different rollups, and they make 3 proofs of 3 state transition functions, and then you just make this kind of multi-proof, which just submits as a public input the claims that the 3 proofs that are coming in are making, and then it sends it off to a batch handler, and then the batch handler basically just tells the rollup, so like, hey, yo dog, I have a proof of this, I have a proof of this, I have a proof of this, and the rollups accept it, right? So this is a kind of layer 2 middleware protocol that could actually be really useful, and it could be like a lighter way to achieve the goals of reducing costs for layer 2s that's lighter than like layer 3s and some of those similar ideas. And like it could be, it's more minimalistic. It can be made to be more permissionless. I mean, I believe like within the Starkware ecosystem, there's a version of this running already, right? But it would be good to have this as an potentially protocol that's kind of shared between an even larger parts of the Ethereum layer 2 ecosystem. And this is, again, a type of, you're supposed to say the word? Yay! Okay. Perfect. So the goal of this is the proof singularity, right? So basically, my dream is we have a block, and that block contains a proof. And the proof is a proof of proofs. And each of these proofs is itself a proof of proofs. And each of those proofs is another proof. So imagine the proofs at the end could be just signatures. Then some of them are signatures, some of them are privacy protocols. Then the proofs in the middle are going to be aggregation proofs. Then the proofs on top of those are going to be layer 2 proofs. And then with the layer 2 proofs, you have a merged protocol, and then it all gets into one proof. And then maybe over and above that, you have a layer, you have like one big master proof to prove them all, and that one big master proof is just going to be a ZK EVM, right? So this way, we might actually be able to get to the point where we literally have like, blocks coming in once every minute that prove everything, and everything in the ecosystem is going to be super efficient and super optimized, right? So this is, what I hope for the ecosystem, and it would be amazing to see. And, builders are going to be a very important part of making this all happen. So this concludes my presentation. Thank you all for listening. Yeah.
Thank you. Thank you for the meme. And we have time for one question, but I could
Sure.
also ask our next speaker to ask the question, if you have one.
Extremely exciting talk about the future of block building. My question would be, these new protocols, how should implementers be thinking about the complexity of the implementations and about shipping them in a timely manner that can fit, that can make sure that we don't end up in a dystopian, centralized future?
How do we think about implementing these protocols? I think just standardization is important, and like cross-ecosystem collaboration, I think, is important. So I feel like we've been having a lot of that between layer 2s, which is good. I would love to see more of that happen between wallets. I would love to see more of that happen between privacy protocols. Like, I think we just need to, identify some of these kind of verticals. And in some, I think it might even be the case that like per vertical, we might need like an intentional effort to try to like really, figure out what actually makes sense to do, and to like try to sort of front run some of the more centralized efforts at solving the same problem.
Thank you. So next we have Georgios, who will be giving us a grand overview of our next chapter, the L2 PBS, which is a brand new frontier. There you go.
So thank you all for coming and for not coming. It has been a very exhausting week and also a week where we've made great progress on a lot of the concrete parts about where the industry is going. In this talk, I would like to give a few questions for the audience to think about, given that now we're entering the layer 2 part of the day. And layer 2 part of the layer 2 part of the day, many people here that you're going to hear next are working on it full time. I'm no longer spending as much time on this, but I'm going to try to offer a zoomed out view and some questions for the audience to think as people do their talks and for hopefully to reach some deeper insights. My name is Georgios, I'm the CTO of Paradigm. So we'll start with what is an L2. I see John in the audience and Togrul in the audience as well. We'll see how that will go. We'll talk about shortly what the differentiators between layer 2s can be and what are net new exciting features that can be introduced. Then I will pose some interesting hypotheticals for shared sequencers, and then I will have one slide for prover, proposer, builder separation, or whatever the canonical name ends up, which our next speaker will also tell us about. So we will talk about layer 2 just from the context of not bridging, because there's been many debates and I have no interest in engaging in any of them. The main thing about the layer 2s that we care about right now is that you have some off-chain state in another place, and then that off-chain state gets posted to layer 1, which is called the data availability layer, and that ensures that anybody that wants to recreate the state of the layer 2, they can go and look at the layer 1, they can very easily derive it. Typically, there is a deterministic derivation function, different in each system, which allows you to do that. Beyond that, a layer 2 is an L1. It's a chain. It has a database, has a runtime, it has an RPC, it has a peer-to-peer layer, it has a bunch of cryptography maybe. It's a standard distributed system. We know how to optimize them. These systems, they bottleneck on I/O and on state growth. If the thing that matters to you is decentralization and the ability for an individual to verify, these are the two things that matter. I/O bottlenecks how fast you can sync a chain. State growth bottlenecks how big your chain can be. And if you want to scale Ethereum or anything else, how you do it is by launching many of these layer 2s. And the rollup-centric roadmap is all about that. Now, some problems for people to think about are, one, how are we going to do composability across the same flavor of a layer 2? So if I have two OP stack chains and they want to talk to each other, how are they going to communicate without necessarily going through the layer 1? If I have OP stack and Arbitrum or ZK stack or Stark stack or, I don't know, is there some extra difficulty in making these two communicate? Are these systems EVM compatible or whatever runtime they need to support, or are they just looking like it on the outside and things on the inside look a lot different? And the natural follow-up question to that is, what does change in the internals and how does that impact the externals? How did an implementation detail make its way to the interface? And one example could be that people maybe have optimized for MEV extraction on Geth because they understand, okay, these are the bottlenecks. But maybe, for example, on the Polygon ZK EVM, maybe it's different. I don't know. Now let's talk a bit about what are the unique things that you can get from a layer 2. First and foremost, from the sidechains paper from 2015 by Blockstream, experimentation. Experimentation, experimentation. We can try new things without breaking the base layer. And then I will pose some bullets with some questions about them. So when we have faster block times or soft confirmations, what does that mean about the MEV extracted in these blocks? Does it really mean that more frequent blocks means less or more MEV? What happens outside of that system, and how does the synchronization time between these two systems change, which directly, of course, affects the MEV extracted? The proposer set in rollups can be less decentralized without losing safety, with some cost to liveness, but not total degradation. Naturally, having a distributed system means it's higher SLA, which is good. If the system allows a custom transaction pool, it also allows for custom ordering. FCFS, we'll hear Patrick McCory talk about that in a bit. I also don't know, but all of these are levers that one can pull depending on the MEV profile that they want the layer 2 to have. Or if you don't have a transaction pool and people just hammer the sequencer, what are you going to do? Proof of work? Are you going to add identity? How are you going to prevent this spam that happens on the wire that comes from the client to the server? And the obvious thing, which is not, I'm realizing the last bullet is off topic, but I'll roll with it, is that we have a bundled role. A sequencer is both a proposer and a builder, and naturally, you want to keep the sequencer lean to allow for, in the future, as many of them to be around. So the same thesis for PBS on layer 1 applies to L2, separation of concerns, how you build optimized systems. I will not talk about decentralized sequencing. I think it's kind of, again, an implementation detail. Any centralized system, you can replace it with a BFT version of it, put it on Tendermint, put it on some other consensus protocol, and that gives you redundancy. And some A's or B's here are, do you enshrine the shared sequencer in your system? For example, the OP stacks superchain, is it the thing? And is it something that gets you better performance than having something like an espresso sequencer on top of it? I would think that like anytime that you have a core protocol operation and you leave the metal, that means that it becomes more expensive. One or many shared sequencers, do you aggregate them? How does that go? We saw the fractal aggregation of proofs that Vitalik showed earlier. The aggregation theory can play in any layer. L2 specific or close flavor, again, same thing. And the thing I want to drive home, shared sequencers are not magic. You know, they don't actually solve all the world's problems. They give you atomic, top of block inclusion. The most classic example being the based rollup. What is the room for differentiation? I also don't know, but I know that like nobody else either knows. So what do? And these are two other questions around the bridge and the atomic success, which I still have only seen Strawman answers to, and I think we should do better. One concrete proposal on how to get to cross-chain composability, and I realize this is kind of dense and low context, so I'm happy to expand later, but we don't have enough time, is that maybe you can have a shared sequencer that indeed only guarantees inclusion without execution, but then you can have a bunch of builders where they cross-chain simulate, and Vitalik kind of alluded to that, that you can cross-chain simulate the block. The builders are indeed going to be running nodes and simulation engines for every chain that they support, and the builder is going to land a bundle that's going to be landing transactions for rollup 1, 2, and 3 together. And the insight here is that we take the MEV builder role and we just bundle more functionality on it, like make it heavier. And basically, the shared sequencer is, funnily enough, the MEV builder, poetic. This is my final slide. I want to talk a bit about this because it's a topic I deeply care about on ZK proofs and how the market will evolve. The prover right now is again run colo with the sequencer. And the sequencer, as we said, is also a builder. We really need to unbundle these two. And there's many, many ways that we could do it. My favorite work was a paper by a good friend of mine, Akis Katis, that was called Proof of Necessary Work, and described a way where you can introduce nonce grinding, a la proof of work, in the snark generation process. And that let you have a leaderless system, or rather, a system where the leader is not known ahead of time for proof generation, for proof proposal. Naturally, anything that is like proof of work-esque, it has a lot of wasted effort. But maybe it's like very egalitarian. So maybe like the next step from that is, should we do a consensus protocol for the leader election? You know, let's elect the proposer. Let's agree, let's put up some stake or something. We elect the leader does it. Standard techniques that we have seen used in consensus protocols are going to be used for prover selection. And the other thing that I don't think I've seen anywhere so far and I just added it as a strawman, and I realized that it's probably broken and there's probably things to do, but I wanted to say it, is that as a ZK proof is generated, you can actually observe that parts of the proof are generated in a pipelined sense. The most trivial example, I have a block with 10 transactions. Transaction 1 is executed. It generates some witness data. That witness data is supposed to get fed to a snark. But while it's getting executed, and it's getting proven, another transaction is also getting executed and getting proven. And another, and another, and another. Do the provers need to be the same thing? Can there not be a market for proof aggregation? The things that Vitalik was talking about. Can there not be something where proof 1 goes to John, proof 2 goes to Nick, proof 3 goes to Josh, you know, and you can keep doing that. It seems like we can come up with collaborative proof generation protocols that abuse this pipelined structure of like proof generation. I don't know how that will look like, but if somebody is interested in talking to me about it, please find me after the talk. And the final question is, how do you distribute the fees? Again, the perennial question in the MEV supply chain or compositional game theory is the new term I hear. How do you put the fees? Where does value accrue? You know, I also don't know, but it's something interesting to think about. I have 3 minutes, and it would be good if we can do some questions, perhaps. Thank you.
Anyone has any questions from the audience? Oh, I see.
Can you elaborate a bit more on how cross-chain or cross-L2 interaction can be facilitated by this shared sequencer model for those of us who are unfamiliar with the literature?
Yeah, of course. Can we get the slides back up? So the shared sequencer is an entity that is ordering things and doesn't really know how to execute them. Or if it were to know how to execute them, it would need to have execution nodes for every chain it is ordering for, because otherwise it would be ordering invalid things. And ordering invalid things might be okay if your chain can support no ops. You know, you just say anything that's invalid, just like skip it. This has junk, this leaves junk on the chain, but maybe it's fine. So perhaps what to do is that you have the shared sequencer, which is basically a privileged entity for submitting data to the chain. And how does the data get ordered to get into that privileged entity? You could have builder 1 and builder 2, but basically, or builder 1 for simplicity, who is running nodes for chain 1 and chain 2. And what they will do is that they will publish a bundle or a full block template to the layer 1, where the first transactions in that bundle are going to be all the rollup A transactions, and the next transaction in that bundle are going to be all the rollup B transactions. And because that person is a builder and has run the simulations on every chain, they can guarantee that by being at top of the block, they can guarantee that the transactions are going to be valid. So by doing that, you can hack your way into shared sequencing in a very clean way. I realize this is a bit dense, and I don't know if it answered the question sufficiently.
Yeah, it makes sense. This also goes back to what Vitalik says about aggregation. I'm just wondering how this helps cross-chain interaction.
Oh, well, I don't think that you can do callbacks. You know, callbacks, I don't know who has said that, like, you can do, you know, contract A calls contract B and then it calls back. It's a bit unclear because people are doing, like, right now, the way the rollups work is that they submit one transaction, one big bundle per block. If we could interleave bundles, if we could say top of block part A is like bundle for rollup A, and then rollup B, and then rollup A again, maybe we could do something where I can call chain A, and then chain B, chain A, and then it calls me back. The main things that we support in this design are cross-chain message passing, and maybe cross-chain bridging. I'm seeing a timeout, so I don't know if I have time for more. Sure. I think the person on the back was first.
The person in the back.
Yeah, nice talk. So I just have a follow-up question regarding the shared sequencing and also PBS for the L2. Like if we have sort of these shared sequencer, actually two questions. The first one, if it's really like sort of shared sequencer, do you think it will overwhelm that machine? I mean, if the sequencer used for multiple rollups? Yeah, like that's the first question. Second question, like
Maybe let's do one. Let's keep it at one.
Oh, sorry.
So is the question that the shared sequencer can be very heavy? I'm not sure I understood that. Like if that is the case, the way that you do shared sequencers, you basically need to make them like cross-chain DA aggregators before you land the chain, before you land the bundle to layer 1. But you do not want them to be running the execution of these chains. So by doing that, you can keep the sequencer as a light DA consensus protocol, effectively, which is what Espresso is, for example. And then you land your data to the real DA protocol.
Sorry, just a quick one. But in that case, like for example, if we really pass the message across the rollups, right, via the sequencing, but do we need to wait for the confirmation from one rollup before like we really execute another message dependent on the...
For sure.
Yeah.
Yeah, obviously, of course. Any transaction needs confirmations. 0 conf, 1 conf is insecure.
I see. So in that case, it's like sequencing plus execution and DA, right? Thank you.
Thank you so much. The next speaker is Togrul, who I don't think we've met before, and is going to talk to us about prover, proposer, builder, separation, or whatever you're going to call it.
Hello, everyone. Before I begin, I wanted to thank Vitalik and Georges for warming up the crowd. It's really nice from them. So, strangely enough, I'm not going to be talking about rollup definitions today. I'm talking about something else. So, my name is Togrul. I mostly shitpost on Twitter and sometimes pretend to do research at Scroll. And today we're going to be talking about PBSifying rollups, prover sequencer separation. So you've probably heard about zero-knowledge rollups, or for the Starkware folk in the crowd, so they understand, validity rollups. So you have sequencers and you have provers in the system, and sequencers perform the role of ordering, and then the provers perform the role of computing the validity proofs for the given order. And the way they work is the sequencer submits the batch is also propagated to the prover submits the validity proof, and voila, you have the finalized state on the layer 1. And so why should we decentralize? Because in L2s and rollups specifically, you don't really care about correctness that much because it's already enforced by the L1 bridge. So why would you decentralize? It makes more sense to just be centralized and be efficient. So there are multiple reasons why you would do that. So one, resilience. Let's say if your sequencer fails, what happens then? If there's no backup, or in many cases, there's no decentralization, then you're stuck and waiting for that sequencer to come back. Another reason why you would need to decentralize is real-time censorship resistance. So while L1 bridges guarantee long-term censorship resistance, for a lot of applications, that's not enough. For example, let's say if your app depends on Oracle updates and you're waiting for a long time and the sequencer is censoring you, you're basically screwed in case there's a lot of volatility. There's also throughput, which is an interesting one because it might seem logical that a centralized system is more efficient because you have less overhead, But in case of zero-knowledge rollups, because you can parallelize proving, you can actually increase the throughput by decentralizing the provers. And that's what I'm going to talk about later. And so what are the requirements for a decentralized rollup? So first, we need to minimize the overhead. It doesn't really make sense to add drastic overhead and make it really clunky and very complex. It needs to have fast pre-confirmations, because if your rollup has the same finality time as the L1, then especially in L1s that are not very fast, it's not a great UX. It has to be provable on chain. So what I mean by that, if you use some sort of a mechanism that agrees on off-chain ordering, you need to be able to prove to the bridge later that the ordering was agreed upon via a certain mechanism. So if there's some non-determinism in the way you agree on the ordering, it might be possible that basically the bridge might diverge. And so we need a way where you can prove it on chain that it actually happened. And finally, which is the reason why I'm giving this talk, is balanced incentive distribution. So and I'll explain why it is important. So why is unbalanced incentive distribution an issue? So since sequencers in the protocol are in charge of the ordering, they get to keep all the MEV profits. And it's likely that in rollups, the MEV profits are going to be the large share of the total protocol revenue. And if that's the case, then what's the incentive for protocol participants to become a prover? Because if all the profits are collected by the sequencer, then I would rather become a sequencer. But in case of ZK rollups, we actually need provers. Sequencers, we need a few, but we don't need that many. And so we need to incentivize provers. And that's where PBS, or proposal builder separation, comes in. So in a proposer builder separation, proposer is a thought leader responsible for proposing and propagating blocks to the network. And the builder is a set, there are a number of builders competing with one another in an auction to have their candidate blocks selected by the proposer to propose to the network. And basically the whole point of PBS is that it outsources the computationally intensive task of creating a optimal value extracting ordering to some specialized nodes that can actually do that efficiently and well. But in our case, we don't have proposers and we don't have builders, so what should we do? So we have prover sequencer separation. So on top of doing what PBS does, PSS also ensures that protocol-generated revenue is relatively fairly distributed with the provers, because as I described before, the sequencers by default get to keep all the MEV. And as with PBS, there are two types of PSS. There is enshrined PSS and external PSS. And the role of the sequencers is essentially to emulate the role of the builders on the L1, and the role of the provers is to emulate the role of the proposers in PBS. And so these are the steps in PSS, in enshrined PSS. So the sequencer bids in an auction, the prover selects the highest bidding thing, the winning bidder reveals the contents of the block, the sequencers reach consensus, blah, 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 that's it, we have the ordering. Well, the benefit of this is that it doesn't have a lot of overhead. Because we don't need a lot of sequencers, the consensus should be relatively efficient, and therefore it should be relatively easy to run. But the downside is that it actually creates sort of a PBS inside PBS, because I might be a sequencer, I might be elected as a sequencer, but I'm not really good at building, so I'm incentivized to outsource it to someone else. So it's possible that you can create a market where sequencers outsource it to somebody else, which creates this loop in which the value is leaked to some external parties because the sequencers just don't want to do it internally. Oh, now it's working. And the second type of PSS is external PSS. And it follows a similar pattern. So sequencers bid in an auction, provers select the highest paying bid, the winning bid is revealed, blah, 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 blah. But in this case, provers reach the consensus. And with external PSS, sequencers don't actually exist in the protocol. The protocol doesn't know about them. There are some external parties that provers deal with, and they can even avoid them and build the blocks themselves, but obviously it's unlikely to happen because provers are not good at building blocks and extracting value, so they're likely to outsource it. And the advantage of this scheme is that it doesn't really require two distinct roles in the protocol, and therefore it makes the protocol simpler and the fee distribution much more simpler, so you don't have to deal with like two different models, potentially two different staking models, etc., etc. But it also has a massive downside. It has quite a big overhead because the idea is that you should have a lot of provers, and if you run the consensus amongst the provers, it's gonna cost quite a lot in terms of networking, etc., etc. There are possibilities where you can, for example, use committees and do random sampling and do that, but the security drops that way, and basically you might get into a situation when where you have a liveness failure. Whereas if you use the entire validator set, then it's much less likely that you're gonna end up having a liveness failure. So those are two options, and we are not really sure which trade-offs are better, and therefore the open question is, I'll leave you with an open question. To enshrine or not to enshrine, that is the question. Thank you very much, and if you have any questions, feel free to ask.
Well, the name of the game is that if audience have no question, we ask
Patrick.
next speaker to see if they're actually paying attention, because these talks are sequenced. And thank you, Patrick, from Arbitrum Foundation. Right?
Hello, Patrick.
How you doing? I was making a joke I was going to troll him for his talk. Here's my opportunity, but I'm bad at it. No, I was just going to ask, like, has Scroll worked out how to do the incentives yet for the decentralized proving? You know, like, how do you do the fee reward, for example?
Not really, we're still thinking about it.
So I just wanted to ask, I guess it's relevant to the talk.
Yeah, now that I've warmed out the stage, you can probably
Awesome.
welcome.
Cheers, awesome, cheers, GG.
All right, thank you.
Can I steal the clicker?
Oh, yeah, sorry.
Yeah. Oh, that was a hard one. Normally before you're talking, your heart's beating like this, you're not really listening. Okay, cool. Should I just get started then, I guess? So, hi guys, my name's Patrick McCrory. I work at the Arbitrum Foundation. And today, yeah, there's my really dinky slides. See, I didn't have that cool intro before. And I'm just going to talk about PBS across the layers for layer 1 and layer 2. And so let's just jump right in, let's have an overview of layer 1, and let's have a consider about, how MEV sort of evolved there. So at a basic level for a blockchain system, you have Alice, and Alice wants to transact. And she needs to get her transaction and communicate it to the block proposers. But the question is, how does she get her transactions across? And historically speaking, you would send this to a gossip protocol or a peer-to-peer network. So Alice would send it to the gossip protocol. Every peer will get the transaction, validate it, and then pass it on to the next peer. And the block proposers live on the gossip protocol. So they'll hear the transaction and then include it in their block as well. Now, the question is, who else lives on this peer-to-peer network? Searchers do. And I'm sure most people here are aware the searcher will hear the transaction, They'll inspect it, they'll say, oh, I can extract value from this. So they'll copy it, paste it, and get it to the block proposers first, and they'll pay a higher transaction fee so it gets into the block proposers first. Or, sorry, their transaction will get in first. But now, not just one searcher is there, many searchers are there, and they're all typically competing for exactly the same opportunity. And we call this a priority gas auction. So maybe let's raise our hands. Does anyone remember these gas auctions? Okay, awesome. And did anyone ever steal your transaction? Have you ever been a victim to the PGA game? Okay, maybe one or two hands there. Anyway, so what is a priority gas auction? Why is it important? So what happens is that, I stole this graph from someone from this really nice article about it. But basically, within that 12-second window, one searcher will place a bid, another searcher will place a higher bid, and very rapidly throughout those 12 seconds, you could have 100 different bids that are all competing for exactly the same MEV opportunity. The block proposer will simply take the bid with the highest fee because that's going to pay them the most money. And so there's two problems that happened here with these priority gas auctions. And this is sort of like 2019, 2020. One was wasteful and failed transactions because the successful transaction would get in alongside all the failed bids. So this is a waste of block space. And two, it's sort of unrestricted MEV as well. You're sort of taking the user, throwing them to the wolves, and their transaction may or may not be executed at the very end. And so when Flashbots emerged, they sort of resolved this problem. So has anyone ever used a direct transaction before with Flashbots? A few people here. Awesome. Cool. So the way they solved the problem was very simple. They set up a direct communication channel between the user and the block proposers. Okay, and so you just basically bypass the peer-to-peer network, you bypass the dark forest, so they cannot eavesdrop on your transaction. But what can we extract from this scenario? So first, we have to consider the transaction ordering policy. So in a layer 1 blockchain, we typically use the highest fee first. Whoever pays the most money is going to get ordered first. The second is the communication protocol. Can a searcher eavesdrop and learn about the user's transaction and then extract value from that? And finally, we have to consider is the user experience. What guarantees do the user get, and how long does it take until they figure out, oh, my transaction's being confirmed, or someone's extracted value from me? And so what do you do about this in the layer 1 world? What do? Do you defend against the MEV? Or do you try to embrace it and just take sort of, it's going to happen anyway, let's embrace it and use it to protect the protocol? So in the layer 1 world, we've sort of gone down the path of embracing MEV and PBS games. And why is that? And that's because to this day, I am not aware of a protocol that can defend against MEV when we take into account 500,000 validators, at the protocol level. We just don't have a protocol that can defend against MEV in any meaningful manner at the layer 1 base layer. Because after all, one of the overarching goals of a system like Ethereum is to maximize who can be a validator. Maximize that set and make the operators of the system as decentralized as possible. And one of the other problems is that, one of the reasons why you would embrace MEV is because one of the assumptions at a layer 1 blockchain is that all validators roughly get the same reward. If I get the same reward as the other validator, then we'll both earn rewards at the same amount, and we'll be equal partners, or equal competition. If one validator can take the MEV for themselves, and it's not shared amongst the validators, then they'll grow bigger than everyone else, because they'll earn more rewards than everyone else as well. And that's a terrible outcome. If we're not careful of how MEV is embraced, we'll break the property of fair reward for the validators, and one validator will grow and basically defeat everyone else. And so that's why Flashbots and PBS sort of solves that problem. When you think about what Flashbots have done, is that they've taken this on-chain auction protocol and took it off-chain. And what they enabled was to allow block proposers to outsource the work of MEV, and then a marketplace of searchers can all compete to extract the MEV and, of course, share some of the rewards with the proposers, and then they get some of the reward as well. And this is also acknowledging that someone in their bedroom can probably do MEV better than someone who's running like a validator farm for Ethereum. Outsource it to the best people who can do the work and share the rewards between both parties. And that's why it's really cool. You can share the reward and you also reduce this on-chain spam. Now, what about a roll-up? Just to highlight, that's why we have PBS for the layer 1, to protect the decentralization of the validators. But what about a roll-up? Is the environment any different? And it's exceedingly different. A roll-up already assumes that we have Ethereum. We already assume that we have this decentralized platform with hundreds of thousands of validators. We don't need to replicate this at the layer 2. We don't need 500,000 validators. We just need a handful, maybe 1, 2, 3, 4, 5 sequencers. And that's it. And as we'll see, the sequencers there to offer the user experience and the fast path. They don't actually impact the safety of the system. But that's cool. If you only have a small sequencer set, that's a much more tangible problem to deal with in terms of MEV. And the scenario is very straightforward. Alice has a direct communication channel with the sequencer, so Alice can give her transaction over, then the sequencer can give an instant response. The sequencer has ample time to do whatever they want with the pending transactions. They have a list, basically like a basket of pending transactions. They can apply any ordering policy that they want, and they could do this within a few minutes or up to a few hours. They have ample time to extract as much MEV as they want, if they wanted to do that. And of course, eventually the sequencer will take the list of order transactions and pass it on, maybe to the executors, the provers, etc. So all they're doing is ordering transactions, and that's it. So let's again compare the core components. So layer 2 is very different. In layer 2, the sequencer can apply any ordering policy that they want. The communication channel is very different. It's a direct communication channel to the sequencer. There's not necessarily an opportunity for a searcher to eavesdrop on this communication. And finally, the user experience. The user sends a transaction, the sequencer can give instant response. It's a bit like playing with the legacy Web 2 world, where you get this instant response when you sort of interact with a website. But as we're going to see, as you try to improve the user experience, you're going to impact MEV, its ability to be extracted. And there's this sort of weird trade-off between extracting MEV and how users experience using a roll-up or a layer 2. So as I mentioned, lots of ordering policies you can consider. Has extraction first, has fee first come, first serve. It could even be cal swap, that's an ordering policy. Any ordering policy that you want there. But most roll-ups today implement first come, first serve. What is first come, first serve? Very straightforward. I give the sequencer my transaction, they timestamp it, they respond to me, then they order the transactions by timestamp. It's exceedingly straightforward. And you would think with first come, first serve, there's still no MEV here. So raise your hand if you think there's MEV. Let's see. There we go, awesome. Now, of course there's MEV. Why? So what Arbitrum tried to do at least is that the sequencer has a data feed. So we get user transactions, we do first come, first serve, and then we reveal that in a data feed every 250 milliseconds. And the reason for this is that we want to provide Coinbase, Etherscan, and Fura with up-to-date data. So a user can send their transaction, look at RBScan and say, oh, my transaction is confirmed. Well, if you have a sequencer feed where you're giving out this pending data to these infrastructure providers, searchers pop up. Of course they do. And what do? Well, they listen for the transactions. If they find a back-running opportunity, bam, they send it out immediately. Oops, look at that, there's a searcher right now. Sorry. Always listening, aren't they? But this is it, you have this rise of this latency game, because in Arbitrum, you didn't just get one searcher, you got 150K WebSocket connections to this data feed. And so one is a latency game, because they're all competing with each other, and two, it's a bit like a denial of service attack on the sequencer, because you have to maintain 150K WebSocket connections, which is not an ideal scenario. So the Off-Chain Labs guys came up with a really elegant solution, in my opinion, but there was some outcry. You're already laughing about it, aren't you? You know, they basically wanted to implement Hashcash, which is basically you create like 20 priority lanes, you do some proof of work, you have the lowest proof of work, you gain access to the priority lane for 24 hours. So reintroducing proof of work in order to solve this problem. But as you can imagine, there was a lot of outcry. People don't want to use proof of work to solve this problem. Whereas, of course, for me, it's an elegant short-term solution, but it doesn't really solve the problem long-term. But this is really frustrating, right? We have this trusted sequencer, this ideal scenario where we can fully trust them not to extract MEV, and the MEV bots are still there. I mean, look at this guy. He just doesn't go away, does he? That's Phil Dion, by the way, from Flashbots. Don't know if you know who he is. Drew little evil eyebrows on him. But he's always there. He doesn't leave us alone. Well, what a guy. The dark forest is always lurking. So then the question is, you know, what's more fair? Are these latency games fair? You know, clearly not. You know, it's a denial of service attack on the sequencer, and, you know, they're just fighting amongst each other. So then it brings you back to the question, well, what about auctions? You know, that's how it was solved in the layer 1. We create this auction and let them bid for the opportunity. And that's sort of the idea behind the time boost proposal by Ed Felton from Off-Chain Labs. And I'll give you a high-level overview of basically, I mean, it's very straightforward, as you're going to see. Maybe they have an academic paper that's slightly more complicated, but the idea is simple. You know, Alice gives her transaction to the sequencer still has this data feed where they reveal the transactions, but now the sequencers compete in these little bundle auctions, very rapid auctions, and then of course the winning bundle gets sent to the sequencer, then the sequencer then decides, okay, here's the transaction batch. But the point here is that this bundle auction is configurable. It could be really rapid. It could last 500 milliseconds. It could last 3 seconds. And what you're really doing is purchasing the right to go back in time. So within this auction window, you're saying, I want to go back 250 milliseconds in the past. Another way to think about it is that you're buying for a specific position in the ordering. Maybe you want to be the 20th transaction, the 30th transaction. But you're buying for that, you know, the opportunity. And you can be selective. So in the time boost proposal, their goal is only to allow backrunning, because backrunning is not seen as bad MEV. You know, there's a lot of moral questions around that. But it can be configurable. You could allow front running, you could allow sandwiching, and because the bundles are so small and the auctions are so rapid, you could probably inspect it. Look at the transaction and say, okay, I will accept that type of MEV, but I will not accept this type of MEV. And so my last slide is basically some interesting questions around that. Should the sequencer be allowed to inspect an MEV bundle and then decide not to include it? You know, this could impact the credible neutrality of a rollup, because now they're sort of being subjective over the transactions they include. But if it's better for the user, then maybe they should do that. The auction time window is set to only enable backrunning, but, you know, should we allow front running and sandwiching as well? And maybe the last one, because these are rapid auctions, so the whole point here is to enable a marketplace of searchers who can all compete to find these opportunities. But if it only lasts 500 milliseconds and there's only 5 transactions, then, you know, there's probably only one MEV opportunity. So maybe you want to set the time window so there's 50 transactions or 100 transactions. And so then you can get more interest in, you know, MEV marketplaces out of that, because they're all competing for different opportunities. But for me, the time boost paper sort of inspired this talk. I thought it was really interesting, and I've been just thinking a lot about it, so it's not really my work at all. It's just whatever I've gathered from reading. So I hope you enjoyed the talk anyway. GG, GM. Cool.
Thank you, Patrick. Well, someone wants to give you a question back. He has been waiting.
Oh, he is here. Look at this. They're going to get roasted.
Yeah, I waited for the end of the talk to ask a very important question. I cannot board my flight without knowing the answer to it. Should we be allowed to refer to distributed ledgers as databases?
Sorry, I was just getting trolled earlier by Bartik from L2 Beats, because I keep describing it as, yeah, this should be a database. I mean, that's what they're all. We're all just building databases. Okay, so that's a bit of an inside joke, but I've been getting trolled all day for it. Sorry, just for context, so basically when you think of these systems, when you deploy a blockchain system, what you're really deploying is a database, and the blockchain has an audit trail for recomputing that database. And that's it, and people don't like that analogy. Do you guys like it? Raise your hand if you like that analogy. There you go, someone take a photo and show Bartik. Thank you, okay, I'm done. GG, guys. Awesome.
Perfect. We're doing perfect on time. Thank you. Next, we have Thomas, who wear many hats. One as a researcher at Flashbots, architect, and also as the founder of Nethermind, talking about MEV Garden and cross-domain markets.
Hi, everyone. So I was told to stand here. The MEV Garden. So that's very, very sweet name because we've been talking about the dark forest for a long time. So my name is Tomasz Stańczak. I'm mate at Flashbots, founder of Nethermind, trying to wear a few hats. And we'll be talking about how to connect through PBS many different domains with SWAF. So this is not an announcement of a product. It's not a suggestion that Flashbot's going to build it. It's more like building the open, presenting you a bit more of undercooked ideas that potentially will be rejected. Like maybe something will be missing in quality. Maybe it will be not really aligned with the values, all the values that are at Flashbot. So illuminating through the bringing transparency to MEV activity, providing permissionless access to MEV extraction, and distributing fairly the MEV revenue. All right, so once again, MEV Garden will move away to something that's a bright place, clearly divided into components, PBS, and with kind of conditions for everyone to participate. So we're talking about connecting everything with the existing ecosystem and making sure that there is place for everyone, especially that the users feel very good in this ecosystem. That's one of the small steps, really, what we'll be showing. And hopefully we'll end up with something like this. And maybe a little survey, like how many of you know what PBS is? Okay, it's going better and better. So now we divided it slightly more, but just slightly more. So I said that builders, we divide them into the sequencers and builders. Sequencers will be choosing the transactions, sequencing transactions, and the builders will be building blocks out of the transactions that are pre-selected. So it may happen in some of the setups. And it's particularly might be important if you start talking about the shared sequencers. So start to forget for a moment that sequencers are what in the rollup is like everything together. And how nowadays we see the PBS done. So I'll go quickly over maybe some very simple visualizations of what we have, what we can end up with. So nowadays many of the rollups are like SAML2 and a centralized native sequencer in it. The decentralization very often is seen as like just introduce a few sequencers and leader election, and they start proposing blocks one after another, depending on some rules. With a shared sequencer, we say that the sequencer is actually shared between multiple L2s, L1s, and we may have some atomicity with it. And then something that is like Ethereum nowadays would be you start splitting the sequencers into proposers and builders. So there's builder market, they're bidding for the best block, and there's proposers. So you know all of this, right? Now I start saying that, we will say that shared sequencers and native sequencers, like centralized sequencers, all of this can coexist, and you can start to have various combinations of all those setups. And also, a very important thing is that PBS does not necessarily require that the proposers are decentralized. You can have a centralized proposer native to the rollup and still create a builder market. So they can be bidding for the best block, and the proposer may decide to either capture that value for the operator of the L2 or to maybe burn it for the protocol. And now, as I say, all of this may coexist. And because we can have many different protocols arriving at the solutions at very different times, with different, like we see an Arbitrum proposal, we see what Scroll was proposing, what Starknet is working on, and so on and so on. So maybe in this world for a few years, where we want to create the markets, start building the markets for MEV and for PBS, and still connect all of those different protocols. So when we know that we want to achieve that, we set some design goals for the protocol that will allow to do the PBS with the cross-domain MEV. And we want to support that heterogeneous sequencer space, different designs. We want to enable permissionless and transparent cross-domain MEV market. We want to be in line with whatever happens on Ethereum, but also be in line with what happens with other chains, right? So think about not too much pushing the protocols themselves to change. We want to operate slightly outside of the protocol. Maybe opposite to what Zaki was saying, or maybe not opposite, but related to what Zaki was saying. We want to respect the position of various market players that are building shared sequencers, middlewares, risk-taking solutions, and so on. So we want to make sure that everyone feels like, oh, wow, there is a marketplace arising, there's a game which I'll be able to play with, play inside. We want to make sure that it's SWAV aligned, so that's my internal goal, like make sure that whatever we're working on at Flashbots is actually part of our greater vision that is strategically well tested and discussed. And one thing is that, and we keep thinking about it, we need to ensure that the equal rights are there for the solo stakers and large operators to participate in that game. And this is for the like validators or proposers. And now, this will be the proposal for what we really can build to try to support all of these requirements. So first of all, we want to have some kind of chain. It can be SWAV chain, it can be something on the side of SWAV chain, which is just like a global ordering system. So a set of oracles or whatever construction, and the construction here is not really defined on the technical level, more on the vision idea level. We want to order the blocks on different chains and have a way of looking at this ordering from the outside just to use it for construction of the proofs and slashings. So I'm saying I'm looking at Etherscan, Starknet, Polygon, and many other chains potentially, and maybe even things outside of the L2 or Ethereum space. And I want to keep order of everything that I can do possibly within all of those domains. And I say that I want to introduce a definition of synchronized block proposals. So if I'm a shared sequencer, for example, I'm practically, in some cases, I'll be sure that I'm proposing blocks that will happen at the same time. Like, so I know that like if it was a based rollup on L1, I know that every 12 seconds I produce block, and within that block I'll be producing blocks, batching blocks for multiple rollups. So I can start making some promises, but to describe those promises, we need to agree on some definitions. And I'm not sure what those definitions would be over time in the market, which of those would be the most, like the strongest. And here, for example, saying something like a very strict definition. Like we're looking at two different domains, and we don't allow anything in between. So on the screen, the Ethereum block 100 will be synchronized with the Starknet block, but not with the following Ethereum block and not with any of the blocks before the Starknet block because they belong to a different domain and there is something in between. So I want the blocks to be exactly next to each other. But then maybe this will be difficult, and maybe I would sometimes not care about the other domains because I'm trying to synchronize two blocks to extract MEV, and maybe not always I will believe that through some other chain's construction I can extract that MEV before this happens, before the synchronized execution happens. So maybe I want to define something that is like strict but within the domain. So as long as there is no other block that belongs to the same domain as the two blocks that I'm talking about, in between that it's synchronized. So here, the Ethereum block is synchronized with Starknet block. It's also synchronized with the Polygon block because there's nothing from Ethereum or Polygon in between. So there's only Starknet block in between, and it belongs to another domain, so I don't care. And the more domains I will see there, the more I will probably want to restrict the number of domains that I care about when defining what does it mean that it's synchronized. And then I may say that, well, I really care only about the situations when both domains that I'm synchronizing between, or multiple domains, like we can probably extend it to many domains, if no set of blocks happened in between that would belong to the same domains, then everything is fine. So here I really say that even one of the last Polygon blocks is still synchronized with Ethereum block 100, but the Starknet block 202 is not synchronized with that block because we see both the Ethereum and Starknet block in between. So this is not very strict. I'm just proposing something that may be relevant when making an announcement. Like if I'm a sequencer proposer, as a proposer, I want to, shared sequencer, proposer, I want to make commitments to what I'm going to do, and I have to describe it in somehow. And as we were working on it, we discovered that, well, the definition is not that obvious. We may still need to work about which definition will stick. The communication about this, the announcements, may happen through something like nowadays through the relay, but potentially may happen through the attestations and P2P network. So there should be no difference whether we keep the existing ideas of Ethereum and existing roadmap, and whether we change it towards the ePBS and Shrine PBS, no really, to the way we approach this solution at MEV Garden. And when you look at the proposals of Pepsi, like protocol enforced proposer commitments, you can think of this a bit like a cross-domain Pepsi. So cross-chain PBS, we're adding communication layer from proposers to builders. So the other direction, proposers make announcements, like in Pepsi, like some announcements of what I would like to commit to. And I define a synchronization between the blocks that I'm about to commit to. And I can be slashed if I don't deliver that, so we'll show how to do that. And once again, think of it maybe as a cross-domain Pepsi. And this is part of the design goals. We want to create the permissionless and transparent market. So you start to feel maybe it's permissionless because we created that chain and anyone can start announcing this like proposals, defining some kind of, we can have some format description of what I'm going to do. As a shared sequencer, I can say, Polygon Ethereum block, in 10 minutes, they'll be synchronized according to the strict domain rule. And if I don't deliver, you can slash me. If I do deliver, then I actually can start bidding on that proposal. And any of those shared sequencers, native sequencers, decentralized sequencers may start judging themselves how much of the probability of delivery of that commitment they have. Do I only propose it, only announce it if it's 100%, if I'm shared sequencer? Or sometimes I want to start extracting value even if I have 5% chance, a 50% chance of success. And I know what my deposit is, what can be slashed. So this is both the global time with the set of proposals. We look at this chain, and we see that we start noticing blocks, and there is a commitment from a proposer saying, I'll do synchronized Starknet Ethereum blocks, and then we start seeing bids from the block builders that are now cross-domain block builders, and they're bidding on what will be the best payment to that synchronized proposer. The block is selected. When it's accepted, when the bid is accepted, then from now on, we practically have a promise that there is some slashing. So the deposits where exactly it's deployed, it's maybe not the most relevant. It can be something on this chain, maybe something outside, some restaking solutions, and so on. And then we see at the end, either I delivered synchronized blocks according to that definition, or I failed. If I delivered, I get the bid that was promised. If I failed, I'm going to be slashed. Why is it important in the SWAV roadmap alignment? Well, if you've seen the presentation from Robert about SWAV, we were talking about this promise that a searcher can say, I'll pay you one if you deploy something on 2 different chains. So without this, maybe the one problem is that I may make this promise, but on the other side, the executor has to have some kind of expectation about how likely they are to achieve that success of landing something on 2 different blocks. And I want to have someone else promising that, yes, they can do that for them. So the executor wants to have a bid, but also a promise that they can operate on that bid and start simulating and building blocks. So this is the component that is needed for SWAV to connect for the cross-domain. And this one thing is here in yellow because it's kind of missing. This is risky, it's to be explored. How the solo stakers, solo proposers, validators can compete with the large operators that have huge overlap between 2 networks. So shared sequencer is a simple case, but if I'm large operator 2 networks, for example, 70% of blocks on one network, 70% of blocks on the other network, more likely 30 or so, then I will have overlaps very often. I can make these promises of cross-domain extraction all the time, so I can capture more and more value. So within these, we have to make sure that those proposals between the solo stakers, solo proposers, can be somehow coordinated, and that we know what exactly happens if the slashing happens, who is at fault for not delivering. And now what's the roadmap? Well, ensuring that the design is actually satisfying all those goals, supporting PBS on multiple chains so they can be connected to this solution. And this is not trivial, as we've seen. There are different questions about what consensus mechanisms are used, like if it's Tendermint, how this will work there, if it's Ethereum L2, how it will work there, how it will work with provers, and so on and so on. So that PBS work already started we look at many protocols and try to help them to build POCs. So reach out if you would like to have those conversations with the Flashbots team. And yes, we'll love to hear from all of the L2s, all of the domains, of what exactly works here, what doesn't work, is there much MEV to make here, how the market makers think about it, is it really needed, and is it value aligned? Yeah. And just to summarize, maybe the slide was initially at the front, but we didn't know about the time. So the Flashbots Nethermind collaboration started around 2021, and there's a bit of invitation for many builders teams or like protocol engineering teams to maybe start collaboration with SWAF, with Flashbots on SWAF on multiple components. We do lots of research materials together, FRPs, but we also do engineering. So I hope that the journey of being totally outside of Flashbots and enjoying the fantastic time on research and building can be your journey as well. Thank you so much. That's all from me.
Thank you, Tomasz. We don't have time for a question, but we have Joe coming up from Aztec.
Thanks. This one. Hey, everyone. Thanks for having me. Cool. So my name is Joe. I'm one of the co-founders of Aztec, and I'm going to run through PBS, MEV, and some of the considerations on L2s. It's not quite as simple as we may think. Ooh, I've never used one of these clickers before. Yeah, it's not working. Okay, thank you. So I was blinding someone in the audience. I'm Joe. So what is Aztec? We're a fully private ZK rollup on Ethereum. We have private state, and we have fully composable contract calls between contract A and contract B. We also have hybrid execution, so there is MEV. We have things like public function calls for AMMs, and as such, we're trying to think through what does decentralization look like, and we have a big focus on launching decentralized. You can follow me on Twitter and follow Aztec for more info on that. I'm going to try and get through this in 15 minutes, but we're going to go through why we should care about decentralized sequences, differences of block building on L2 versus L1. There are some key distinctions. A walkthrough of two proposals we received in our RFP process for decentralizing the sequencer, and a little kind of some thoughts on enshrining MEV auctions in L2 protocols. So firstly, why should we care about decentralizing sequencers? I think it's fair to say the industry doesn't really care right now. L2 Beat has an amazing dashboard, and I think no one, including Aztec Connect, has made it past stage 0 or stage 1 on the training wheels framework. If this was kind of like a report, we're doing pretty badly. You get the meme. I think like some of the actual reasons we should care, a lot of rollups are designed to be first. So we want to be the first private rollup, the first CK EVM, and this actually kind of has pretty harmful consequences. I think we should start designing things to be last. they need to stand the test of time. Decentralized systems need to be really robust. We learned this the hard way with Aztec Connect. Trying to decentralize a system with hundreds of thousands of users is way harder than just going to the whiteboard and getting it right first time. And if you're at the whiteboard, I think we can start to solve some of the issues in the L1 block supply chain and try and get to a world where maybe more than 5 people are producing blocks. And the last one won't be a surprise. I think regulation is a key reason to do this. Crypto's global, but regulation definitely isn't, and having a very centralized point of failure is something we need to kind of work around, especially with headlines like this between the differences between the UK and US, for example. All right, so let's look at the differences between blocks on L1 and blocks on L2. I think the first place to start is around the size of transactions. So for kind of non-private chains, you just submit a signature over kind of like a request or a transaction request. But for a privacy L2, you submit a proof of execution, so a zero-knowledge proof of the transaction. This leads to kind of much larger transactions. With Aztec, if we use something like Goblin Plonk and very wide circuits, they could be kind of 20 times larger than a normal Ethereum transaction. This isn't a deal breaker, but it just means that the same infrastructure or same things we need on L1 may need to be adjusted on L2. The second area is compute. So just a quick look at kind of like the CPU cycles that are needed to actually produce a block on these different kind of domains. First of all, everyone's kind of familiar with searching. There's a lot of compute that goes into the knapsack problem, trying to figure out the correct ordering for a block on L1. And then you've got to execute all the transactions and do. It doesn't really stop there. For ZK L2s, we also have proof construction. So constructing a proof of correct execution can be 1,000,000 times slower than actually executing the transaction. So when you kind of put all that together, the summary is kind of block building on L2s is not really the same as block building on L1. So should we use the same systems to kind of produce our blocks? And I think the main point of this slide is just, this is like a huge centralizing force. If you need 10 times the compute, 100 times the compute to be a block builder, and you're the 5th best block builder, is it really worth it to turn on your machine? So that's something we need to design around. We don't have all the answers, so we did an RFP to try and crowdsource some of them. We had some fantastic input from teams like Espresso Systems and Flashbots and Astria, so thank you everyone who participated. I'm going to run through 2 of the proposals now. One of them was written by me, and one of them was kind of written internally, but also it learns a lot from some of the Espresso Systems work. They also have drinks names, which I don't know where that came from. If you want to kind of look at the in-depth write-ups, you can scan these QR codes. I'll just wait for 5 seconds. So the first one, Finette, it really isn't that different to Ethereum. It tries to kind of take what works on Ethereum and mold it a little bit for L2. And it really focuses on fast transaction pre-confirmations. To do that, we use an L1 smart contract to like administer the whole process, and we have a proposer builder separation like we're all familiar with. A proposer, likely with the help of MEV Boost, will submit a block header to the L1 contract, and that will include commitment to the ordering of transactions, like hiding the actual ordering, but a commitment to that through just a commitment scheme, and a VRF output on their staking public key. All proposers have to stake in this model, and the VRF output between proposer A and proposer B will differ on each block. After kind of the proposing phase ends for a given slot or epoch, the proposer broadcasts the block contents to L2, and provers who are listening to kind of the L2 can compare the VRF outputs, look up on the L1 contract and see if it's a winning score for the VRF. If it is, and all the data is available, they can start constructing a proof from the contents. So the cool thing here is that like anyone can submit that proof back to the L1, and it doesn't have to be kind of submitted for the chain to move forward like at that point in time. It's needed to be submitted for finality, but you can kind of look at the chain and be like, if I've got all the data and this is the winning VRF output, I can move forward. And eventually the block which has a valid proof and the highest VRF output will become canonical. This means that we can get soft finality by building or proposing blocks that build off kind of unfinalized blocks if all the data is available. And you can use this with shared sequencer designs, and kind of it's quite extensible and much more like Ethereum. Yeah, if no proof's submitted, you kind of roll back to the last canonical block. In B52, this is where things get a bit more controversial. My kind of goal with it was, let's try and get rid of the proposer. And to do that, we enshrine an MEV burn auction in the protocol, and we instead focus on decentralizing the prover network. So firstly, I guess, why does a proposer exist on L1, which may lead us to kind of see, could we get rid of the proposer on L2? And I think it exists because you need to check the work of other proposers. It's the main reason it exists. A proposer on L1 could technically lie, and other proposers check that work. That's kind of the power of the Ethereum consensus model. And it also exists for censorship reasons. The wider the set of proposers, the higher the chances are that eventually someone will come along who's not willing to censor me. So it's pretty good reasons for it to exist on L1, and as such, the block rewards on L1 kind of incentivize creating a very large validator set. On a ZK-L2, my claim is that these properties don't really hold, so we don't need to check the work of other proposers. You can't lie. ZK proofs mean that if the proof system's correct, we just submit a proof to L1, and we can inherit the checking work of all the proposers on L1. And we also don't need the censorship property, because we can force transactions in directly from the L1 smart contract. So these two kind of main reasons for having a proposer don't really exist on a ZK-L2. So what's the point of enshrining a proposer into the protocol who can really just sell their right to produce blocks to someone else? Instead, we could use a block reward to incentivize a proving network or something else in the protocol. So how that works, we split things in B52 into two distinct phases. There's a block proposal phase and a proof acceptance phase, a bit like Finet. There's no proposer here, so the builder is doing everything in this scenario. The builder broadcasts a block header to the L2 network. This contains a commitment to the transaction ordering, like before, and a bid in the MEV burn auction. This is the amount they're willing to burn for this block to become canonical. They also commit to payment to the staking network, who's going to help them make a proof later on. Stakers then vote on the L2 for which proposals they will construct proofs for, likely based on how much they get paid, but there could be other factors like censorship or other factors which influence this. And each vote is weighted by a VRF output from the staker's public key. The builder then kind of aggregates all these votes on the L2, and they assemble a transcript of the block. This is committed directly to L1, and it kind of allocates who's going to do what in the proof construction phase, and also lets us define a total score for the block. And the L1 rollup contract can rank these proposals by the score, and the two weights are kind of the sum of the prover votes and the amount they're willing to burn. We're still modeling this, so it could change significantly. Again, like with Finet, because this is on L1, at this point, the prover network can just look up on the contract and see which blocks have data available for them, and are they safe to start constructing proofs for. Anyone then can submit a proof to the L1 rollup contract, and the same property kind of applies. The proof with the highest score becomes the head of the chain. And you can pay a block reward to the winner plus uncle provers as well to keep liveness. So these proposals differ quite a lot on what happens to MEV, and we don't know what the right answer is right now, but we can look at kind of other L2s and see what's happening and see how we compare. So on optimism, I think the rough model is a centralized sequencer at the moment extracts MEV to fund public goods. That's a great outcome. On Arbitrum, I think with the time boost proposals, any MEV that comes from that or like fees will go to a DAO potentially. Aztec, if we go forward with the Finet proposal, will look very much like Ethereum. You'll have a proposer and a builder who can extract MEV from the protocol, and this will be facilitated by a market like Flashbots, for example. If we go forward with B52, we've deleted the proposer, so it's the protocol and the builder that can extract the MEV via an in-protocol MEV auction. So to help us decide on these, we're doing a lot more research, but I've tried to put together some rough economics of what I think the different variables are in this. So if we look at kind of the revenue stack for a proposer today, it's roughly transaction fees, block reward, and the bribe they get from the builder to get the block on chain. And the costs are pretty straightforward. There's also, obviously, the builder's revenue stack. The ordering preference fee is designed to kind of just encompass all of the different arbitrage opportunities that exist for the different builders. And there's kind of the unknown relay costs. We don't really know who pays those at the moment, but I guess it's VCs, and some costs associated with searching. If we were to kind of remove the proposer, the builder's revenue stack could look a bit like this. So they would get the full transaction fees, the block reward, and the ordering preference fee. And in return, they have to increase their costs by doing some in-protocol MEV burn. So yeah, I guess my claim is that these are the same thing. So the bribe that's currently paid to the proposer could be paid to a protocol for a zk-L2. Lots more research needs to be done on this to see if this is a good idea. There's research on Ethereum around maybe doing something like this, but for a zk-L2, I think the requirements are a lot less strict because we can rely on the L1 for a lot of these censorship properties. So the main takeaways so far of where we've got to in our decentralization of the sequencer journey, the two proposals we're kind of going forward with at the moment are slightly based, so it's not full anarchy. You can't just submit roll-ups to L1 whenever you want, but they do use an L1 contract to decide which block's canonical, and there's some scoring logic in that contract for both proposals. They also both used a VRF. This helps us kind of protect against 51% attacks and someone kind of acquiring too much of the stake or other attack vectors here. Finet decentralizes proposers like Ethereum, and B52 tries to decentralize the proving network. We need a lot more research on enshrining MEV markets, and that's pretty much all I've got time for. So instead of you guys asking me questions, I'll ask one question to you guys. Should we enshrine MEV at the protocol or not? If you have any thoughts, please come and talk to me afterwards. Or now.
Thank you very much to Joe. I mean, I think Aztec's approach to all the proposals has been one of the most thoughtful in the space when it comes to PBS. Now, though, we turn the stage to Ben Fish, applied cryptography professor from Yale and also the co-founder of Espresso Systems. Take it away.
Thank you, Reid. Thank you very much. Right. So I modified the title a bit from the original one. There's the clicker. Let's see. There we go. Okay. PB Espresso. This is not my idea. This is Quintus's idea. I stole it from him. He has all the creative ideas. So I'll be talking about PBS for shared sequencing and responsive consensus protocols. These are sort of two unrelated topics. Well, maybe not completely unrelated because responsive consensus is Espresso's consensus protocol for shared sequencing, but the talk will be split into these two different subjects on PBS. So first, just to quickly introduce what is shared sequencing. So rollups are horizontally scaling the application layer of Ethereum. The idea is that when you add new applications, then you can have those applications add new servers that execute. Some of those applications are rollups that support other applications, but I view rollups as basically applications that support other applications. And the layer 1 is now not doing any execution. They are just verifying fraud or ZK proofs. It's also leveraging this heterogeneity, so you can have powerful servers on the application layer. You can keep the servers on the layer 1 very weak. They just verify proofs. They don't need to do any extreme execution. The problem is rollups control a lot, and that leads to the need to either decentralize the rollups themselves and add some kind of decentralized process for each rollup to decide on the ordering of its own transactions, or it moves us towards a different model where they share the L1. So the other problem, which remains if each rollup just runs its own consensus protocol for its own transactions, is that they remain very isolated from each other. And so currently, even though we're sharding the application space of Ethereum, we're sort of ruining this amazing property that Ethereum has, which is the interoperability of contracts. One contract that you deploy can easily make function calls to another contract, and they share liquidity with each other. So rollups don't scale Ethereum without changing its fundamental properties. And that's not really scaling, that's scaling and changing the target. So how can we regain the functionality of Ethereum as it is today while still scaling Ethereum? So one idea that has come out is for rollups to share a consensus protocol for ordering transactions. So this is this idea of separating ordering from execution, where the L1 doesn't build or execute, right? The rollups do that. But the L1 can provide finality on transaction ordering, availability of data, verification of state proofs. And transactions submit directly to the L1, and the rollups just read from the L1 and execute. So there's the question of, does this give us interoperability? It's also good to note that this layer that's shared by the rollups for ordering doesn't need to be Ethereum itself. It could be some layer 1.5 that sits in between. And the main reason for that is protocol modularity. Perhaps we would introduce a new protocol that has the ability to provide faster pre-confirmations than Ethereum does. Ethereum has slow confirmations time. So this is a reason to design shared sequencing layers that are not Ethereum itself, but some other protocol that sits on top, whose sole purpose is to provide a different property to rollups, like higher throughput and faster finality. The concept is, though, the same. Users are submitting their transactions to the consensus protocol that is independent from the rollups. Rollups read from this consensus protocol and only execute and report state results. So, does sharing an ordering layer help interoperability if the ordering layer is not doing execution? That is the main question of the first part of this talk today. So I'll say there are 3 advantages, but I'll focus on one that has to do with PBS, proposer-builder separation. Right? There are also advantages such as simplifying cross-rollup bridging, mitigating systemic security risks for bridges. We've written about this in blogs from Espresso Systems, but I will focus on this topic today of supporting cross-rollup building with economic bonding. And what is this? So first, you've been hearing about proposer-builder separation all day, but maybe everyone has a slightly different way of describing it, so I'll just do a quick review and present sort of my view. So the proposer is a fundamental part of the consensus protocol, because all consensus protocols today are based basically on leader election. If we use consensus protocols that are not based on leader election, then we might end up with something different, but consensus protocols like Ethereum and like the consensus protocol used in Espresso or Tendermint or any of these systems have a leader that is elected to propose transactions that then get ratified or signed by others. So if there's always a proposer. If someone says that we can remove the proposer, what it really means is that you can just use the layer 1 proposer and you don't need to introduce new proposers in the layer 2. But there's always a proposer from the system that finalizes the ordering of transactions. So builders today can compete and then produce a block. The proposer doesn't need to build a block. It can play this passive role of accepting a block from builders. And if we design this, if we leave it up to the proposer to do this and don't design anything into this building layer, then what ends up happening is a first price auction, where the proposer will just accept the most valuable block that comes out of the builder network. And so that's a reason to take a different design approach, where either we might do this in terms of implementing some smart contract that introduces some rules that we hope proposers will follow, or it can be some kind of other ideal functionality similar to what Suave is designing that implements some kind of order flow auction among users and searchers. If we can design something that is not just maximizing the profit for the proposer, but is stable and better for users, and users are only submitting their transactions to this ideal functionality, whether it's a smart contract or a protocol like Suave, then the proposer will have no choice but to accept the block of transactions from this ideal functionality because there's no transactions going anywhere else. And this only works because the consensus protocol is decentralized. Right? If the consensus protocol was not decentralized, then a proposer could say, I'm going to ignore this smart contract. This isn't good for me. I'm going to ignore this ideal functionality. I want people to submit to me the most valuable block. I want to extract all the MEV because I'm a monopoly. Right? The decentralization of blockchains breaks this monopoly so that a proposer is a monopoly for only one slot. And that is why, if we design an ideal functionality stable for users, the proposer cannot influence what happens. The proposer can either take it or leave it. If it leaves it, the next proposer will pick it up. The most it can do is delay. So that's why extreme decentralization is so important from an economic perspective. This is one of the most fundamental properties of blockchains from an economic perspective. So proposer-builder separation over shared sequencers looks the same as over Ethereum today, because Ethereum is a shared sequencing layer. So if we introduce a layer 1.5, it's just introducing a new modular layer on top of Ethereum, which runs an order finalization protocol, but still has some proposer as part of the consensus protocol that will accept blocks from a builder network, and we can design that builder network to be smart and do things in a way that's good for users, like Suave or some kind of smart contract design. So one of the things that I'm not going to really focus on MEV as much as how this problem of regaining interoperability and atomicity among app rollups that are sharing an ordering layer is that through PBS, builders can actually make promises to users about atomicity, and they can be slashed if they violate those promises. So a very simple example is the following. A builder can say, I will process your trade on Optimism and your trade on zk-Sync, which may be taking advantage of some arbitrage opportunity to 2 AMMs on the different rollups. And I promise that I will only execute them, I will only include them, I'm building a super block for both rollups, and I will only include these transactions together if they both succeed. If one of them fails, I won't include either. And this statement can be cryptographically signed, so it can be used as evidence against the builder if it violates this promise. So it can be slashed. It can build up a very large collateral that gives the user confidence it will respect its promise. And the builder then provides this to the proposer of a consensus protocol that's not executing at all, but is basically auctioning off wholesale a super block that produces a sub block for every rollup simultaneously to the builder network. Okay, very simple. Without a shared sequencer, this would not work. Or at least it would not work as well. The builder would have extremely high risk that if it tries to make this promise to the user, it's possible that the independent sequencer or consensus protocol for zk-Sync will accept the transaction, but the independent sequencer or proposer consensus protocol for optimism will reject it, right? It is not now, there is now 2 independent auctions, and it doesn't have a guarantee it will win both. Whereas with a shared sequencer and a single proposer that is elected, there's 1 auction for both together. So the builder could be slashed and lose its high collateral, even if it doesn't do anything wrong. So that's why sharing a sequencer reduces the risk of builders, allows for more builders who can make these atomicity guarantees. So the builders sit on this layer on top of the shared consensus. This is how it looks in Espresso. A slightly more complicated example would be a flash loan. So let's say a user wants to get a loan from Aave on 1 rollup of 1 million USDC, deposited into an AMM trading USDC against DAI. So now I can't immediately bridge its funds over and just deposit it directly into this Curve contract on rollup B. So we'll introduce a bank contract, and the bank contract is going to have a branch on both rollups. Okay, so there's a branch on rollup A, there's a branch on rollup B. We'll explain how the builder can ensure this atomicity of these two events, but basically the user will send DAI to the bank contract on rollup A, and it will get DAI from the bank contract on rollup B. Then it will deposit into the Curve, get back its USDC, and do the reverse, right? Deposit into the bank contract on rollup B, get it on rollup A. I haven't explained how we ensure that those can happen atomically. I will in a moment. And then return the USDC to Aave on rollup A and keep the profit, right? All of this needs to happen in a single transaction. That's a flash loan. So how does a builder enable this? Well, the builder who's building the block for both rollups simultaneously could provide a signature, right? Again, backed by some collateral. And that just gives an instruction to this bank contract on rollup B that says this action happened on rollup A, right? So you can release the funds on rollup B. And the builder creates a super block. The bank contract on rollup B just trusts the collateralized builder signature. If the builder lies, it's accountable and loses the collateral. And rollup B is not absorbing the risk. All the risk is absorbed into the bank contract. So it can become a business to design these contracts and specify your requirements for what builders need to put up in terms of collateral and other possible conditions. And it's assuming some risk, but it can also be taking a fee. So this is an example of something that's enabled by shared sequencing, which would not work without shared sequencing, right? Of course, it's not exactly the same as what you can do in a shared execution environment, but it opens up a wide design space. And really, this is just a straw man, simple construction. I encourage people to come up with more creative ideas. The builder signature would do the same for rollup A bank contract as well. It's symmetric. There are some concerns that having builders execute for all rollups may lead to builder centralization. The reality is that executing for all smart contracts, for all rollups is not actually that high a barrier to entry, right? In fact, compared with ZK proving, it's not that high a barrier of entry. ZK proving is extremely expensive. It can be like 10,000 times or more expensive than executing. And the requirements of the builder market don't need to be the same exact requirements in terms of decentralization as the consensus protocol. We need many, many nodes participating in consensus so that proposers act passively and don't monopolize. But we don't necessarily need 12,000 competing builders to have a competitive market that takes care of monopolistic forces. So it can just be sufficiently permissive and open and free entry and have low enough barriers to entry such that it's sufficiently competitive. In fact, the barrier to entry for builders is much higher without shared consensus because builders take on more risk, as I illustrated a slide earlier. Builders would require more capital to win simultaneous auctions. They would absorb more risk. They can't promise user atomicity without the risk of being slashed. So, where there's a will, there's a way. It's better to have shared sequencing. We will lower the barrier of entry for builders rather than increase. So, now for something completely different, I will talk a little bit about PBS for responsive consensus protocols. So Ethereum's consensus protocol is not responsive, meaning it has a fixed block time. That is 12 seconds. Ethereum's finality is not actually 12 seconds. It's much longer than that because the transaction needs to be several blocks deep to be confirmed. So it takes about 15 minutes to finalize in Ethereum. A responsive protocol does not maintain the extreme availability that Ethereum has. These two properties are incompatible. But what a responsive protocol can do is it can give finality as fast as the network will allow. Fundamentally, it will stall if the network is not doing so well, whereas Ethereum can continue even if only 10% of the network is live. So due to the CAP theorem, these two properties are essentially incompatible. But optimistic responsiveness is the property that can get you as close as possible to the performance of a centralized sequencer in a decentralized way. And the nice thing is you can compose them together because you could run optimistic responsiveness on top of a dynamically available protocol. So consensus protocols that can return an answer immediately under optimistic network conditions are called responsive. Okay? There's no block time in responsive protocols. So how does this affect PBS? So let's look a little bit at the round structure of Hotshot, which is based on PBFT and is a responsive protocol. In the first round, the leader proposes a block, collects back signatures, then it will aggregate these signatures, form something called a quorum certificate. It will broadcast it again, aggregate them, and collect signatures on that. So again, this can happen if the network is very well connected, or maybe there's even a content delivery network that assists this to proceed at very high rates. Then as soon as these signatures are collected, the protocol doesn't need to wait. It can just move on. Finality has been achieved. So under optimistic conditions, we can finalize blocks as fast as the network will allow. The problem is with PBS, if a leader has only one proposal before the next leader comes up, then it's incentivized to delay. Because in order to run it could, for example, run the auction for longer and obtain a more valuable block from builders. So one solution is not to rotate leaders based on blocks, but rather to rotate leaders based on some time window. Okay, so we can allow the leader to propose and obtain finality on as many blocks as it wants consecutively until this time window expires. Right? I'm not going to go into the details of how you do that in the consensus protocol, but that's the main idea. It doesn't completely get rid of all incentives to delay, but it goes very far to mitigating this primary concern. When is it safe for a builder to release data? So in PBS for Ethereum today, the builder releases data after receiving a block hash. And then it races with the proposer to relay that block hash in order to get that block accepted. And at this time, it releases the data because Ethereum nodes won't accept and vote for the block without receiving the data. Now, if the proposer proposes a conflicting block hash, it could get slashed, but sometimes that slashing amount is low compared to the amount of profit it could make from stealing the MEV from the builder. So they really do engage in this race. And it's even possible for the next proposer to fork the block and steal the MEV. So the protection for builders today in Ethereum is not actually that high. And I'll argue that it becomes a little bit better when we're looking at a responsive protocol. With a responsive protocol, once a builder has received a signed proposal, it can ensure the network reaches strong finality within a certain time window and under good network conditions. Of course, it's possible for the network to experience a fault, but it can gain confidence given its observation of the network that it has and again a much higher confidence that it will be able to succeed in getting this finalized and not allowing the proposer to steal the MEV and do something else. For even stronger protection, the builder may only release the data after seeing the first quorum certificate on the original proposal. Remember, there's 2 rounds. This just brings it closer to the finalization gate, and it doesn't really need to release the data until the second part. There are some caveats of that. Now we only have 1 round to broadcast the data instead of 2. That's easily solved by broadcasting an encryption of the data starting at round 1, and then releasing only the decryption key starting at round 2. The decryption key is small and can be broadcasted faster, so that solves that problem. It's harder to pipeline proposals, though, with this idea. So one of the nice things about protocols like Hotshot is it allows for overlapping rounds. But if we hold on to the data and we're already proposing a new block in the second round, then this gives the builder of the previous block an advantage for building the next block, since it's the only one who really knows that information ahead of time. This might be addressed by order flow auctions, right? These ideal functionalities might be able to take care of that. They essentially create one builder abstractly that is the ideal functionality, and have all the real builders just participating in it as a multi-party computation. So thank you very much. That's what I had to tell you about today. And next up, we have Evan Forbes, who is going to tell us something exciting about ending the proposer monopoly.
Thank you. Hello, hello. Okay, so I work at Celestia. I'm a core dev. My name's Evan. And I'm here to talk about exploring MEV capture in modular systems and really start a discussion about a few ideas that they already exist. If we combine them, we can create a very powerful tool. And to be honest, I just don't think enough people are talking about it. And now, before I get any further, this has trade-offs. Everything has trade-offs. Only Siths deal in absolutes. So, just getting that out of the way. The alternative title to this talk was How to Make Validators Cucks. And on one sense, I'm just being playful. But on another sense, I'm being very real, weirdly real. So like the status quo of validators is capturing large amounts of value, right? This is how it works today. And this stems from the fact that they have a monopoly over that given block. Now, it is a small monopoly. It is only for one block. But sometimes, like in the context of a builder, it's very important. We can have a builder build a block. It has 3 heart emojis. That's a lot. Everyone loves that block, but that's not the block that gets committed. That's not the canonical block. That's because a different builder found a way to exploit more MEV or do something else and ended up bribing the proposer more. So now we pick that block. So the proposer's getting most of the money. Now, that's not the end of the world. It's not even the worst thing. Ideally, like the proposer can up the security budget. It's not even sure that like this is not ideal. Like all MEV has to get captured somewhere. Going to the proposer is not the worst place. However, it would be really nice if it was more programmable. If we had a way for L1s and L2s or rollups to be more programmable. So we also have to consider that with rollups, this has to be scalable. Not just in the sense that there's like 1,000 different instances of this setup, but also in the sense that rollup devs only have so much brain capacity. They can't be playing like this 5D chess when they're thinking about these things. So shout out to Skip, if anyone from the Skip team is here, for pushing the narrative of sovereign MEV. Now, all I'm trying to say here with sovereign MEV over solving MEV is that there's many different solutions to capturing MEV. There's not just one, there's many. We're picking winners and losers here, all right? So that decision is between like a community and their God. That is not like a decision that you can make for everyone all at once. That's at least what I believe. So in order to solve this, to make sovereign MEV, you have to move it on chain. Because when something's on chain, it's programmatic. And when something's programmatic, it inherently, in the context of a blockchain, is verifiable. So if we want it to be sovereign, all we have to do is choose to change our binaries. By simply switching our binaries, right, we now have changed how MEV gets captured, assuming that we can get it in protocol. So in order to do this, you have to break the proposer monopoly. This must happen. So this is a meme that I stole from Elijah. Elijah works at Duality. He's done some amazing work in this area of ending the proposer monopoly. And if you recall the first slide right, if we don't end the proposer monopoly, then there's always going to be some sort of censorship that they can do in the context of MEV to game the system. So we can write whatever clever rules we want on chain, but it doesn't really matter because the validator can always, or the proposer can always accept a block that gets built to game the system. So also shout out to special mechanisms groups. A lot of this work is just like repurposing their work. Highly recommend. So we kind of have to think about different things differently. Instead of building a block and then coming to consensus over it, we have to come to consensus over an unbuilt block, and then we build it, right? We build it using a deterministic function. So there's two things necessary here. We need to have a way to have for proposers, multiple proposers, include their input for what they want to be in the next block in the next block. Elijah refers to this as multiplicity. So there's many different ways to do this. One of the simplest ways, or one of the ways that I keep coming to, is just some different flavor of narwhal and or tusk. And that is great because it makes the entire block censorship resistant. There's other ways to do this. So Skip does top of block auctions. They already have this implemented. If you want to go try some of these ideas out, you can literally go do this by building a Cosmos chain right now, thanks to Skip. And you have self-assembling blocks. So this is the second part. The second part is that you need a deterministic function to build a block. And you can't just, it's very important that the order of the inputs doesn't matter, right? It's addition. You can add two numbers in any order and you'll get the same result. That's the important part here. Once we have these things, we are now free to define MEV capture. So this is again in the context of L1s at the moment, where for the simplest case, all we need to define is a less than or equal function of what a bundle is. Now, what's the only thing better than one fire emoji? 3 fire emojis, correct. So if we have this, we can do something that's similar to a fork choice rule, but now we have a bundle fork choice rule. So you imagine we have a less than function, that's all you need for it to sort. Now we can sort these transactions or these bundles. And if there are any conflicts, then we go back to that rule. Well, which one has more fire emojis? Okay, well, we're going to pick that one. And you can replace fire emojis really with anything, but this has a cost. This has trade-offs. This is not for every state machine. This is not for every blockchain. In the context of Celestia, there's one thing you can do. You can pay for data to be included in the block. That's it. It's payments. This means that there's basically no conflicts. Conflicts are incredibly rare. So that dramatically, that makes it so it's like a very viable thing to do in Celestia. Now, if you consider other chains, like most chains today, are like these permissionless Turing-complete smart contract platforms that whenever you see a transaction, you can't even know what state is accessed until you execute the transaction. That's not really like a viable thing. You can't just have like a deterministic function. Not only that, is that if you have a lot of like MEV to be exploited, then it turns out that you have something that I'm referring to as death by gas auction. You just get completely overwhelmed, unless you have some sort of private mempool. That's not like a hypothetical, that's like a well-tested thing that happens all the time. So this is like, it's very dependent on the chain. Fortunately for Celestia, you can do this. So now the proposer monopoly has been broken. We can define how we want MEV to be captured on the L1. Rollups should also be able to easily define how they capture MEV. And they can do this too, right? The proposer monopoly is broken. We can submit multiple different rollup blocks as if they were a builder, like in PBS, to the same Celestia block, and now it gets included, right? And now we can define, similar how we defined a bundle fork choice rule, now we can define a just fork choice rule, a normal fork choice rule, except for it's completely arbitrary. We're used to fork choice rules with like hash power and stuff, right? This is just completely arbitrary. What does heart mean? It could mean judging by Twitter sentiment, people love to burn tokens. I hope we get more creative than that, but that is like a perfectly functional thing. Whoever burns the most roll-up token, not the L1 token, the roll-up token, whoever burns that, that's the canonical block, right? Fork choice rules rule, because you can just have anyone build. You can make it so that I can have, like, literally anyone can submit a block. Rollups do not have the same issues that L1s have, where you have a limited set of block producers. Rollups can have however many they want. It just has to be defined in your fork choice rule. So you can, like, again, like, this can be very arbitrary. Rock beats scissors. But the coolest thing about this is that if we ever decide that we want scissors to beat rock, all we have to do is change our binaries, right? We can just do that. And in the context of modular blockchains, in the context of these, we have these trust minimized light clients, right? These light clients are the ones that are verifying the chain, the node operators, right? So they decide, light clients decide how this actually operates, how MEV gets captured. Oh, and as a side note, you can decentralize how your rollup gets sequenced just by simply having a fork choice rule and relying entirely on the consensus of the base layer. No big deal. Shout out to Rollkit. They're working on this. If you really want to get your minds blown, talk to a Rollkit dev. Lastly, again, not everyone can do this. This is extremely limited. It almost requires privacy tech. You can ditch sequencers entirely. You can just have a bundle fork choice rule, and the blocks just build themselves. So there are trade-offs. This will not work for everything, okay? So it has increased demand for block space. Currently, that's DOA. It won't work. But can we imagine a world where block space is abundant? Thank you, Nick. So if block space is abundant, this is actually more feasible than we think. And increased full node requirements. There's no way of getting around that. This has increased full node requirements. However, it's very application specific. If it's very dependent upon your fork choice rule. It's very dependent on so many different things. So we can build around this if this is a property that we want really bad. And I mean, this isn't really saying anything new, but like, in order to have good MEV, we need more privacy tools. And same thing goes for here. So when MEV is defined in protocol, and when light clients can verify the protocol, right? That means that light clients can determine how profits are captured in a system. That's pretty crazy, right? That's pretty damn crazy, right? Power changes hands. It is no longer just the validators, the politicians, the technocrats, and yes, even the token holders who are deciding these things. It is light clients. They are cucking all of these people, okay? So that is how I would like to end my talk. If you're interested in anything else, I have a GitHub, Evan-Forbes, or just find me on Twitter or anyone from Celestia.
Thank you very much, Evan. And next up, we have John, who will take the stage.
Okay, cool. I've had a lot of coffee and I have a lot of slides and I don't have a lot of time, so I'm probably gonna be bouncing for this a bit. I'm gonna be talking about why like proof of stake like kind of makes sense, but like kind of maybe doesn't make sense. And particularly I'll be, there we go. So this will be applicable to like pretty much any proof of stake type chain, but in particular, I'll have like a lens on rollups for this when I'm talking about it. So we've all heard there's like a million different sequencer decentralization options, shared sequencer, you can run auctions, proof of stake, like all these different options. In particular, I'm gonna be focusing on these last like kind of subcomponents of that, which is applicable to a lot of places. So that's proof of stake and proof of authority, and kind of like variations thereof. And my goal, kind of by the end of this talk, is to convince you that those two are like actually kind of the same thing when you play out like how this rationally looks at the end of the day, whether you have a proof of stake mechanism or you just like literally let your governance just say, hey, these are the people that we want to be our delegates, and you just don't even bother with staking. They kind of end up in the same place roughly. So starting from really basics, what is proof of stake for? It is not to slash people's money. The like fundamental reason why you have proof of stake or proof of work or similar things, it is fundamentally a Sybil resistance mechanism. We need people to vote for us, and if you just let any single person, one vote, you get Sybil attacked, so we need to like meter who can actually contribute in this system. So the simple way to do that, generally in any permissionless protocol, is you tie it to some kind of real economic resource. So proof of stake, you put up stake. Proof of work, you prove that you burned energy, so you've submitted some real cost. The other way around this is also you could just have basically like a permission setting, noting that the difference between permissioned and permissionless is like actually kind of subjective in like how people define it. But you could just basically have some form of trusted setup where we say like, hey, these are the people who are voting for us. We know who they are. We trust who they are. So looking at proof of stake, how does it play out when you like actually look at what happens and where the incentives go? So simple, delegated proof of stake. If you don't do it in protocol, it'll rise out of protocol. But basically, there's a clear separation between the people who have capital and people who like actually want to run the operation. So you naturally need some form of delegation. Like I might have capital that I want to stake, but I don't want to run this stuff. So I delegate it to someone else. That's super capital inefficient, among other issues, so you end up with liquid staking tokens. Like this is what we see on Ethereum. This is why Lido popped up. So this helps provide people liquidity, do the out-of-protocol delegation for them, hands people back like, okay, I don't want to stake, so I get my Steth token, and like someone else, they go figure it out, like how to manage that for me. One of the problems with liquid staking that like people talk a lot now about is this like kind of inherent principal agent problem between someone like Lido and someone like Ethereum or any other protocol, is Lido may have like a profit incentive that is not aligned with like my values and my governance of my chain. So this is why something like dual governance is like pretty much necessary in my mind for like any kind of liquid staking to be viable in the long term. So like some way for that protocol to align itself with like the underlying protocol. So in the case of like Lido, what they're talking about is like, okay, what if we get, instead of just letting, LDO tokens decide everything, we give Steth holders veto rights who are like presumably a subset of like this Ethereum consensus that are aligned and will have like a different motive than necessarily the profit-seeking LDO holders, which is helpful. So then I'll get to the next thing. So proof of authority kind of like is like this like dirty word that like whenever I try to like say this, the reaction is generally, oh, it's super centralized, it's gonna be way less secure, like this doesn't work. I'm gonna try to convince you by the end of this that I think like variation of this can be more secure and more decentralized than a proof of stake mechanism, like very clearly. So proof of authority, I think that's a reasonable term when you're talking about like a truly like private permission type blockchain, potentially even like an RWA one where like Circle has like real control over this thing. Proof of governance, I'm saying that like there's a clear and credible governance mechanism in place to choose these delegates. So it's like actually a bit reminiscent of the way that like Mustafa has described the difference between sovereign rollups and smart contract rollups. It may be more of like a social distinction more than like a very concrete technical one, but I do think it is important. So simple example would be like, look at rollups. Like they'll presumably, taking the simple case, like you have a smart contract bridge on Ethereum that has like very powerful governance for this rollup. And for something like Arbitrum, you already even see the initial form of this today where like you can force inclusion of a transaction through the L1 and they could forcibly remove the sequencer if they should so choose. And similarly, they could just choose like, hey, here are the 10 delegates that we want to be our sequencer instead of the 1. So now I'll start to go through like concretely like what are the differences between all of them. So one is permissionlessness. So this is part of why like I'm targeting this specifically at rollups. Like I would say off the bat, this is obviously not an Ethereum like an Ethereum type option. And it should be very obvious why. Like Ethereum does not want to be like actively saying like, hey, here are the 30 people that like we trust to do this for us. You want to let validator number 1 million join the validator set and like be non-opinionated about that, which I think is like very different from rollups. And that's the point here is like, that sounds like a downside, but I don't think that rollups are optimizing for the same thing that their base layers are optimizing for. Like they're already paying the base layer for that decentralized consensus in the first place. Like, and that is why they're not going to, even from an economic perspective, it's not even going to make sense for them to have validator number 1 million and no one's going to want to do that and it doesn't add anything really. Like it's particularly for that kind of doomsday scenario that they're already paying the L1 for. And in addition, like kind of going back to like Patty's talk before, it's actually like very helpful in many cases to have permissioning because like you want them to do things like enforce certain transaction ordering. Okay, and governance, this is very related to the point before, like Ethereum does not want like active opinionated governance. That's like saying, hey, we're picking all these people. I think the practical reality is that like for most rollups though, they're probably going to have this. Like you look at the ones today and the simple examples like Optimus and Arbitrum, they have this giant bridge. You're required to have some form of like legible on-chain governance that will be presumably powerful, unless you think that they're optimizing for this like very immutable type contract and governance, which I tend to think is like rather unlikely for most of these, but it does make a difference if you do. So accountability, this is like one of the things that everyone kind of like harps against here is like, this is one of the big benefits of proof of stake is like, oh, we could like slash the bad guys. And like that is seen as one of the benefits. I like tend to disagree with that once you like actually play out what this looks like in the long run. Because the reality is the large majority, if not all stake, is going to be delegated. Like there's a natural economic incentive to separate capital from labor, and we like see that play out very, very clearly in every proof of stake system. What I think is like the real advantage of proof of stake over proof of work is like, it's not necessarily the slashing aspect. I think it's more so, particularly once you play out the economics, it's the very targeted removal of who the malicious attacker is. Where in proof of work, you nuke the hashing algorithm and you restart from scratch and you're kind of screwed. So in proof of stake, it's not so much the slashing part of it that I think is like necessarily the most important part of it. It's that you can very targeted remove, okay, these are the bad guys, these are the people we want to get rid of. And you still keep the same thing here if you have your governance just electing them. So this is why like, I think like economic security just gets like a little overhyped sometimes when you like look at the simple incentives. Like you could have $1 billion or $100 billion if the guy who's like the operator who's doing that, like it's literally not his money. This is not like an incentive compatible thing. It is just a reputation game that you are like assuming that they don't want to light your money on fire, which is fine. But like they also don't want to like screw their business and like lose out on all future profits. It's the same thing. Like it's an understanding that this is a reputation game and not like a cryptographic, like crypto-economic incentive compatible design. So the other point is like, so you realize, okay, so if it's not necessarily just as a punishment mechanism, you realize, but it is still important, like, okay, if I'm gonna get slashed, I'm gonna pick my delegator wisely. So it is an incentive mechanism for me to pick a delegate appropriately, which does matter. And so, so moving on. So like this is from like a post that Nick Carter had a while back called "It's the Settlement Insurance Stupid," which is actually very good. So taking some pieces from it, ledger costliness, you're talking about the amount paid to validators / transaction selectors per unit of time. And like particularly in the proof of work context, you can assume like reasonably closely like this reward paid is proportional to like very close to the amount of like energy and real cost that is spent to earn that. And a greater salary to them means like a greater security because like it is more costly to reorg that chain if you're paying them more because that means it is a higher cost to do so. And then on the other side is a like kind of badass quote from the Prince that Josh sent me, which is like kind of reminiscent of this, like it reminds me of it a bit, where if you're basically relying on mercenaries, like when the day comes when they're like not necessarily aligned with you, like you might kind of be screwed. So you probably want to have people who are like are aligned with you and not just always like explicitly dollar for dollar profit seeking in a situation like this. So talking about settlement insurances, broadly, systems' ability to grant recipients confidence that a transaction will not be reversed. So economic security, when we talk about it, we're talking about like what is the cost to reorg the chain here? So proof of work, as I mentioned, like very simply, you know, you have to pay some money to like literally mine the blocks to do this. Proof of stake, it's costless to simulate blocks. So like when we're generally talking about the economic security, we're talking about the slashing. But like as I kind of just described, that slashing is like not necessarily deterrent if you're delegating all of the capital to that person. So it's like it's not like the actual same protection there. So delegation does remove that, and you start to realize it is more of a reputation game. So if we play out that scenario where you do have that separation of capital and labor, which is like where the natural economic incentives lead to, what is proof of stake at the end of the day? It is back to that thing that I said in the beginning is like the fundamental thing. It is a Sybil resistance mechanism and a mechanism for us to delegate who are the people who care about our system, and like those are the people we're going to delegate to vote for us. It is not necessarily like a way for us to actually penalize them because there's an incentive for it to not be their money and like have that separation again. So then the question is, okay, if this is a mechanism for us primarily just to like actually pick people who are very aligned with us and like have the right distribution of the validator set, is this the best mechanism for us to pick them? And like, this is where I have a rather strong opinion. I do not think that it is. Because like, it's a simple like tragedy of the commons if you take out like liquid staking protocols. Like I think DPoS is like the worst without them, arguably, because like what does regular user, you know, like do in this scenario? I go look for like who's the biggest validator, the second biggest validator. Like I go delegate it to Coinbase or whoever else. Like it's nice that you have a permissionless long tail, but the practical reality is the large majority of stake ends up going to like 2 or 3 people. Versus proof of governance, you're not putting like, okay, my dollars go to this person, like I select that person. We are voting as a collective for like what is the best distribution as a collective interest for all of us. So we can go intentionally pick, okay, here are the 30 geographically distributed people that we like, and we give them equal voting power across them. I think that's like significantly harder to corrupt and like potentially more decentralized, and that's like actually what we see with like, so like moving on here, like this is the decentralization, which like kind of follows on that. Like what is decentralization? It's like that, it's that kind of that point that I was saying there of like, is it validator number 1 million that makes you decentralized, or is it like the composition of what do we care about like the top of the stake? And in particular, like this is kind of like the like visual example of it, like which of these is decentralization? And particularly for a rollup, I would argue like the second one is actually the much more important one, particularly because they're paying the L1 in this case, like for that doomsday type scenario of recoverability. They are like very much optimizing for like what are the real-time short-term guarantees, because like also their reorg cost is like being immediately reset once they like go back to the L1. So I think the second one is more important, and the second one is actually like that is Lido's Ethereum stake distribution. Like this is very intentionally what they do under the hood. It is we pick these 29 delegates who are decentralized, who are responsible, and these are the people that we equally distribute votes to. And like that is the kind of thing that you can basically just in-house to your protocol if you have the opinionated governance to do that. So in terms of capital efficiency, this should be intuitive. TPOS, incredibly capital inefficient. Like it's not good for your, your type of like roll-up economy or whatever it is. LST is significantly better, but you are adding on like the additional risk of like these financial derivatives, discrepancy between like different types of holders, unbonding periods, et cetera. I would say proof of governance is like absolutely optimal in like kind of all of these dimensions. Everything stays in the native base asset. Everyone has like an equal value capture to like whatever it is you decide. You want to burn it, go ahead. Like you want to send money to your treasury to allocate it based on whatever your subjective governance process is, go ahead. And like you just have this explicit agreement, like the validators get paid X / your sequencers. And so like this is what it comes down to, is like the alignment that I was like kind of touching out with the dual governance before. So like this is a section taken out of like Danny Ryan, his like very popular post on like the risks of LSD, where he's talking about, okay, like Lido's doing this dual governance thing, which is supposed to like, okay, that'll mitigate the principal agent problem. But he's saying like, okay, but stETH holders and ETH users, like that's not the same thing. It is still like a significantly lesser alignment. And then Hasu had a post after that pointing out, which I agree with, is like this is not just like a Lido / liquid staking thing. This is just like an inherent problem with proof of stake. Like people who are staking in DPoS, they are also not the entire like superset of like rollup / chain users / social consensus. Like there is a disparity there. So what do you want to have? Do you want to have your rollup token holders just like deciding by themselves? Like these are the people that we delegate to. Do you want to have an LST governance deciding it like completely for your chain? That's like maybe a little bit better because it like maybe it's more decentralized, but it's also maybe worse because you're less aligned. LSTs with dual governance, I would say, is the best of those three because like you're letting a subjective governance process intentionally decentralized, but like retaining power over it to like veto harmful actions. And the last one is the cleanest one of just why don't you have your own chain decide? Like again, this doesn't make sense for something like Ethereum because like they're not going to have that opinionated, concrete governance process to be like selecting all these different validators. But that is the exact opposite of what a lot of these rollups are doing. And I don't think it's a coincidence. And like happened to actually see it, I think it was like a day or two ago. Optimism is, to the first of my knowledge, the first team to announce this in their governance post that they put out the other day. That they intend to basically, this is their plan, at least initially for the sequencer, it appears, that their token house will be able to initially choose like who are like the sequences that we want to whitelist, and then their identity-based citizens house would be able to veto those decisions. Like that is very different than just like a straight up token holders alt vote. And so like that is kind of the point here is like, we all know that like token voting is like not necessarily the best, and like this lets you bring in that more subjective governance process that you may want to be creative with. Even if it is just straight token holder governance, I would argue that the majority token holder governance as a collective would make a better decision than everyone doing it individually. But when you also introduce something like this where you allow identity-based governance to be able to have additional rights, like that is a very clear advantage over these other ones where you're entirely subject to like, okay, what do the token holders decide? So this is like kind of related to that, like who is the monopolist in this scenario? There are like short-term monopolist powers of like whoever is the sequencer / whoever is the validator in these protocols. I would argue like the much more important monopoly power on like any rational time span is like whoever chooses those people. So whether that's the token holders, the governance, like whatever your mechanism is. And this is like a similar quote again out of like Danny Ryan's post, which is like, yeah, like Lido could become in that position. Like that's an important reason for dual governance. But that is a power that you don't want to be handing over. And like, I don't think that is a power that the sequencer reasonably has. Like, yes, they could do things on a very short time horizon, and then you can immediately remove them and they lose all of their future revenue. Like, I think that latter person is the person who's actually in control there clearly. So as a quick summary, I mean, like proof of stake, like it makes sense for protocols that are permissionless. They don't want opinionated governance. Like that makes sense for Ethereum, but like clearly LSTs will rise, and they do help decentralize meaningfully in my mind. Like Lido adds to the decentralization of Ethereum like very clearly on like just look at the operators and distribution of like versus if everyone just gave that stake to Coinbase. Like it's clearly significantly better. So some form of dual governance is also necessary in my mind. Proof of governance, like I think that too many rollups are just over-indexing to like, okay, this is what Ethereum did, so we need to do the same thing. But I think that they're just like, they're fundamentally building for a different thing. Like Ethereum is building for rollups. Rollups are building for users primarily, and they're like optimizing for very different things because they're already paying their base layer for all of those types of assurances. So I do think that this is like very viable for them because they do have very different priorities, and because sequencers are fundamentally just like less powerful than like L1 validators. In particular, like as like they are getting this finality, and like you immediately like that cost to reorg effectively goes back to 0 when you're posting to the layer 1. Like they are very short-term guarantees. This is like kind of the key, I would say, synthesis of the whole argument is like, as a summary, if we put things back together, just like how does proof of stake end up playing out? You do some form of simple DPoS, and okay, capital holders, like they want some form of liquidity, we want delegation of stake away. Liquid staking arises. Like that's very natural. It's capital efficient, it's better. But we have that principal agent problem, so we introduce dual governance. And what did we end up with at the end of the day is a total separation of capital and labor because that's where all the economic incentives are. And we have a governance mechanism that is aligned with our chain that manages the delegate selection. So the only questions at this point remaining are really, do we want to let that delegation sit outside the protocol? Do we want to have this staking mechanism let, you know, Lido, Rocket Pool, whoever decide that? And then we like try to rein them in with like some sort of veto right / have a market there? Or do we just like in-house that because we have our own governance, we don't need to let them decide / we don't need to leak value out to some other protocol that's gonna like take you know, a chunk of all the revenues. And then why add these financial derivatives? Like I came from like a financial derivatives background before this, and like I'm rather opposed to just like layering on a bunch of financial derivatives on top of the consensus layer if they're unnecessary. Like they tend to introduce a lot of hidden risks that we like don't particularly understand. And like, I don't think it's a Pandora's box that needs to be open for rollups necessarily. And in particular, if we realize that it's primarily a voting mechanism, it's not like an incentive compatible like deterrent. So we don't necessarily need it. And I think that is a risk that is like better to avoid. So it's not even that like proof of governance is like this like perfect thing. I think that this is inevitably where you end up if you just play out the economics. I think this is the rational market outcome of letting these economics play out, is this is where you end up. It is the governance, it is the chain that is in control in the best case. So why not just like enshrine that and put it in the best way? This is the reason that like I'm kind of like skeptical about it. Like governance is really hard. I like do not doubt that. It's really, really hard to do this. Like just saying like, oh yeah, go replicate everything that Lido does. But in particular for like chains like Optimism, like Arbitrum, et cetera, that have an active, that have a very involved governance, that is thoughtful and is able to decide like these are the delegates that are aligned for us, I think that makes a lot of sense. This is PBS day, and I didn't really talk about PBS. You could do PBS with all of these, and I think it like actually makes it easier because when you have a permission set, you like the simplest example would be like you're kind of back to like the Mev Gethi days, more so where it's harder if you're trying to optimize for like Mev Boost, like oh yeah, we need validator number 1 million to be able to do this, and like we can't trust them. If you have like 10 people, 5 people, whatever it is that you can kind of trust them, makes it a lot easier to like not have a lot of these censorship and centralization problems. Like the sequencer can like add transactions in and you trust them kind of not to screw you. And that is all. These are the slides. Thank you. And I have no idea where I am on time. I'm assuming I'm over and that Tina is up next.
Well, in fact, we're switching order a little bit. But before we do that, one question from the audience. Anyone? All right. Oh, it's going to be a tie.
Hi, really enjoyed that, thank you. And it's in line with, mostly aligned with most of that. One question I do have is, how do you think proof of governance affects liveness and the relationship between that and censorship resistance, right? Because there does seem to be some use cases, maybe it's a governance vote, maybe it's DeFi liquidation, maybe it's sort of a game that's being built on an L3 that requires very strong liveness guarantees. And it strikes me there are a lot of instances where liveness failures can actually be censorship resistance failures. So I'd be interested to get your perspective on how, whether or not proof of governance changes that and your thoughts in general.
Yeah, I mean, it's definitely primarily like one of the largest reasons I think that you should at least decentralize the sequencer to some capacity, even if you don't need to go to a meaningful extent. It is the simple fact of like, yeah, servers go down. Like that is not a good thing for any application, whether it's high value or low value. I would say the like absolute minimum that I would want is, even if you have a default centralized sequencer, is governance votes of, okay, we have these like 5 backup sequencers that, okay, if X number of blocks are missed, like we just go to the next one, we go to the next one, just like down the list and then open it up after that. So I do think it is like critical, even if you want like a default centralized sequencer, because it is super efficient to just like have one person giving you these guarantees, but be ready to go of like, these are the governance elected people that we trust to fill in for us. Similarly for censorship, I think it is like, again, it is easier in my mind to like do the PBS stuff when you don't have to trust like validator number 1 million. You could say like, hey, we have 20 of them, and like the builder becomes less of a choke point now, because like, okay, they could see the block, they can add in the rest of the transactions. Like it looks more like MEVGeth, which is helpful. And then also just the simple composition of like the sequencer set themselves is, I think it is much easier to get like a graph that looks like the Lido distribution graph versus if you just like let staking economics play out. It's like what you really care about here for censorship resistance there is like, it's not like what's the composition of the last like 5% of validators, how many are in there? It's how many do you need to get to 1/3/51%/2/3. And I think this is the clearest way to get like a very broad composition across that. And then you could also add in other mechanisms if you want like multiplicity, et cetera, to help with that as well.
Great question and great answer. I'm really curious of Nick's question. So I'm gonna let you ask away.
Can you elaborate on why you think this is more appropriate for rollups rather than L1s? I remember on the slide you mentioned the permissionless part of it, which I do agree with, but can you elaborate more?
Yeah, so I guess I would say oversimplifying there, it's not necessarily just a layer 1 versus layer 2. Like as kind of shown in like a lot of the screenshots there, like one of the people who's been like starting to tweet about this lately is like Sunny, and like I think this makes sense also for like plenty of Cosmos L1s, where it's very similar to what I'm describing with the rollups of like, okay, we have a very clear tight-knit community that's like aligned on like what our values are, we have an active governance process, like we are able to manage this. So it's more of a neutral/permissionless base layer is like what you're going for. That like would not want this, like it's just not an option. So Ethereum is a perfect example of like, obviously they cannot do what I'm describing, like it would make no sense. And that is reasonable in my mind, because particularly for the base layer, like that is generally the area that you're looking for, like, okay, we want to be completely credibly neutral, like no subjective process, even if like the free market economics are like kind of concerning in the long run. I think it's also the place where like you have a best shot of like winning that battle, I would say, quote unquote, where if the economic incentives are to like, okay, centralize all of this, like there has to be like some kind of soft pressure against that. And I think like Ethereum is a type of place where even if there's like a slight incentive to centralize it more, like there is a very strong community and like a very strong push for decentralization. I think that's like a winnable battle to like very intentionally keep it decentralized subjectively. So they're different optimizations for different chains. So it's not necessarily just an L1 versus an L2. I think that just generally speaking, broad brushstrokes, like L2s tend to fall in that latter category of like more opinionated, more active governance, and are optimizing more for real-time guarantees as opposed to like neutrality and long-term like nuclear war type resistance.
All right, thank you, John. Thank you for your 2x speed speech. Next up, we have a panel, the Endgame. How many of you here have read a blog post called Endgame? Raise your hand. Okay, Is it by Rune from MakerDAO? Or raise your hand if it's from Vitalik. All right, we've got an informed audience. Shall we?
Hello, everyone. I think we'll be joined shortly by a floating avatar in the universe.
Avatar.
Oh, there we go.
Hey.
Great. Hey, Anatoly.
Yeah, I hope you're having a good day, Avatar. Sorry, I haven't watched your second movie yet.
I mean,
It's pretty good.
It is true that Anatoly does look like he could have been an extra in the Barbie movie, but you know, I don't know what else to say about that right now. But nice.
This is my fame and cosplay for Oppenheimer.
Yeah. Well, you know, as we learned today, Vitalik prefers Bob the Builder, and maybe we'll have Bob the Builder next time. But as many of you know, this panel is the Endgame panel, and I think you know, part of this panel actually stems from last year at the last Modular Summit, which was sort of April 2022. So before Luna, when we were all, you know, felt safer, more comfortable, less annoyed at people in the world.
I felt less safe before the Luna collapse.
Maybe that's also fair. Safer as in, you know, I think the debate was actually quite different at that time. At that time, I think there was a lot more hype about monolithic architectures, and modular architectures were sort of coming from behind. And I'd say, obviously, some of the stuff that happened the last year made people flip, or you know, things change.
The Luna stuff, like, it had lots of moral lessons for me, but like totally nothing to do about monolithic versus modular. So I'd love to hear that case.
Yeah, I think that's more like app chain versus monolithic.
Yeah.
Luna thing, yeah.
Right, but like, okay, I guess to me, like, Luna was not bad because Luna was monolithic versus modular, or like on Ethereum versus on Bitcoin versus on you know, Cosmos versus or Solana or whatever, right? Luna was bad because it was a fundamentally bad design. Like the exact same design carbon copied onto Ethereum would have been just as big a collapseful failure.
For sure. I'm more pointing out that at this time, people were much more living in 2021 land.
Okay, this is true.
And like that was when, you know, I think the psyche was broken, right? So it was, I just wanted to say, like, give some context of like the last time we did this. There was sort of, modular was really the underdog.
Yeah, it's like, I feel like there are like a lot of arrows, right? Like, remember the scene where like Boromir just like gets like shot down by a bunch of orc arrows at the same time? And it's like, you know, first you have Luna, and then like you got the Celsius arrow, and then you got, and then you got the big FTX arrow, and then he's kind of dying, and then there's just like one extra arrow from like, what was it, I guess like DCG or whatever, just like shoots in. Yeah. But
So there's been a lot of arrows.
Indeed.
More than 3.
Indeed. Well, may all our future arrows be in beautiful diagrams.
There you go, exactly. Commutative diagrams only. You know, we're all secretly category theorists.
I don't know, I prefer non-commutative because, like, you know, we want to have progress, right? Like, we don't want to just, like, go from the same place.
All right.
No.
Well, clearly there's already even debate about whether anything has changed since last year. So maybe Anatoly and Mustafa, let's start with, you know, in the last year, what in the monolithic versus modular worlds has changed from your minds?
Yeah, so I think like one of the biggest changes is a year ago there wasn't really any kind of like roll-up frameworks. You know, there was like Optimism, Arbitrum, and other kind of like optimistic roll-ups, but there was no kind of frameworks to kind of create your own roll-up. Now we have, you know, Upstack, we have Arbitrum, Orbit, Rollkit as well. And I think kind of last year, a lot of the emphasis was the main reason why you need roll-ups is scalability, which is true. But I think there's been what I've realized over the past year is that one of the most underappreciated aspects of roll-ups and modularity is that it gives developers more choice and freedom over the execution environments. And that lets you do really cool things that just haven't fundamentally been possible before. You know, you can modify the EVM and add a ZK opcode so you don't have to, you can do more efficient ZK verification than just Groth 16, and that's really good for privacy. Or for example, Curio has modified their EVM game engine to add their entire game as an opcode on the app stack, which can be fault proven on their MIPS fault proving system. So I think this kind of this flexibility of execution environments is really underappreciated, and I think might be just as bigger or as important for impacts of the space as the scalability aspects.
Anatoly?
I think it's been really cool to see the development of rollups and having them ship and actually seeing their performance numbers. And from my perspective, I've never thought of them as scalability technologies because fundamentally, you're still limited by the bandwidth of the layer one. And if you can't exceed that, you can't really scale beyond that. We can do all sorts of other tricks, but that's kind of like the bottleneck. And when you start scaling that piece, we haven't yet seen folks go beyond what a monolithic architecture that can provide. So I think that's coming. I actually am pretty bullish on things like light clients giving pretty close to better than honest majority assumptions between shards and all these other things. So I'm excited to see for that next iteration in like the actual base layer. But so far, from my perspective, like actually the main use case for rollups is that, like giving new execution environments, giving new ways for devs to build, a full game as a fraud provable thing. I think that's a really, really cool thing.
Vitalik, any?
It's interesting because I think pre-2019, Vitalik was fully on board with the idea that rollups are not real scalability technologies, but then that was when I moved pretty decisively away from that paradigm. If you read my pre-2019 stuff, I was talking about how rollups aren't real scale because they're not a big O notation improvements, right? I talk about how regular blockchains are OFC, their capacity is linear in the capacity of a computer, but then sharding is OFC squared, right? But rollups are OFC times somewhere between 10 and 500, right? And for a long time, the mathematical purity side of myself got really hung up on that. But then at some point I was like, okay, yeah, fine, a factor of 10 to 500 is still a big deal. And that was when, well, I guess, and at the same time, we kind of exhausted, state channels and Plasma and all of those things that, just realized some of the fundamental limitations that they have in terms of how Plasma requires every object to have a logical owner and the whole defragmentation problem that, I'm sure if Carl Fursch was here, he could tell even more about because they tried to even actually implement that. Basically, yeah, a gain of 10 to 500x is still a gain. I think it is true that in practice we've been slow on getting there. One of the reasons why is because close to half that gain comes from data compression, and rollups have been pretty slow to actually implement data compression. And, there's all of these reasons of oh, well, we don't want to have L2 nodes have to be archive nodes and all of these things, but they're issues that can be engineered away, and even EVM parallelization, it's can be engineered, and there's a difference between sort of solved in your head and hard engineering slog solved, and that's been one of my own big learnings about the ecosystem. So I think, to me, I still look at this from the perspective of what is this going to look like even 3 years from now, right? Because we're definitely nowhere close to the frontier of what even currently known approaches can provide, right? And so.
So with that, actually, a great thing to talk through. There've been multiple endgame blog posts all over the internet, but all three of you, I'm sure, have very strong views on your views of what the end game should look like. So, maybe in your own words, define what you think the end game of the technologies you're really interested in should look like. What kind of things should they offer users? What kinds of things should they offer sophisticated actors to who maintain them? What should they not offer them? And, I think having an eye towards where you really think the long far future is. I think Vitalik's talk today ended with a very good picture of what he thinks the future is, at least in terms of, you know, the big proof thing.
Yeah. Yeah, I mean, like, my view on the future is definitely that, like, you know, we have proofs now, and I think, like, I've used the analogy that, you know, succinct zero-knowledge proofs are to cryptography what transformers are to machine learning. Like, they're or to AI. Like, they're this one single technology that is just so powerful all by itself that just, like, completely, you know, like, sweeps across decades of hard application-specific work by thousands of talented people and just says, like, okay, you know, bye-bye, you're gone, and replaces it with a vastly better alternative, right? And, like, that's just something that we have to adapt to, right? Like, anything that gets built today should be built with the assumption that, like, proofs exist as an ingredient. And, like, that was not really part of the mindset a few years ago. And, like, a lot of things change when that becomes part of the mindset, right? I mean, obviously, you know, like, projects like Mina were, I think, pretty early to that. And, you know, had the EVM been conceived even 5 years later, it would have looked very different. Had, I mean, even the beacon chain been conceived even a few years later, it would have, I mean, looked very different, right? Like, even when the beacon chain was built, it wasn't really built with this assumption of proofs in mind. And so if we have a world where we can just, like, assume that, you know, things can be proven and there's going to be, like everything that can be computed is going to have a light client of it and all of those things, like, that, in some sense, like, simplifies a lot of things. But you know, it still leaves open a pretty interesting design space of what kinds of things are going to exist, and there's a lot of details that you can talk about.
Yeah, so to piggyback on that proofs aspect, when I kind of, like, think about the end game, I think about, you know, what is scalability. I define scalability as throughput divided by the cost for an end user to verify the chain. And so for the end game, I think, like, how can we maximize throughput, transaction throughput, without increasing the end cost for the user? And that's only possible thanks to you know, proofs, you know, data availability sampling, fraud proofs, decay proofs. And that should be the case even in the world where there's centralized block producers, because we can still achieve the properties of a blockchain. We can still have you know, censorship resistance and verifiability even in a world where there's centralized block producers by using things like PBS and CR lists. But to kind of go further, to me, the end game, I see a world where it will be easier in the future for developers to create their decentralized application by deploying a roll-up chain than deploying a smart contract, simply because in a world where there's proofs, there isn't a good, strong reason for apps that are not too directly connected to each other to be sharing computational resources when the computation can happen on their own environment and simply have a proof that it happened correctly.
All right.
I think the biggest exception to that is composability, right? Like, yeah.
Anatoly, with that, I think we're ready for your end game.
Yeah, it's kind of interesting how different it is. So even going into the space, you know, 5 years ago, I always thought that the biggest challenge was the equal and fair availability of the data itself. And this came from my experiences as kind of like amateur trader through like interactive brokers and all these other systems. Whenever I had an algorithm that I thought had an edge, my trades would always be a little slower, and the data that I would need would always arrive a little later, and I would always kind of lose. And that's because I was playing in an unfair system. And the way that I designed Solana was with this idea that we have a single global message bus, and it tries to propagate all the information around the world simultaneously as fast as possible at the speed of light, with this kind of like end state being that, you know, imagine some crazy trade event happens in Singapore, that news wire still has to travel speed of light through fiber to a Bloomberg terminal in New York. But by the time that trader looks at it, a state transition propagating through Solana already adjusted for price impact. And the price information at NYSE is exactly the same as in a market running in Solana, because all that data is propagating at the same time. So this is a system that I envisioned, you know, back in the day, and this is kind of still what we're building, We're trying to reduce block times from 400 milliseconds to 200 milliseconds. We're trying to make sure that there's multiple concurrent block producers, so you can send your transaction to the most geographically closest one. There's competition for MEV. All of this stuff gets better and better and faster. And in that world, what's cool is that, like, I think Solana obviously needs to have a lot of hardware to do that because you're sending a lot of data. You're trying to keep it all together. And rollups are not going to help you. You know, like, you're not going to improve that system by splitting up state logically. Those effectively create logical shards, and you're not sending information globally to everyone. You're sending information only to some of the folks, which kind of breaks the whole point. So, but that system that we're building actually helps rollups. Like, in my ideal world, all of these settlement chains that have rollups should be all atomically sequenced on this one giant, super optimized, hyper-fast synchronizing engine, right? That's one giant global atomic state machine. But obviously, we still need trustless computation. We still need to make sure that users that can't afford the hardware have some guarantees that about, like, honest execution of these systems. And, like, I think the research in light clients that have been done by the folks, you know, like the teams on the stage, has been awesome. And I think in the future, like, Solana, for Solana to function, it has to have those capabilities as well. But the fundamental problem that I want to solve is that global state synchronization as close to the speed of light as possible, as open as possible to everyone in the world.
Okay, so let's suppose that we end in a world where there's only really one settlement layer, and your chain of choice becomes an L2 of the other chain. I only ask this question because Anatoly's been writing a lot of tweets about putting, making Solana, making ETH an L2 of Solana. How does that? I mean, first of all, Anatoly, maybe you want to explain your tweets, because I personally was very confused when I read them, but.
I was trying to create a straw man to demonstrate that what an L2 is there's a mechanical component to it, which is a bridge with better than honest majority assumptions that functions because all the data that you need to prove that this Merkle root that's on your L1 is correct is also on the L1. So you can then run the fraud proofs. You can basically, or whatever, compute a ZK proof, whatever it is that you need to do. You have all the information to validate this Merkle root, which the root itself does not have anything else, right? It's just a hash. So that's kind of like, you can do that with anything. You can actually take Ethereum L1 data right now, dump it into Solana, dump the state root that's computed from that Ethereum data, and then run an optimism style proof, right, to check if fraud has occurred, and then do the bisection and stuff like that. Does that make Ethereum a Solana L2? Mechanically, yes. Socially, no.
One reason why is because, like, there's the saying that, like, the sovereign is the one that decides the exception. And in blockchains, the exception is bugs and 51% attacks. And the question is always, like, what happens if Ethereum hard forks, for example, right? Like, if Ethereum hard forks, then there's a few possibilities, right? Like, one possibility is that the Solana bridge, and if we assume that it's a perfect ZK bridge, then according to the old ZK rules, the Ethereum chain will just start being invalid, and, like, that bridge will just basically create its own version of, basically its own Ethereum Classic 2.0, right? So that's, like, one, but then the question is, like, well, do the assets, like, what do the assets follow, right? And realistically, in this case, the assets would follow Ethereum, right? But, if you get into a world where, like, the majority of assets are rooted onto Solana and then bridged onto Ethereum, then, like, that would look very different, right? Or another world in which, right, and in that case, then, like, Ethereum would not actually be capable of hard forking unless there is, like, some kind of on-chain governance, right? Or a possible third world would be a world where the assets are all based on Solana, but at the same time, the Solana community is willing to hard fork whenever Ethereum is willing to hard fork, right? And in that case, that's, like, a construction based off of, I guess, some sort of like more deeper version of on-chain governance. And in that case, like you could, you would still be able to call Ethereum and L2, but it would be part of this ecosystem where sort of like things are basically, like willing to be part of the governance of each other. So I think like you basically just have to look at, like what happens if one chain or the other chain gets 51% attacked, and what happens if if one chain or the other chain gets 51% attacked and the community decides to do a user activated soft fork to kill the attackers. Right, so not like an easy slashing hard fork, but like a censorship hard fork where the community responds by picking the minority chain, and on the minority chain, the majority would have to either skip being on that chain or get slashed. And if they skip being on that chain, then they get leaked. Yeah, and then like what happens in that case, right?
So the thing is, though, that there's always going to be a subset of users that are hardcore cypherpunks, censorship-resistant maximalists that will always pick the right hard forks. They will always fork Solana and Ethereum towards the right state. So the real L1 is inside of all of us.
Then this, this gets into like yet another theater of the debate we've been having since 2015. Which chain is the real Ethereum? Who here thinks Ethereum Classic is the real Ethereum?
But I think
that's some good bravery. No,
that's way higher than I expected. I'm going to be honest.
Who here thinks Bitcoin Cash is the real Bitcoin?
Yeah, I mean, I think this kind of like gets into the debates of like how you define L2 and so on and so forth versus what's a sidechain. But like but those definitions aside, I still think it's an interesting proposition or useful to like have a validating, like Solana, the bridge between Solana and Ethereum would be validating. Like because most bridges between trust zones are not validating; they just have a committee-based assumption. But like if the Solana bridge to Ethereum at least verified the Solana state via ZK proof or fraud proof, I think you could, and then even if the DA wasn't on Ethereum and the DA was on Solana and there's a committee assumption, I think that would at least be, as far as I can tell, the same security properties as a Validium or an optimistic chain, which is like kind of like a much better scenario for like a multi-chain ecosystem.
So one thing that did come up in all of these answers to whether it's possible for one settlement layer to usurp another one and make it an L2 is the role of governance in these futures, in the modular or monolithic futures. And so, I think we've seen a lot of different variants of what qualifies as governance. I think choosing a hard fork, following certain people is a sort of weak form of governance. We just heard John's talk about POG, which I haven't fully processed because it was spoken at high speed, to be honest. But I think like where do you view the role of governance in your preferred modality towards the end game? Like how much, how minimized is it? How important is it? Where is it necessary? Where is it only sufficient? Where is it non-necessary?
Yeah, I mean, I really feel like this upgrade thing, the roll-up upgradability, is the kind of like core, like the core nuance. There's been a lot of debate about like, Kevin from Optimism is arguing that all roll-ups are sovereign, and there's kind of a very controversial statement. And the reason why he argued that is because he argues that all roll-ups can just, the community for roll-up can just upgrade a roll-up. Ultimately, what a roll-up is what the community defines that roll-up to be, and not the bridge. But I think there's some interesting nuanced questions about like how do we have upgradable roll-ups while keeping the security properties of a roll-up. Like the only kind of like way I know about I know of doing so is to have an upgrade delay and allow users to mass exit, which is not clear if not clear how practical that would be in an actual practical scenario.
Yeah, this is a tough choice, right? Because I think like right now layer 2 rollups are, I guess there's like two camps. There's sort of the more activist side, and if you're on the more activist side, then like I think the safe and responsible way is to like choose a delay number, and like it could be somewhere between 30 and 365 days probably. And if an upgrade happens, and if you're not happy with the upgrade, or if governance gets taken over by evil people and the upgrade involves stealing your money, then like you just have to leave. which is good enough for most users, but it's not good enough for like really long-term applications that want to base themselves on that rollup, right? And then on the other side, like I know like Scroll, for example, you know, like really values the idea of like neutrality and like sticking to Ethereum principles and kind of seeing itself as being a kind of an extender of Ethereum land, and like something like that might be willing to like say like, hey, you know, we're at code level, we're not going to be willing to like deviate from anything but being a you know, a copy of the protocol spec. And like if they do that, then that doesn't like, it takes away that risk for applications, but then it also opens up this interesting question of like, if Ethereum itself upgrades, then like how would Scroll end up copying that? And then this gets into like protocol questions. Like I know this is one of those things that's like controversial within the Ethereum research team even, right? Like there's some people that are in favor of enshrined rollups or an enshrined like rollup assisting precompile. Like basically imagine a precompile that just does EVM validation, and it just does whatever EVM validation means during the specific block. And like maybe you could let it like do either the current hard fork or the previous hard fork, and then like in the back end, clients would just implement that by like waiting for, you know, like whatever their preferred ZK EVM proof is, for example, right? And like if you do something like that, then like you can preserve that kind of like that tight coupling for the projects that want to do that. And then if you don't do something like that, then like layer 2s would basically need to have governance for the like on-chain governance for the sole purpose of keeping, at the very least for the sole purpose of keeping up with whatever layer 1 does, right? So that's like that's one of those trade-offs. So like, and then obviously the you know, the other side of this is like this kind of underexplored class of like crazier ideas where like someone creates a layer 1 where that layer 1 is like intentionally willing to be more, you know, like activist and and like basically hard fork in such a way that like even layer 2 like assisting layer 2s with you know, like hard forking along with those kinds of changes. So yeah, I mean, I know, there's like a big set of possibilities in off-chain governance. There's obviously a big set of possibilities with on-chain governance as we see it, and especially once you start like properly moving away from the coin voting stuff. And then there's like a whole set of debates about use cases of governance. Like, are you protecting against hacks and that's it? Are you improving the protocol? Are you doing public goods funding, right? And then if you do public goods funding, then like, do you do it kind of by enshrining an on-chain mechanism, or do you do this kind of like retroactive off-chain thing the way that Zcash does, right? It's like every 4 years they basically, as far as I can tell so far, they like decide, you know, who the public goods funders, who the top level public goods funders are, and then they do a hard fork to give them the block reward, and then that gets revisited every 4 years, which is like kind of cool in its own way, right? And Zcash has made the choice to be more interventionist than Ethereum and Bitcoin are. But yeah, I don't know. It's a big design space.
But do you think there's a way to allow rollups to have upgrade mechanism with the same security properties as a rollup, but without coin voting and without enshrining that rollup into the L1? Because that's one of the reasons like some people are interested in sovereign rollups.
Right.
Yeah.
Right. Well, I guess the challenge with sovereign rollups is like if you start using any assets where those assets are not registered within that rollup, right? Then it's like, well, for those assets that you can't be sovereign, right? Yeah, unless unless you have like more activist off-chain governance.
Yeah, for sure. But I think like even though L1 is truly sovereign, like you have, you know, USDC and USDT, which is kind of like a you know, a non-sovereign bridge between Ethereum and Circle or Tether. So it's definitely, you know, sovereignty is a spectrum. And, yeah, there's definitely trade-offs though between sovereign rollups and non-sovereign.
Right, that is true. I mean, you definitely could have try to get every application to have, you know, separate instances on all of the different rollups, and so you don't like even cross rollup kind of bridged assets don't exist anymore, and then everyone can be sovereign. But well, if you do that though, like you would not be able to, like ETH would not be usable on rollups, right? Because ETH is like by definition homed on Ethereum. Yeah.
And Anatoly, any thoughts on governance?
It needs
I mean, like the major problem are 0 days. All these systems are too complex to not have some really fast path to upgrade and deal with a 0-day bug. That's kind of like the end of the day. Like you have to, I don't know how long it's going to take for us to construct something that is so simple that everyone agrees this this can be upgraded with a 30-day delay. We're okay with that. And if you have a fast path for 0 days, you're kind of introducing honest majority assumptions. And I think that's mostly fine. If that's what we're dealing with, I think we then have to be very, very careful about how we construct those majorities. Should they be like well-known security firms, et cetera, like kind of the proof of governance talk, I think went into a lot of those considerations. But like, I think it's really, really tough to avoid those.
I think like a couple nuances on that. Like one is you technically don't need you don't technically need a fast path to upgrade. You need a fast path to freeze and an arbitrarily slow path to finalize whether or not you're going to upgrade. And then the other thing is, I definitely do not think that upgrade buttons should merely be a majority, right? If it's merely a majority, then whatever proof system you're doing technically has no votes, right? And you might, I think you need to have at least a 75% threshold. This is, I mean, the thing that I've been pushing for in the stage 1 definition, obviously, but I do think that being greater than 50% is important, because otherwise, it's mathematically true that the code itself has no votes. And then, well, the other thing is, I guess, one of the ways that the Ethereum ecosystem is doing this is they are doing this kind of inversion thing, right? Where, I know some of the rollups want to do this, right? They want to have multiple ZK VM implementations, and then the Security Council only gets activated if at least one of them disagrees with the other or something like that, which is, I think, an interesting path too, as long as the implementations are being built independently enough.
Yeah, I think at some level, it seems like everyone thinks that there is some necessity of governance at the bare minimum, but it may be, sort of to summarize, in some ways synchronizing multiple chains in the case of the modular world, or in Anatoly's view of the world, kind of response measurement. Now, maybe let's take a tiny detour. Imagine you had to come up with a complement for the architecture that's the opposite of the one that you like. You had to find something really favorite, you were just your life depended on coming up with a really good complement for the other architecture. What would you say to your fellow developer?
I mean, speaking of Solana specifically, I mean, the way I see it is that Anatoly and Solana is trying to build. The way I see it is scalability ultimately has trade-offs between scalability and composability, and so even at the Ethereum-centric roadmap, you have some liquidity fragmentation of liquidity, let's say optimism and arbitrum. But the way I see it is Solana is trying to see how much throughput we can get as much as possible without any composability sacrifices whatsoever. That's why Anatoly doesn't see rollups as a scaling mechanism, because it defeats the properties of the system he's trying to create, which is basically, as I understand, the vision is decentralized version of the New York Stock Exchange. But so what I appreciate about Solana is that they've made some great advancements in kind of execution environments. The parallelized execution environment, that's a massive improvement, and I appreciate that. Solana is actually taking trust minimization a bit more seriously over the past year. There's been some work and proposals over trying to create light clients and implement fraud proofs for Solana, and even some proposals to see how we can add data availability sampling to Solana.
And I appreciate that there's a strong technical team, and I appreciate the willingness to just say, here's some set of use cases that kind of we understand, we're passionate about, and we're going to basically optimize and be willing to make trade-offs to do the best that we can for them.
Anatoly?
Well, I think the data availability sampling and the whole fraud-proof construction is beautiful design. It's awesome. So, and that actually is I think came out of the research of both of the teams here. So pretty cool. And like the really cool thing is that like everything's open source. As soon as those folks had really good ideas, I was able to understand them and start thinking about how to apply them to the Solana stack.
If we fast forward, to kind of applications that you find interesting, either within ecosystems that you're working in, or sort of maybe even in the other ecosystems, what are some applications you're interested in 2023 and 2024 that will be used? I think a lot of EthCC this year, at least from my perspective, has been quite a bit of infrastructure, seeing a lot of updates on how certain proving systems are working, understanding how those developments have moved on. But we do at some point have to find some other applications in them. But, obviously you all probably have tons of examples of these that you're most interested in. What are they?
Yeah, I mean, I think in the short term, there's kind of like been some really crazy progress in like gaming kind of rollups. Like Curio managed to kind of like run a real-time strategy game with a 0.5-second tick engine using a modified EVM that adds that part of the game as an opcode. And there's kind of other stuff like Argus and other teams are working on interesting game engines. Now, I don't think gaming is the kind of like ultimate purpose or like the most real-world case of crypto, but I think historically what we've seen even in computing, a lot of advancements in computing has come from gaming. For example, the concept of sharding actually originated from gaming. So yeah, I'm just kind of interested in following those developments there, and I think in the long term they will have significant impacts on applications outside of gaming as well.
I kind of want the OG application to come back. Like I want people to pay for coffees with ETH, yeah. Remember back in 2013 when this was the big thing, and I remember this was actually the very start of my Bitcoin trip around the world, where we would have I went to Boston and I went on a pilgrimage to Veggie Galaxy and Thelonious Monkfish because those were the two restaurants that accepted Bitcoin. And then we had the Bitcoin Keats over in Berlin, and York Platzer got 10 restaurants in a block to accept it. I want that culture to come back, and I think a big part of the reason it died is obvious, which is fees got too high. But the original pitch back then is hey, this is cheaper than PayPal, but then it stopped being cheaper than PayPal. But with rollups, it actually will be again, which is amazing, right? And I would love to see some of those amazing OG things that we did back then come back now that the world is, or the ecosystem's starting to be ready for them.
Yeah, I think that will definitely happen. We're seeing banks already using USDC for settlement. I think that will eventually be exposed to the end user. It's being used kind of on the back end, but it will eventually be exposed to the end user.
I'm impressed. None of these applications so far have had any advanced cryptography. So, Anatoly?
I want the payments privacy preserving, but
okay. Anatoly?
Yeah, I would say simple things like payments and DeFi. I guess DeFi can be very complicated, but I think both of those really serve the two fundamental things that crypto provides, and that's self-custody and this idea of a global source of truth, right, for pricing or the ability to transact. I think those are very transformative at scale. If you have everyone in the world that now has cryptographic keys that they know can move value around, everything else can be built on top of that, real world governance, right? If everybody knows that we can all communicate and coordinate with cryptography, we can actually build very quick, fast, global political movements that can take on action and solve real world problems. I think, but the foundation is that cryptographic base of users that get self-custody, get what they're doing, they know what this thing means. So yeah, the simple things. I'm on Vitalik's camp here.
Well, I mean, we are in France, and DeFi is the French word for challenge. Okay, fine, it's pronounced DeFi, but come on.
I'm more generally also interested in experimentation around DAOs and kind of form ways of organizing people on chain. There's there's a lot of different kind of proposals: DeFi, ReFi, Disco, DAOs. A lot of interest. I'm kind of excited to see how that goes as well.
My last question, which is a false trichotomy, but you have to pick an answer anyway, which is Barbie Oppenheimer, or you think it's really bad that we're lionizing Oppenheimer via a movie?
I choose Bob the Builder.
Oh, sorry, I forgot Bob the Builder. I forgot Bob the Builder.
I want to see like the crypto space come up with its own like epic, you know, like we've had songs, right? Like remember there were Bitcoin songs back then. There was like that "Love You Like a Bitcoin" parody that like continues to be one of my favorite songs to this day. Like it's actually good as a song despite being a parody. There's I think didn't like Simon de la Riviere write a novel at some point that I would love to see just like us come up with a movie that is like uses themes from these top that we care about, but is like actually good as a movie at the same time.
I unfortunately saw that there was an online TV show about SBF, so maybe that's not the right type of movie, but that is coming out. It's an animated short.
I see. It's an Oppenheimer for a different cause. Yeah.
Yes, exactly.
Yeah. Price is definitely duked.
Anatoly, I mean, you look like you're ready to be in the Barbie movie, so like you got to have some opinions here.
This is me cosplaying Feynman, so definitely Oppenheimer.
All right. Well, thanks everyone for joining us. It's been a great day of talks. We talked a lot about the public broadcasting system of the U.S. Proposer-builder separation, and hope you have had a good week in Paris and enjoy.
Thanks everyone for staying for the entire morning plus an entire day that started at 2 p.m. Just a few closing remarks. There are supposed to be slides, and if they don't appear, I will still say the same things. So basically, the reason why we had went on this PBS Day journey is to seek out an answer that I wanted to know, me as a community member, take off my Flashbots hat. What can I do to contribute to the PBS research that is critical to fight against essentially the centralizing force of MEV? And so this is something that I wanted to have as a call to action, which is to build as a community a open R&D map for the ecosystem on the topic, on the problem space of PBS. And so, of course, I stole a few slides from every speaker today. This is one version of the end game, thanks to Vitalik. And whether you do believe in the end game of approved singularity or not, the question really is, where are we now? And of course, understanding that there are a lot of ecosystems, different like participants and contributors sitting here. So this may be just one of the many examples or one of the many roadmaps that you're familiar with. The one on the right was, I believe, at the end of last year, Vitalik posted the Ethereum roadmap that is quite modular. And so where was PBS back then? It was right there with a couple components. It looks like we're 25% there. And today, we got a zoomed-in version of a heart-shaped roadmap from Mike Neuter. And there is still a lot of uncertainties to be figured out in terms of actually how do we actually get rid of certain intermediaries that is currently not quite accounted for in the protocol, as well as many other technical challenges. So I started to ask myself, okay, as a non-EF, non-core researcher, non-core developer, what can I do to actually understand how big, what is the lay of the land, and what can we do individually? or as part of a project. So I went on a rabbit hole of mind mapping. So, of course, we have already on Ethereum MapBoost ecosystem that's in operations, that Flashbots, many of my teammates are working on, along with many of the EF and the community members contributing to it. And it's up and running. There's also a healthy ecosystem that's beyond just the MapBoost ecosystem that is doing a lot more of the R&D work. So after I actually interviewed around 10 to 20 researchers who are actually working in a space, working on PBS, I realized that I really can't recognize much on this mind map anymore because it has expanded so huge. And I realized there's a lot more problems than I realized there was. And ultimately, these questions are very hard auction design problems, very hard consensus design problems, and there may not be a right answer. And when I look through from the farther away research problems, zooming into the development and finally the operational problems, I realized that the reason why I have a lot less branches there is because there's a lot more to be done by the community. But yet, we kind of just relied on, hey, the EF is going to take care of it. Not my problem. But that shouldn't be the case. There is so much we can do just in terms of figuring out in today's up and running out of protocol PBS MapBoost ecosystem, how do we keep relays economically sustainable? That's a research question. How do we actually have data transparency such that we could enable us to keep the ecosystem in check? And how do we actually contribute to the prototyping, the economic audits, the security audits of all of the early research work that is going to production before they turn into an EIP? Those are just open-ended questions unaccounted for. So it's a call to action, and this doesn't just apply to L1. Today, we heard, I think for many of you here, probably for the first time, for me probably for the second time, because I interviewed every single speaker, what would PBS on L2 look like? And this may be just a starting point. So I'll end right here with essentially the theme of today. Let's turn zero-sum game into positive sum. Let's keep crypto decentralized. Thank you.
I'd also like to ask if we can all give Tina one more round of applause for actually curating the whole day as well. Thank you, everybody. Happy hour begins.